三个。Hi, morning, everyone. My name is Wuyang Chen, and here is our fifth fifth version of the UG2 challenge and workshop. And I think our audio and the screen sharing and the video should be okay. And if you have any problem, please feel free to send us any messages to the chat, and we will have some co-hosts to help coordinate, see if any problems. And I'm very glad to see that our UG2 workshop is now 5 years old, and every year we bring new data set, new challenges, and new speakers on different topics to our workshop. So to keep our workshop alive and keep updated to the community. And this year, our three topics on the challenge includes the dehazing and action recognition in dark videos and air turbulence. So it's still a very hot topic and long-lasting topic about understanding and resolving the degraded visual environments in the machine learning system. So nowadays, we can still see many different kinds of downgraded or perturbed images or videos in our daily lives and even in many standard ML pipelines, like the blurred ones or low light ones or raining or hazing. All these kind of images are uploaded or processed in many cloud machines or ML pipelines, even on our edge devices. So most of the applications are actually trained on standard images, but these all degraded images are not well handled by many standard ML pipelines. And another important issue is that when this kind of images are actually a kind of domain shift to the ML system. So it's very easy for the ML system to train on standard images, but then forget and then fine tune on this downgraded images, then forget about the original distribution. So this kind of degraded data can raise a lot of problems. So as I mentioned before, the current system is trained on many clear environments, but this in real life needs, we actually are facing many different kinds of complicated unconstrained degradations. So what's our aim? Actually, our aim through these 5 years are not changed. We always seek to first build large-scale data sets that is collected from various degraded visual environments. And then we hope to leverage these large-scale data sets to provide both the low-level enhancement algorithms and then seek to bridge the gap between the low-level algorithms and the high-level application algorithms. So these two goals are not changed in these 5 years, but we keep improving both our data set and our algorithms. And this is the past 5 years, and we keep improving the challenges. And in this year, we have first time we have 3 challenges: the object detection in haze, and we have the action recognition from the dark videos, and we also have the atmospheric turbulence mitigation. And since we have 3 challenges this year, we have a breakthrough in both the number of teams that registered and also the number of final submissions to our challenges. And we have 289 teams, which is about 100 more than last year. And for the final submission, we have 400 successful submissions, which is almost double last year. And then we have 9 teams that is awarded. And we would like to share our warm congratulations to these teams. Okay, the first challenge in our workshop this year is about the object detection in haze. Although we have seen many haze data sets for either detection or segmentation in the past few years, our data set this year is the first time that our data set first the fog is real in the pictures, and then it is the magnitude of the fog is controlled, and then it is paired. We have all the objects in the data sets they are all paired. So we have a clean image with objects in there, and we keep the position of the objects unchanged, and we keep changing the magnitude of the fog. So everything is real and paired inside our data set. Also, this is the area data set since we have a drone flying on top of the objects and taking the photos from top to down. And we have 177 paired haze and clean images, which is the frame selected from 12 videos, and we also have annotated clean image for the vehicles. And then we have 50 his image is reserved for the fine testing. So this whole data set is a small scale, but we also allow the teams to use any unlabeled extra data set. So our best team can even achieve over 90% of the MAP from the University of Science and Technology of China. And actually all three teams are above over 93 MAP. And the second one is from Alibaba Group from China. And also the third one is from the South Korea. Then for the next change, I'm about to shift to Yue Song. Yue Song, can you hear me?
Yes, hi. Can you hear me from there?
Let me unmute you actually. Just 1 second.
Can you hear from me? I think I'm already unmuted.
You are also the co-host, right?
Yes, correct.
1 second. Please allow me a second. Just 1 second. Could you check send message to the WeChat group to see this is him? I see.
Hi, can you hear me?
So you turned your mic on, right?
Yes. Okay. I think I think the
I really can hear you, but
there's no sound in the scene live scene, right?
So, could you can you hear Yue Song's voice from your laptop? Okay. Yue Song, just 1 second. Yue Song, could you have a try?
Hi. Can hear from me?
Yeah. Yeah.
Okay. Cool. Okay. Hi everyone. I am Yue Cong from the Institute for Infocom Research in Singapore. I'm very glad to present our this year's challenge on action recognition from dark videos. Okay, so this is actually the second year we've held this challenge in this UG2 Plus challenge and workshop. So we noticed that while action recognition has been applied in various real-world scenarios, such as smart homes, autonomous driving, etc., actually most current action recognition methods focus on videos shot under normal illumination. So in the meantime, there are various scenarios where videos shot under adverse illumination, or for example, in the dark, is actually unavoidable. For example, scenarios such as night surveillance or autonomous driving at night. So it is actually therefore highly desirable to explore possible methods that are robust and could cope with these scenarios. This is in line with the trend where over the past few years, there has been a remarkable rise of research interest with regards to computer vision tasks in dark environments, which have been actually expanded to the video domain more recently. Meanwhile, given the high cost of video annotation, it will be unlikely that such videos are labeled exhaustively in real-world scenarios. With the availability of a variety of large-scale labeled videos shot under normal illumination, this challenge aims to fully utilize these videos with possible pre-processing or post-processing steps to capture actions with high robustness towards darkness. So therefore, the UG2 Plus Challenge Track 2 aims to promote video-based action recognition algorithms, robustness with special focus on dark videos. We drive these participating teams to utilize semi-supervised algorithms, which could utilize both clear videos and dark videos. Furthermore, given the high cost of video annotation, this challenge also aims to elevate the importance of eco-friendly and efficient learning by decreasing annotation costs. This challenge is actually based on the ARID dataset, which is the first real-world dark videos for action recognition in dark environments. Okay, the next slide, please. Okay, so we can see that compared to last year's edition, this year our challenge has been vastly upgraded. We've included 11 categories of daily actions, up from 6 from last year. And also our data set has been largely expanded. You can see that we've included almost doubled the number of videos provided to the participating teams. And so for this year, there's actually a total of around 6,000 videos provided, both dark videos and normal videos from current public data sets. For the testing videos, we've also largely upgraded from 722 videos of last year to 3,100 videos of this year. And we've also seen a very large rise in the number of participants as well as valid submissions, with almost 5 times, actually more than 5 times, the number of submissions, valid submissions from 20 teams. And we can see that the competition is actually very fierce among the teams, especially among the top teams, where actually there's only a 5% gap between the top 5 teams. And so here I would like to congratulate our top 6 teams. So the first team is from TAL Education Group with an accuracy of actually around 91%. The second team and the second runner-up, so the first runner-up and the second runner-up actually is just divided with only 1 sample. So the first runner-up is Nightcrawler from Shenzhen Institute of Advanced Technology, CAS. And the third team is actually from Sun Yat-sen University, Titan 5 HPL. And due to the very close results, we would also like to honor the 4th to 6th teams, which are from Sun Yat-sen University, CT Yun, as well as a collaboration between Shanghai Jiao Tong University, NUS Singapore, and Meitu. And that's it from my side. Thank you very much. I pass on to the third track.
Thanks, Yue-Song. And now let's welcome the Zhiyuan from the third challenge to introduce his challenge. So, hello everyone. I am Zhiyuan Mao from the Purdue University. So, the third track of the UG2 Plus challenge focuses on the imaging through atmospheric turbulence. Atmospheric turbulence is a fundamental factor that limits the performance of the high-resolution long-range imaging systems. Imaging through turbulence is both an old and a new problem. It is an old problem in the sense that this problem has been studied by the astronomical imaging area and by the optics society for decades. So there are really a lot of tools that are ready to use. However, it is also a new problem in the sense that what we are looking at is the near-ground horizontal imaging. This is bringing a lot of new perspectives and challenges to the field. For example, our image will have a lot more diverse image contents. We are also probably handling some moving objects across the scene. In addition, the acquisition device, the cameras that we are using may also pose some new limiting factors here. So recent years, we can see that there's an increasing interest in the problem of imaging through turbulence because there's an increasing interest in the long-range visual recognitions. So our third track aims to promote the development of the atmospheric turbulence mitigation algorithms. So participants will design the image reconstruction algorithms to remove atmospheric turbulence effects from multiple input frames. Okay, so we will evaluate the reconstruction algorithms with the text recognition accuracies. So for utilities, we provide 500 long-range text sequences for text recognitions. In addition, we also have 50 artificially synthetic hot air turbulence sequence, which contains aligned turbulence distorted and clean image pairs. This can be allowed for use for PSNR calculations. All the training data used in this challenge are synthesized by our latest physical-based simulators. So this year, we have winners from the TAL education groups. We also have runner-ups from the Tech University of Korea and the University of Maryland. So congratulations to the winners. Finally, as a closing remark, we are planning to run the same challenge next year as well, with some upgraded new data sets. So stay tuned to our website. Thank you. All right, thanks, Zhiyuan. And we appreciate the great our great sponsors from NVIDIA and Army Research Lab. And as Zhiyuan mentioned before, that we will continue our challenge next year. So keep tuned on our website, and we will broadcast our new challenges and perhaps new data sets. Thank you very much. And now I think I see Professor Qifeng is already here. Let me see.
Yeah, I'm online. Hi, Ouyang.
Just 1 second. Hi, Professor Qifeng. Qifeng Chen, can you hear us?
Yes, I can hear you.
Yeah, okay, I can hear you now. And you may want to share the screen.
Okay.
And I will give a short introduction here. Yeah, I can see the screen. Let me make myself full. Just 1 second. Okay, that's great. Hi everyone. I'm very happy to start our 9 wonderful invited speakers right now. And our first speaker is Professor Qifeng Chen. And he is now an assistant professor of the CSE department and the EC department at the Hong Kong University of Science and Technology. And he received his PhD in computer science from Stanford University in 2017. And he has more than 50 top conference and journal papers. And he is also named as one of the 35 innovators under 35 in China in 2018 by MIT Technology Review. And he also won the Google Factory Research Award in 2018. And he is also a co-founder of the startup Lino in 2017. And thank you, Professor Chen, for joining us. And I think you can feel free to start.
Thank you, Ouyang, for the introduction. And it is my pleasure today to share some of my research with you. And today's topic is about how we can utilize polarization images and dual view cameras to see something that cannot be seen normally from a single RGB camera. And in today's talk, there are mainly 3 parts, and I will spend a few minutes to talk about some related research highlights in my research lab. And then I will talk about how we can utilize polarization images to estimate the shape, especially the normal maps in complex scenes in both indoor and outdoor environments. And then I will talk about a method that can reconstruct high-resolution images from our normal smartphones, like an iPhone, and how can we get the 8K image quality by utilizing, the images from telephoto and wide-angle cameras. So now I'm running the visual intelligence lab, and our lab focus on solving visual challenges that arise from smartphones and autonomous vehicles. And there are a few aspects I think I can share with you briefly. One is the AI-based sensing technologies. And recently, I also have some work about the invertibility in image processing. And I also do a lot of research in image and video processing and synthesis. And lastly, I am also interested in autonomous driving, and I will focus on the safety aspect. How can we do the safety aware planning and prediction? So here are some related research to this workshop. For example, we have some work about how we can see and in a very dark environment to generate high quality images and video in a very dark environment where we propose to learn from the raw sensor data. And to see better for distant objects, how can we do better digital zoom? And we also propose, instead of starting from the RGB image, we unify the ISP in a camera and the super resolution to achieve optimum the digital zoom quality in a learning-based pipeline. And for 3D sensing, we propose a 3 cameras vision system where we can see the object, to get a depth map for objects that's beyond 300 meters, which is beyond the range LiDAR camera usually can achieve. And also know that for LiDAR camera, it's very difficult to get dense depth measurements for distant objects. And recently, I have some works in terms of the invertibility in image processing and restoration, where we can easily convert different modalities. For example, between raw data and the RGB image, between video and image, and between image and binary encoding. And in fact, this problem is image compression. And we can also convert novel view synthesis model to a single image where we can decode it from a single image. And in a recent work in AAAI, we introduced invertible image processing where we can make the image operator to be invertible for a lot of operations. Let's look at one example. For example, in invertible ISP, we would talk about how we can generate high quality RGB images from the raw data. But at the same time, there are also research about how we can recover the original raw data from the RGB image. Because the raw data is in a higher dynamic range that can be benefit HDR reconstruction, image retouching. And we unify this by an invertible neural network. And I'm also interested in image and video synthesis. For example, we have quite some early work in semantic image synthesis. And recently, we also work on future video synthesis and how we can, we have some general approach to predict the future frames for arbitrary video. And we can also do 4K video in painting by an internal method. This is related to our talk today, and we can utilize a polarization sensor to do the reflection removal, or use flash to do better reflection removal. And our group is also interested in how we can utilize gain inversion. So the image you see on the left, the input image is a natural image, and we can perform very high quality gain inversion where you can see the background is also closely matches the the original image in our editing result. On the other hand, my group also does some research in safety aware autonomous driving. And for one instance, how can we predict some unseen vehicle, some unseen people in the future? For example, in this video, it's very hard to predict there will be a girl coming out from the left, but we may want to predict the worst case. So in today's talk, I would mostly introduce two recent papers in our research lab. One is straight from polarization in complex scene, where we can estimate the high quality normal maps for both indoor and outdoor. And it is not like getting the normal map from a depth sensor, because for a lot of depth sensor, it has a short range. And our approach is a passive sensing based approach. And then we'll talk about how we can, use, the two lenses. Sometimes we can even have 3 lenses on a smartphone. How we can utilize this, camera to achieve very high quality image construction. So let me introduce what polarization is. The light has some polarized direction, and normally when we have some polarized light, okay, when it is when it goes through some material like glasses, it would be reflected, and or some would go through it, and it will become polarized light, and it will be good to understand the material. So there will be some sensor from Sony which can provide the polarized results that would be quite useful for our research. Okay, so and here is some visualization of the polarization image. For example, on the left, we can see a normal camera where we, there is a blue cube. It's hard to tell, the physical property, but in the polarization direction image, we can very clearly see the like the direction of the such a cube. So it could be beneficial for some tasks. And there's some related work that has been done in our group where we can use a polarization sensor to get high quality reflection removal. For example, this is the input image with some reflection, and here is our recover the background image. This is the reflection image because in the in the polarization image, where the reflection can be easily seen, by the degree of polarization, which is relatively high on some reflective object. And in today's focus, we will focus on how we can do the shape estimation from polarization sensor. So there are many different types of sensors for shape acquisition. We can have photometric stereo, but that's not very convenient to use, and also we can only make it work for a small object. And we have some time of flight sensors, LiDAR sensors, okay. But when it has a long range, then we can only get a sparse, usually estimation for the very distant object. There are some pros and cons with different sensors, and we will think whether maybe we can use polarization sensor, and we can estimate high quality surface normal from the polarization image. And well, certainly there are also a lot of works in RGB based approach for shape estimation. But there are some challenging cases like this. If we have printed the paper, okay, we have printed the paper, it's like stair, and then the RGB based method would be full because it would focus on the semantic information rather than the actual physical property. And in fact, our polarization based approach can understand this is actually a flat surface. So we can give the correct shape estimation. And in this work, what we focus is the polarization. First, we will have a very dense observation. For each pixel, we will have an observation. And if we visualize the polarization angle, from this, you can feel that there is some, relationship with the direction of the material. And so I think maybe we can do that to get a high quality surface normal estimation from such a polarized image. Yeah, so here is our output normal map. So so there is some strong connection between polarization and the normal. So it's there is this Fresnel equation has linked the surface normal and material, certainly also lighting condition, and there are different properties in a unified formula. So in fact, the physics-based shape from polarization is complex. It requires a lot of assumption. So in fact, if we have the material property, then we can derive the normal directly. So, but the challenge is here. So there are two cases. Okay, there specular case and also the diffuse case. And there is also this refractive index about the material, which is unknown, usually when we do the surface estimation in the wild. So unless we have all these property, we know whether it is specular reflection or diffuse reflection. We also need to know the zenith angle so that we can derive the normal. But this is not feasible in the general scenario. So there is a lot of limitation in applying the physics-based shape polarization. And previous work need to adopt a lot of assumption. For example, they may have some object level data where we can roughly assume of a graphic projection. And for the object material, okay, it could be maybe the whole object will share the same refractive index. And it could be purely specular or purely diffuse, so that those equations can work in according to their equation. But for complex scene, all this assumption cannot hold. So instead of going from the physics-based approach, we would consider a learning-based approach. And what we want to do is we want to map the polarization image to the corresponding normal map. And one of the first challenges, certainly, we need to create some data for our task. So so we create the first scene level shape from polarization dataset, and we use a 3D printer to print this mount and to keep the two cameras together. One is this high quality depth sensor, and here is the polarization camera, and we can capture the the polarization image and the depth maps. And we do some registration. We would for the normal map is like the high frequency part of the depth map. So if the depth map is noisy, the normal is not that accurate. So we would capture like 50 depth maps and then do the averaging so that we can get a relatively high quality depth map so that we can derive the corresponding normal. And then we would manually mask out some visually inaccurate normal and have some high quality normal maps for our for our model. And another challenge we found is actually the polarization intensity is also dependent on the viewing angle. And unlike for image, okay, we have this translation invariant property, but for polarization image, it doesn't have such a translation invariant property. So to address this issue, we wanted to work for perspective projection. We simply introduce viewing angle encoding, so that for each pixel on the image, we would add the viewing angle so that it can know what viewing angle it is. And then we for the polarization image, actually for each pixel we can receive for each point we can receive the polarized light from 4 different angles. And from this original polarization image, we can derive the unpolarized image, the polarization angle, and the degree of polarization. And then we put all of this into encoder decoder with multi-head attention, and so that we can get the lastly estimated normal. So here is some result. Okay, for the first row, we can see that there is a printed paper attached to a wall. Okay, so this is the input image about the polarization angle. And then if we don't have the polarization information, we will make mistake. And this is our result. It's basically like flat. And we can also make it work for the outdoor scene. And here's some result for the indoor scene. So we also evaluate our method on some existing data set on the object level, and our approach can still work well. And this is our result. Okay, and here is our result. I think we have seen such an example before. So for the shape estimation, we can see that the polarization can provide the very valuable Q, and I believe it may be also useful for some other scenarios, such as maybe in the hazy environment, we can use polarization to do better haze removal. And one of our, although our data set is only collected in indoor, and we can reasonably generalize to the outdoor scene. Based on the quantitative evaluation, and we are significantly performing better than the prior work. Okay, so having looking at the polarization, and we are also interested in looking at how we can utilize the information beyond a single camera. So I think most of the modern smartphone will have at least 2 cameras. One is the telephoto camera, and another is the wide angle camera, and they have different field of view, and how we can combine them to do better image reconstruction. So it's very common, such a configuration. But know that the 2 cameras are not from the same camera center, so there will be some challenge in the alignment. And for the DSLR camera, the optical zoom is usually can be adjusted by changing the focal length. But for the smartphone, it is not the simple case. If we adopt a similar idea for the smartphone, okay, where we can have a very good optical zoom, but the challenge is if we very big, the camera would be very big. So most of the camera smartphone manufacturers will adopt the dual or multiple camera system, and they will have different field of view. And how we can utilize this to have better imaging quality. There is some related work. For example, we have done some research how we can use stereo image to remove the water drop. That would be useful for vehicles in rainy days. And here the problem is different from the stereo scenario because the field of view would be quite different. For example, for this scene, the telephoto would provide a 4K image in the center of the image, and there is another wide angle image. Another 4K image here. And then our objective would be how we can combine this, this pair of 4K image to get the 8K image. So that should be visually better by at least much better than the wide angle image. So there are a lot actual challenges that do not exist in the stereo cases. So certainly we still have the geometric alignment. They are not, the two images are not shot from the same camera, and then we will have some color mismatch. Okay, the color of the the color distribution of the two cameras are not the same for the same patch. And then because the field of view would be different. And then for the low resolution one, where we call the wide angle one would be the low resolution, and it will be blurry. And then the telephoto image can serve as the reference image. So there, we can also have a lot similar reference image for this low resolution patch for the super resolution. Due to the resolution difference, it's also challenging to have pixel level alignment. So there are we can have a look briefly have a look at the iPhone 11 and then their configuration. The main difference is they will have a different focal length that will result in different optical zoom level. Okay, one of the challenge is the geometric alignment. Even we align the two image very well by homography, they cannot fit perfectly at the pixel level. This is an overlaid image. And if we try some like a flow-based registration approach, then the resulting result is always poor. What we found is it actually loses the original high quality texture in the warped image. And the color distribution are different. You can see we generate the image intensity histogram. They are not the same for some region. So there are a lot of challenge when we want to utilize. You may see, okay, there would be, such a overlaid image and in the middle. Okay, yeah. So we can have some maybe some result. So here is our result compared to some baseline. Some reference-based baseline. Yeah. So for example, we can see the license plate much better in the grass, much clearer. So our framework is as an overview, it would look like this. Then I will share the key idea with you. So there are some major key idea in our approach. So at a high level, what we want is, okay, we have this telephoto image where we want to use it to enhance this wide angle, which we call low resolution image. And then we need to do some patch-wise registration first, where we have to know where the corresponding patch in the other image and the similarity based on some cosine similarity matrix. And then we would do it with in a multi-scale stage where we would have the aligned attention and then the adaptive fusion. We will talk about these two parts in more detail. And the basic idea is we keep use the aligned attention to warp the feature from the reference image and then put it into this adaptive fusion module to combine with the low-res information and keep enhancing the result. And so where in the aligned attention, we will look at some challenge we have here. And we also look at, in self-attention or cross-attention for images, it doesn't consider it mainly can solve the translation. But what happens when we have rotation and reflection and scaling, invariance? So maybe we can have a better attention mechanism that can better utilize the patterns that may be rotated, maybe reflected, so that we can better utilize the reference images information. So this is our aligned attention. Okay, so so the F reference is some feature about the reference image. This is the reference image. This is just a bilinear upsampled low resolution image. And what we do is we just because we have the corresponding point, then we can keep to the warping to warp it to be aligned with the the low res image. And then we will have the transformation network that can have the local alignment in terms of the rotation, scaling, and so that we can, in the end, generate some aligned feature with the low-res image. And then when we have this aligned feature, then we can do some fusion. Yeah, so we also take the confidence map into account, how similar the two patch would be, and have adaptive fusion, where the network try to learn the most residual for the feature. And for the final composition, we also follow the similar idea, where we will learn the residual from the the high frequency residual map, and then combine them together. You may refer to our paper to see the exact formulation. So now the whole idea here is how we can keep using the aligned attention to borrow the information from the reference image. And we also utilize the fact that actually this reference image is already very well aligned with the reference image. So we can utilize this to do better registration. And in the end, there is one more challenge I think we face when it's a unique challenge we face when we do the 8K image super resolution, because we don't have the 8K image ground truth because the camera doesn't provide that. And we propose some self-supervised objective so that we can obtain the high quality result. If we don't do that, if we just train the model from 2K to 4K, it doesn't work that well for 4K to 8K super resolution. There was some domain gap. Yeah, so we proposed to fine tune our model for 4K to 8K super resolution without the ground truth. Okay, so and another contribution is we collect a data set where we have the paired telephoto and wide angle images. Yeah, so this could be the input and this the reference image. Here is another example where we can use it to do the 4K to 8K super resolution. And on the other hand, we also evaluate our method on some public QV5 dataset. And on this dataset, it is a reference-based super resolution dataset. And our approach achieve a state-of-the-art performance. Yeah. There is some comparison with different reference-based super resolution methods. And here is our result. Here is our result. You can see the comparison and the baseline. Here is another example where we can see the texture clearly. Similar on this case. We don't, it's very blurry here, and we can still see the detail. And we evaluate also our proposed data set. They are captured in the natural environment. And here is some result for 4K to 8K super resolution. So you can see we can make the image quality even better than the, I think this is captured by an iPhone 11. So we can do it better by combining the result from the two. Here is another example. You can see that the texture would be sharper. So, okay. And if we zoom in for the detail, and especially when we compare with some baseline, we can see the texture, the these Chinese characters much more clearer. Here is another example. Yeah, and if we zoom in for more, so we can see the texture much better. So that could be beneficial when we want to see something very far, and we need to have a very high quality, high resolution result. Yeah, and this is, I guess, for this, it's probably here. Yeah, and we can still get some texture like this, which is very difficult to get, I think, by other methods. Yeah, because the light from the input it's basically blurry, but we can still recover the texture here, although it's not perfect. And we can see in this example, we can see the text here much more, clean. Also for this texture. And this is another example, I think. For this one, it's probably here. And this is some regions out of the telephoto range, and our reconstructed the result is also better. You can see the texture like here. And to evaluate our approach, we look at our aligned attention, where the aligned attention can do rotation and scaling. And if we don't do this alignment, then the resulting image would be, I think it would be more blurry. Yeah, and then the adaptive fusion. Yeah, so combining the feature and residual combination, the result would be sharper. So there also quite some, small designs, although they are small design, but they would affect the result quite a lot. Mm-hmm. And lastly, with this fine tuning for 4K to 8K, I think we have seen this before. So as a conclusion, so we have done something, we studied some problem beyond a single RGB camera. First, we have looked at how we can use the polarized images to do the scene level shape estimation, where the prior work focus on the object level. And we propose a new data set and also a new method for the telephoto and wide angle combination for most of the smartphone we have today for extremely high quality image reconstruction. And you can find the source code and data set on our website. So for the future work, I feel there should be also, we are still missing a lot of polarization data for many other tasks, although we have polarization data set for shape estimation and reflection. And then for the dual view images, videos on our smartphone, maybe we can also explore many other tasks. So that's all for our talk, and I think we may have some time for questions.
Yeah, thank you very much, Professor Chen, and I like this great talk. I wonder if any questions from the audience, either from audience here or any in the audience. Yeah.
Can I speak like this?
Yeah, you can just speak out.
All right. I have a question about the very early slides where you talked about invertible mappings, right, for image restoration. That you talked about, yeah, exactly this one. The question is, how do you think about processes, image processing that are non-invertible? What does it mean to be invertible in the context of non-invertible operation?
Well, so let me rephrase your question first. So is your question about how we can, I think the task is non-invertible, and how the model can make it invertible. Is this your question?
No, more like when we speak about invertibility, do you mean like, is there any kind of mathematical notion you introduce for invertibility in case?
I see. Yes. So in our, normally in our model, we would use a invertible neural network. And invertible neural network can make sure the input and output are invertible. Yeah, so this is guaranteed by the invertible neural network. There are some flow-based, normalizing flow-based methods. And but for some tasks, it's impossible to be invertible task. So the invertible network would be a submodule for the model. Try to maximize the invertible part and have a small part that's non-invertible. Yeah. So that's the general idea how we can, for example, for image compression, we outperform the learning-based and traditional methods by designing an invertible neural network, almost invertible, but some part is not invertible. Yeah, it's a hybrid. Yeah.
Thank you.
Thank you.
Thanks for the question. I think we are about time to start next talk. So let's thank Professor Chen again.
Thank you.
Muted. All right, I think it's all set up. All right, welcome everyone. I'm a second speaker at the talk, and thank you. How you want to introduce?
Yeah,
All right.
sorry.
Sorry about that. I need to first briefly introduce Professor Lubeck Kamilov. Just 1 second. So Professor Lubeck Kamilov is an assistant professor and the director of Computational Imaging Group at Washington University in St. Louis, and his main research area is computational imaging with an emphasis on the efficient acquisitions, reconstruction, processing, and analysis of the spatial and temporal data. And Professor Kamilov obtained his PhD in electrical engineering from EPFL in Switzerland, and he's also a recipient of the NSF Career Award and IEEE Signal Processing Societies in 2017 Best Paper Award. Thank you very much.
Thank you very much for the introduction, and thank you very much for invitation. It's a big pleasure to be speaking here. And today I wanted to talk about, maybe I'll stay closer to the microphone, about a more recent line of work in my group around the topics of neural fields. And neural fields have taken computer vision and graphics with its elegant formulation. And I will want to talk about that area, but in the context of inverse problems in computational imaging. Before I get started with actual technical part of the talk, let me say that my thanks to the members of my group, of CIG group, Computational Imaging Group at WashU. In particular, a lot of the effort I'm presenting has been led by Dr. Yu Sun, who just graduated from my group and is going to continue to do his postdoc at Caltech. And he collaborated with several other members of the group, including Wen Dao, who's going to start his PhD at Boston University soon, and Ren Hao, who's still working in the group, but also working right now at Google. And with this, let me get started with the talk today. So the line of work I'm going to talk to you today is based on this elegant formulation centered around the view synthesis based on NeRF. So many of you, I guess, are familiar with the concept of NeRF, or neural radiance fields. And it's a very elegant formulation, which kind of swaps the way we think about neural networks, in particular in imaging, about convolutional neural networks. So in NERF, the way the algorithm works is that you design a coordinate-based neural network that takes in coordinates and array. Okay, so you have array and a coordinate x, y, z, and by combining these inputs, you try to predict an output which will be some value on your sensor. Okay, by training this coordinate-based neural network on available data, meaning you have several views of a 3D scene, the hope is you learn an interpolator or a really advanced interpolator that can now synthesize the views you didn't have. Okay, and this is a very elegant formulation for many ways. In particular, one of the most elegant aspects, and we're going to talk about in a second, is the fact that your representation become independent of the grid. Okay, so it's a gridless representation. And it is also a continuous representation, meaning I can synthesize any new locations at X, Y, Z, and the new angles. And this concept, when I read about it, I really appreciated it. So I started thinking about it and bringing it back to the context of inverse problem. And this is what I want to talk to you about. So let me remove this little thing here. All right. So if you're, I'm guessing most of you are familiar with inverse problems, but for those who are not, let me quickly introduce you the idea. So in inverse problems, we're interested in a quantity. So usually in my case, this will be an image that unfortunately I cannot have directly, but what I can have is a measurement of the image. So what we call forward problem is a mapping that goes from unknown image S, goes through the imaging system. So we saw previous talk, it was mostly camera systems, but this could also be microscopy systems. It could be medical imaging systems and so on. And what we finally observe is a noisy version of this unknown quantity. And what I'm interested in is the inverse problem. Okay, so inverse problem is an ill-posed problem where I now try to recover the true image S given the measurements Y. Okay, now, and my group is particularly interested with inverse problems for one single reason, because it gives us a very nice unified approach to address many different problems. Okay, so we can look at problems in super resolution, the blurring, but I can also look at the problems in sparse UCT, MRI, and optical microscopy, and all of them can be addressed in a very unified mathematical way, which is something I'm after. Let me give you a couple of examples of topics we're going to discuss today. The first one will be computed tomography. So in computed tomography, the inverse problem is that you collect a bunch of projections of an object. What we call sinogram is on the right-hand side. So in this data here, in the sinogram, theta here is an angle of projection, and a t here is a sensor location. So for each angle, you collect a projection of the object by integrating along this line. And usually, if it's a parallel beam CT, you can use a radon transform to compute an inverse mapping, or usually filter radon transform to compute an inverse problem mapping between the an image and the measurements. And then, of course, in the computerized tomography, if you can collect full angle coverage, meaning you cover all the 360 degrees, then you can easily use radon transform or filter back projection to recover the image. But once you start missing angles, you start having to deal with artifacts. But however, we really wanted to reduce X-ray radiation doses. So usually we go after to trying to reduce or try to do the sparse view CT. So the second example I'll give you is intensity diffraction tomography, which is very related, but it's in a microscopy domain. In intensity diffraction tomography, we have a very simple microscopy setup. So this is set up by my colleague, Lei Tian at Boston University, where we have a light cert, which is usually LED array. We have a sample, 3D sample we want to recover, and we have a very simple optical system that finally has a camera here. So the idea in intensity diffraction tomography is to eliminate one of the illuminations, so one of the LEDs, right? It goes through a sample, the light scatters, and we measure it at the camera, and we see something like this. It's an intensity image at the camera. If I illuminate another location here, then I'm going to see another image which acts like a tomography. So by collecting hundreds of those images, unfortunately, you still have a missing angle because you cannot do a 360 coverage. We can try to recover the 3D refractive index distribution. So what you see on the right-hand side is for each location here, I computed the refractive index of the object, which is a complex valued quantity. And it tells me something about the shape of what I'm looking at, but also tells us about the material of the things we're looking at. And that's intensity diffraction tomography. All right, the three challenges we would like to address are the fact that because of the accelerated acquisition, we would like to accelerate acquisition because since in many application acquisition is sequential and indirect, think of tomography, the acquisition could be slow, so we would like to accelerate it. The second challenge we want to deal with reconstruction images containing artifacts because of undersampling, motion, model mismatch, and noise. There are many sources of it. And finally, high memory requirements. Once you start moving to 3D images, XYZ, 4D, XYZ time, or 5D, XYZ time and spectrum, and so on. I will have to deal with the memory requirements. All right, so the way I want to talk to you about is to connect my talk back to the traditional way we discretize inverse problems. Okay, this is something many of us don't think about regularly because people have set it up, and very often when we deal with inverse problem nowadays, we actually look at discrete inverse problems. However, the way you can think of it formally is that usually the desired object that we're after is actually a continuous domain quantity. Right? It's a continuous domain quantity of spatial coordinate and usually a temporal coordinate, right? That's what we would like to recover. Now, the forward model or the measurement operator is usually a mapping between a continuous domain object, which lives in L2 RT. So L2 here means it's a bounded energy, bounded L2 norm object, and the sensor measurements that are vectors, right? That's a mapping that we get. And then if you have a linear inverse problem, you can often represent it as an integral operator. So you can have an integral operator where this little at the I here is the impulse response of the ICE sensor. If you know the impulse response of the ICE sensor, by integrating your object over RD, you can actually get your specific measurement at the sensor location. All right. So now the question, if I understand my forward model, my mapping, I know that my object is continuous. So how do we represent the continuous domain objects, right? And this is something that has been studied over and over in the past in the context of wavelet transforms, in splines, or any other basis functions for discretization. Usually we say, you know what the way I'm going to distribute, I have some region of interest, ROI, that's denoted by this omega. Inside this ROI, I'm going to define a basis functions for each location inside the ROI. And by multiplying this basis function by some number and summing this over, I'm going to synthesize my image. So this is a linear expansion of a continuous domain image. And if you plug this back into this integral equation, you can easily obtain this inverse problem where now each coordinate of the matrix A will be inner product between the basis function, the impulse response, and the basis function. So this, for example, could be a wavelet. This could be like Fourier operator or a projection operator and so on. And by doing this, now you can formulate a discretized inverse problem. Okay. Now in today's talk or in this topic, what I've been exploring is trying to move away from this linear representation, but trying to consider neural fields-based representation, where we're going to have a data-driven representation of the continuous domain object and try to use it to solve the inverse problem. Okay, so the setting I think is pretty clear, and I'm going to talk to you about three techniques. They're all a little bit different, but try to go along this line of trying to represent continuous quantities for reconstructions. All right, so let's start with the first technique, which is coordinate-based internal learning, or COIL, which is a pretty recent work. So the idea of COIL, and especially it was proposed for computerized tomography, was to deal with image reconstruction ECT where we have a projection. So let's say we have an object that we would like to reconstruct. We have a bunch of projections at different angles. So what you see here is a sinogram of this, but represented as a 2D function, right? So I kind of, for each sensor location, I put the response as a function. Now, once I know the sinogram, usually we do the image reconstruction by using any techniques that you like. It could be filter back projection, optimization based reconstruction, or deep learning based reconstruction. Now, the idea of COIL is to do something pretty simple to understand conceptually, which is to do the interpolation, okay? Sinogram interpolation. So how do we do it? Let's say we have a subsampled sinogram measurement. So I have a V, which is a coordinate, the sensor location, and I have a sensor response, R. So for each sensor location, I have a response. And once I have a sinogram, a sparse sinogram, I have a set of those. Okay, think of it traditional nerve where you have a set of views of it. Oh, and I'm trying to generate the missing angles for this, right? So the goal is to have MLP based or a coordinate based neural network that would learn the mapping for the specific sample. There is no training data set between a coordinate and the response. So I'm going to train it on a variable sparse sinogram. Once this is trained, we can try to synthesize missing angles. Okay, so it is essentially a sinogram interpolation technique. Right? So once we do it, now I can actually put this interpolated sinogram to any image reconstruction method that I like. So it could be optimization again, or neural network-based methods. They can all be used by now combining my true measurements that were collected and my synthesized measurements together to perform the image reconstruction. And that's a kind of idea of the COIL approach. So this is a basic high-level concept. And the way it is done is essentially building on the work on nerves. So the neural networks that can do this consist of two key elements. Just like most of the nerve-based neural networks, it has a first part to it, which is a Fourier feature mapping, and I'm going to talk about in a second, followed by a simple, fully connected neural network with some number of layers, some skip connections, and so on. And an idea is, as an input, it takes in a coordinate. As an output, it will give us a sinogram response or location on that sinogram that either I have or I'm missing. Okay, so Fourier feature mapping is something that has been introduced in the original nerve paper, but essentially you can think of it as a Fourier series expansion layer. Okay, so Fourier feature mapper takes in the V vectors, which are the input coordinates, and passes them through sinusoid at a predefined frequency locations. Okay, so I take a predefined frequency locations. So I take a location, I put it in. By the way, the sines and cosines are evaluated coordinate-wise, meaning if I have a three-dimensional vector as an input or two-dimensional, I'm going to have two outputs of that side. Okay, and by just concatenating all of this, you're going to end up with a Fourier feature mapping vector. And essentially, what the first layer does, it learns the weights of those Fourier spectra. Fourier decomposition. Now, in the original nerve paper, if you look at it, the sampling was a little bit different. They proposed kind of logarithmic spacing in the sampling. However, we saw that the linear was working better in our case. If you look into the paper or your eyesight is very good, you could see that the COIL's linear sampling does significantly better than exponential or random Fourier feature mapping. All right. So at this moment, let me just quickly say that we did compare COIL against several baselines, and here I show you in the sinogram space some results. So let me explain you this table. So P here is a number of views, number of projections we have of an object. This is all simulated data on X-ray. 60 views, 90 views, 120, more is better, right? You have easier problem to solve if you have more projections. 30, 40, 50 here means amount of noise. They're measured as an input SNR. So higher again means there is less noise. So if you have 50 input SNR is less noise than 30. And then here we're looking at the sinogram space. You can try to do linear interpolation by cubic interpolation, which is essentially using this basis function based linear expansion of the sinograms versus the COIL approach. But also here we put a convolutional neural network that has been trained on a set of sinograms to learn to interpolate it. Now, let me kind of give you a flavor of the result. First thing to observe is, of course, if you do a training, you learn a convolutional neural network, it usually does better than actually using just neural fields to try to learn into the sinogram. Okay. Now, the reason and you can see also the gap goes down between the two when there is less noise. On a more noisier sinogram, the gap is bigger. If you have a less noise, the gap is smaller. Now, the reason, of course, if you train an interpolator on a sinogram, it also acts as kind of a denoiser. It learns to be a denoiser versus COIL that doesn't do, because ConvNet here has been trained on a supervised way, and COIL here is not training based. It's just a test time training method. Now, on the other hand, now if you look at traditional interpolation methods, COIL does significantly better by getting multi-dB improvement over those methods. Now, the reason is because COIL is in fact a data-driven interpolator that adapts to local features in the sinograms, and this is what allows it to perform better. So in some sense, if you can see, it's not as good as training a supervised convolutional neural network, but it's significantly better than using traditional interpolator. And of course, the key advantage of COIL is you don't need any training data you just get it on a test time training basis. Of course, you can now use it combined with different type of reconstruction methods. So here I filter back projection, Vista TV. Sorry, the screen is small. If you want, you can look into the paper, but I'll give you a summary of the results. So basically, there are 4 different flavors of reconstruction algorithms: regularization by denoising, UNet, Vista TV, filter back projection, and without coil and with coil, meaning we use synthesized data, or we don't use synthesized data in the reconstruction. Across the board, of course, coil improves the performance, and more improvement happens when you have a simpler method, of course. So if you take FBP, filter back projection, you get a huge improvement, right? Now you have a sophisticated reconstruction methods like regularization by denoising, improvements become smaller and smaller because there are strong priors that act on those. I'll show you some visual results. You don't need to try to see all the numbers. You can look them up in the paper. So let me show you a few results. So this is on the left-hand side, everything will be without the coil approach, on the right-hand side with coil approach. So here's a zoomed in region. So without coil, this is filter back projection with 120 views and 40 dB noise. So just if you do filter back projection, you would see something like that. And if you use neural fields to do the sinogram interpolation, it usually improves the results. So here's another region of the same image zoomed in with and without coil. Now, if I use total variation regularization on this, you can see both of them suffer from, the screen doesn't show pretty well, and the contrast is not good on the screen, but anyways, both of them have the same type of total variation artifacts, which are piecewise constant artifacts, but coil significantly improves the results by 1.5 dB or so. If you do red regularization by denoising, you observe a similar behavior, like 0.5 dB improved by using neural field synthesized angles and so on. And this is for filter back projection followed by UNet. You can again see a boost in quality by 0.7 dB improvement in the features of with coil and without coil. All right, so to summarize, my first part is that you can use neural fields to simply adopt what original NERF did, trying to generate new views in CT. And this is something I exploit. The key difference, by the way, between coil and original NERF formulation is in original NERF, you take into account also the forward model. You try to take into account the exact ray. Now, in a coil formulation, we don't do it. We actually train on just available sinograms by learning an interpolator. So that's something to keep in mind. All right, the second talk, I want to talk to you about 3D refractive index reconstruction in optical tomography. Now here we're going to shift the gear and we're going to try to continuously represent unknown refractive index map. Okay, so what do I mean is that I'm going to try to use a neural network that will be coordinate to response mapping that will represent to me a refractive index of a 3D object at every location. So for every x, y, z, I'm trying to get a real and imaginary number. It's a complex valued output. That complex valued output will be refractive index. Okay, so how do we do it? Well, we use a neural network to be able to synthesize the object. Once I synthesize object or parts of it, I can put it through my forward model, which simulates light scattering, or the physics of the light scattering, and brings me finally the simulated measurements in the sensor domain. Okay, so there is a mapping between the output of the neural network and the measurements in the sensor domain, just like in original NERF formulation, except the forward model here is wave-based. It's a diffraction-based forward model. And then the goal is by comparing the actual measurements with predicted measurements, we want to do error back propagation to update the weights of this operation, of this neural network, to try to synthesize high quality images. Now, of course, one of the key advantages of this is that once we generate 3D refractive index, I can easily generate it by feeding in any coordinates I care about. Okay, so I can synthesize it on any grid I want. It doesn't have to be the grid I do during my simulations or during my training process. So in fact, once I learn the weights of this neural network, because its representation is independent of the voxel grid, I can synthesize it on any density that I would like to have. So here you can see different densities that we do. Now, to train the weights here, we did something quite interesting. We have a loss function. So as a reminder, I'm trying to get the weights here, which is a representation of my refractive index. we have a loss function that consists of two terms. Right? There's a first term, which is a data fidelity term, and the second term, which will be an regularization term. And then if you really want to see the details of this implementation, feel free to go to the code online or look at the paper. But essentially, the data fidelity term takes into account the light scattering and tries to map it to the measurements. But we also have a prior term, which tries to pass the refractive index through a neural network, which has been trained to denoise images, to push it close to the fixed points of this neural network. Right? So the fixed point of a denoising neural network is an image that is noise-free according to that neural network. So we try to minimize the distance there. So if you look at the paper, this is what we're trying to minimize. Now, what's interesting here is that this has been pre-trained on a natural images, but at the test time, we update those weights. So nerve formulation or neural fields formulation gives us ability to adjust the priors at the test time by doing test time training. So there is kind of a nice, elegant connection there to test time training strategy here. All right, so let me show you a few examples of what this method would look like. So here there are comparisons with a couple of methods. So this is a simulated, again, the contrast is not so good here, but this is a simulated phantom data with a high quality light scattering simulator where we simulate high fidelity wave propagation. So this is at a single Z slice here. So there's a ground truth cell phantom, which is a 3D cell phantom. And then you can use a Tikhonov. This is a DNCNN based reconstruction that's from prior work. And finally, the decaf approach. Eventually, if I summarize this thing, besides better overall imaging quality, the decaf approach, interesting enough, does a much better optical sectioning. Because we have a missing cone artifact, we have missing angles, the resolution along Z is usually worse. You can see those cells are elongated, and this is an artifact. But once you use the neural fields, usually it improves the performance. And one of the reasons I can talk to people who are interested in this is a test time training capability. Of course, we also validated on experimental data. So here's a 3D sample, which is diatom algae. You can see we're going through the sample slice by slice basis. As we go through, you can see some parts of the features. You can see the artifacts that we see here are because there's a leakage in the optical axis between different slices because of the optical axis is not good. So let me just show you again. Some objects appear and go out of the slice as we move across the slice in this image. So this is a view, lateral view of that slice. Here's just upsampling it because we can synthesize the object at demand at any grid we want at any moment. Here we just synthesize it on a much denser grid, and we just show the results compared to bilinear interpolation compared to just pathing through the MLP. Here's another example for different samples. This is human buccal epithelial cells. Again, you can see the amount of artifacts is significantly reduced. And here we show you different existing or non-existing seeds. So it's when we train the weights of this neural network, it has been trained on only using certain depths, but you can try to synthesize anything that's in between because you have continuous representation of the sample in X, Y, and Z. And finally, this is a C. elegans sample. You can see it's much clearer compared to the other prior work. All right, so I have about 15 minutes left, but I want to spend like a few minutes on the final part, which is cross-video neural representation, which is a cure, which is again a similar ideas, but applies to a different problem, which is trying to continuously represent the videos. Okay, so what's the idea here? We have a video file, which means a sequence of frames. Of course, there's a certain frame rate, so we're missing certain frames. So the goal is we're trying to add missing frames between two consecutive frames. So this is a classical problem in computer vision, and then different approaches have been proposed. And a particular approach I'm going to talk about is trying to continuously represent the video, just like we did in the previous parts, to be able to synthesize the missing frames. But here, our architecture will be slightly different. We're going to adopt a conditional neural fields approach, where besides the coordinates x, y, z, t, we're going to also give a feature vector, which will be the features of two input frames that are extracted by neural networks that we call a spatiotemporal encoding module, which will extract some features, and we're going to pass that neighborhood as an input to the MLP that will finally predict RGB value at that specific location. Okay, and that's an idea here. So if you go into the details of the architecture, this STEM or STEM module here essentially takes two frames, uses the optical flow to predict optical flow between those two frames, and try to predict warped full feature maps by using two optical flows and going backward and forward. So there are two flows. So we take one of them forward and then backward. So we end up with a 4 feature maps. And we're going to, after taking those feature maps, we're going to take that neighborhood from that and put it as an input by concatenating it with the coordinates to pass it through the MLP. Okay, and finally, the MLP will be what will give us the desired RGB value. Okay, now the way this is used is that you can, so the reason we call it cross video representation is because you can now train this end to end. Once it's trained, given any individual video, you can do test time training by just updating the weights of MLP. Okay, so that's how it's used in this implementation. So we tested across many different methods, and it does give us pretty good results across several data sets and several prior works appearing in the recent times. And overall, it gives us a state-of-the-art results relative to PSNR and also SSIM values. This is all in the paper. Let me just give you a couple of examples. So this is a low frame rate video. You can see the thing. Now, if you pass this through MLP, you can see pretty realistic. You can see some artifacts if you look carefully, but it's pretty realistic and smooth interpolated video compared to the input. And by the way, all those frames have been synthesized completely by that MLP at the desired frame rate. And then you can compare the two. Let me show you another example. There are many more examples on the website. You can see lots of video examples of different interpolated videos. So here, another sample. If you look carefully, you can see a bunch of artifacts. The motion of the car might look a little bit unnatural to you if you look carefully at it, but this is what's basically synthesized it, but it looks pretty impressive. It's 10 times interpolated, temporal frame interpolated video using the MLP. So it's completely synthesized. All right, I think to just leave some time for potential questions and give the next speaker enough time to settle up, let me conclude my talk. So NERF and many follow-up works around the idea of neural fields give us a very elegant and simple formulation to try to learn non-trivial mappings between coordinates and some form of responses. And in that mapping, you can embed or not embed the forward models or some prior information. It's a very flexible representation. So I give you 3 types of applications of that idea with slightly different flavors. But let me highlight 3 things that I think are potential benefits of adopting this representation. The first benefit is the test time training, and I alluded to this several times. What does test time training mean? In the NERF-based methods, just like if anybody is familiar with deep image prior, you don't need to usually pre-learn. There's an implicit ability to adapt to the training testing data by updating the weights on a testing data. So that's what I mean by test time training. The second is gridless representation, which means once you get your representation, you can on demand synthesize only parts of the image that you want. So if you have 3D, 4D, or 5D data, that can lead to efficient memory management because your representation is independent of the grid. It's based on the weights of MLP. So it all will be depending on the way you represent your scene and so on. And finally, there's an implicit regularization ability, just like in deep image prior, where MLP itself is shared across coordinates. So it can act as an implicit regularizer on your imaging data. And that's a third advantage. So with this, I'll thank everybody for attending my talk. And I thank my group members for helping to prepare this talk. And I'm open for questions.
Thank you, Professor Kamlov.
Yeah, so it's more in general regarding this video interpolation. So there's kind of the strange effect that if you look at the frames individually, they look correct, right? But when you look at the motion of all the video sequences, it seems kind of weird,
yeah,
way too smooth, right? Can you comment a little bit on that? What's the cause of that, and maybe how you can solve that?
So So it's a very good question, and you can, if you look at it, you can clearly see during the dynamics. I think one of the reasons is the way we take into account dynamics is pretty naive. We just use optical flow between two frames, but then we take an ambitious goal of interpolating 9 other frames in between. I think a smarter way would probably be have some form of models that takes into account a more temporal dynamics better, right? Instead of just doing a simple optical flow between the two. This was the first work, so we didn't do it, but I guess you can do a much better job than what I've done. So your comment is spot on. I think just the way we embed this, although, here's another thing. It's very important to use optical flow because if you just use neural fields, it's not enough. So if you look at the paper, you can clearly see it's not enough. So you need some information about the dynamics there. But the way we did it is, I think, naive and could be improved. Yeah. So if you have a good idea, I'll be happy to know. But yeah. Thank you.
Thank you for the presentation. Really interesting. I wanted to circle back a little bit on the test training time.
Yeah. Yeah. So there is a series of papers by different authors. So I think that one of the deep problems when we deal with imaging inverse problems and we use neural networks is the distribution shifts. So you have a training data, you have a testing data. There's a distribution shift usually between training data and the testing data, right? And then depending on the problem, it can be pretty severe. So in some applications, people train on simulated data and then on experimental data. So there is a naturally distribution shift happening there, right? The test time training is one of the remedies proposed by several people in the field. And I can give a pointer to maybe Reinhard Heckel at TU Munich. He has done some work on this and so on. And the idea was, if you do add, you pre-train your network on some data, now you want to apply it to a new data under distribution shift, okay? If you update neural network weights on a testing sample, so that one sample itself, a little bit, you actually improve your generalization ability to shift the data. Now, neural fields gives you one mechanism to do this very easily, right? So you can still have a prior, as I discussed, so you can pre-train, you have a prior information that's there. But when you have a new testing sample, you can just update the weights of MLP that will allow you to adjust better to the test time training data. And I think this is a reason we have improvements in several applications in terms of final reconstruction quality. And I think the improvement is because of that ability to capture the better test time training data. I hope that answers your question. Okay. Yeah, so the coil method here doesn't use any training data, but of course you're right that if you do have a few samples of data, you can design a smarter way like we did with for others. You will do better by embedding some information that you have. And again, leveraging test time training to refine it to your test sample distribution. You will usually do better by doing this. Yeah, in the coil, we didn't use it, but you're definitely right. Yeah. Yeah, let me repeat the question. The question, and I think it's a spot-on question for generally neural fields projects, right? So the test time training, okay, you get something, but you lose in computational complexity because now you don't pass the data through CNN, but you need to do a training on a test sample. It's definitely true. And you do see that the complexity goes up. So there is nothing that, but I guess the question will become, how much are you willing to tolerate for how much improvement? So that becomes more like an application related question. In some of the applications like decaf I presented here, takes us almost 24 hours to train on a 3D sample. So that's very expensive, right? It's not a practical thing. But I guess with improvements in our ability to train, maybe you can cut it down. There's certain progress happening around instant nerve and so on. You could probably adopt this to try to cut. But fundamentally, it will end up being, there will be a cost to it. Okay, whatever that cost will be, eventually there will be a cost. Now, the question is whether that benefit will be worth to you in your application. For some applications, it will be definitely worth it if you can, for example, do better in reducing artifacts that are critical for your application. So, which we see, for example, in decaf, that it does it. So. Thank you very much for the invitation.
You already shared your screen. Share screen, yeah. Screen keynote. It's working? Yeah, I think it works. Hi everyone. Thanks for keeping staying here, and I'm very happy to have Professor Achuta Kadambi to here give us a talk. And Professor Kadambi received his PhD degree from MIT and then joined UCLA as an assistant professor. And his publication has been presented as a ORS at CVP, ICCV, and ICCP and SIGGRAPH. And his currently also a co-author at the textbook called Computational Imaging, and is also a co-founder in robotics imaging startup called Akasha. And Professor Achuda Kalvi's research is recognized by the NSF Career Award and Forbes 30 Under 30 and Google Faculty Award and Sony Imaging Young Faculty Award and also Army Young Investigator Award. Thank you very much, Professor.
Thanks very much for having me. Thank you to the organizers. So let me start with, now this talk is being recorded, so it has to be a little less controversial. The title of the talk is ground truth possible for image-based derating and deweathering? So by the end of this talk, those of you who work in the area, we can assess this question. And if you work out of the area, you can kind of appreciate a hard problem where ground truth is a little tricky to pin down, and that affects how the methods have been developed. So before I start, I just want to give credit to the team that makes this possible. You know, the work that I'm going to be presenting is all thanks to the students I get to work with at UCLA, and also to our funding agencies, and in particular for this research, we're supported by the ARL. The student and postdoc authors on the technical report that I'm going to discuss are all attending CVPR in New Orleans. Actually, they're all in this room. So Howard is a first year at UCLA doing his PhD in ECE. Yunhao is also doing his PhD in ECE, except he's going to defend and graduate in the fall. And then finally, Alex is a collaborator on this project with us. He's been closely involved. He's also a UCLA affiliate. He's a UCLA postdoc with Stefano Soato, and he is going to join Yale Computer Science Department later this fall as an assistant prof. Okay, let's begin with a little bit of the motivation here. Let me play this video. Let's see if the sound will play. We're going to try to just download a rainy image from the web. Okay, so we click and we look at this image, and maybe we want to download this. Okay. All right, so we've downloaded a rainy image from the web. And the problem that we're going to tackle and discuss is how we take this as the input and then remove the rain from this image. Okay, so we want to get the image looking almost exactly like this scene, as if the rain was removed. Okay, so we have an image. It's been downloaded from the internet. And actually, this field of deraining, how many people here have worked in deraining? Anyone? A few people, yeah, excellent. So if you've worked in deraining, there's a lot of excellent work every year that you can look at, multiple papers at CVPR each year. And so here's a really good one. This is MPRNet that we're going to apply to this image. Okay, so we do a pass through that, and this is the output of MPRNet. All right, so that's kind of what you get if you download an image from the web. Okay, so you know, this is actually a really good paper. And if you look, you can actually compare it to a lot of other papers. So here's MPRNet, and here's MSPFN, which is another very nice paper. And if you look, both papers are doing something roughly similar. They're removing rain to a very small degree. You can kind of see at the very end of the image, when it transitions over from the wipe, you can see that some of the rain has been removed. Here's RCDNet, another paper. Same thing. So we actually did not work in deraining at UCLA for a while. And we just started downloading images from the web, running them through, and realized that this is a fun problem because it's very hard to actually remove the rain from these images. So we came up with a new method. We'll call this ours. And this is how it works. So if you look, the rain has, you know, arguably been removed better. Okay. So I put a question mark there as kind of what's going on here, right? Because if you think about it, it's not like we're going to come up with a model that is so much better than previous work to give you a result like this. Okay. So what did we do? Any guesses? Supervised training. Unsupervised training. Not quite, actually just the opposite. We actually did supervised training. A lot of the methods, I'll start giving some opinions here. A lot of this unsupervised, self-supervised, all this kind of stuff, sometimes there are challenges with actually getting it to work in practice. So what we actually did was we went back to this tweet. This is a tweet from Andrew Ng. It's a really nice tweet. 2021, I guess in the pandemic, this is how you're communicating with scientists. Okay. All right, so this is how the Andrew Ng tweet is saying basically that, okay, let's come up with a new type of thinking where we hold the models fixed and we vary the data and see what starts to happen. So we start to look at the data for this problem, and this is how data is generated for deraining. They take images that are clean and then they overlay like streaks onto these images, and these are kind of the rainy images that are on there. And there are a ton of excellent papers on synthetic data sets out there. Rain 12, Rain 100, Rain 100, Rain 14,000, Rain 12,000, and so on, right? All of these in CVPR. And of course, there's a lot of papers in ICCV as well that I have not listed down in ECCV as well, right? So real data sets, there are none. The supervised training is not exactly happening with real data. Does anyone know why? There's no ground truth, right? Unless somebody invents a parallel universe, there's no way that we can have the same scene in the same exact time and the same exact lighting. And so the previous work has all done synthetic data because of that very logical observation, right? Okay, and if you look at this, synthetic data itself is tricky to get right. Rain, this is where, our home, my own lab's home is in physics-based vision. And we look at the physics of light transport, how it behaves, and the subtleties of that. And it's really hard to get the physics of light transport just correct to simulate rain. Okay. So there's a haze. I can talk to you about the humidity. I can talk to you about the size of raindrops. I can talk to you about something called the veiling effect, where if the rain is less than the pixel pitch of your camera, it starts to create a defocus blur and actually becomes more similar to fog, so on and so forth, right? So the complexity of rain is not so simple where we can overlay lines onto the images. If we do that, we're not going to be able to have good DL performance. Okay, so synthetic rain is tricky to get right. So any guesses on what we did? Yeah, wouldn't work if it's a deep scene. If we watered it with a hose, then we would be very specific to that type of hose and that type of rain. Would that match the rain in Florida, let's say, which is, well, so I'm from California, which is very, very dry, right? So Florida is very humid. The raindrops are quite different in Florida. So that's not quite what we did, but we did think about that. We did try that when we started this project, and it didn't work. We were downloading internet images, and we were performing worse than the synthetic simulators in that case. We also thought about that. Living in Los Angeles, we thought about that. A lot of our colleagues recommended it to us. I think Alex and I had a chat about that. But same thing, it's just like the hose. It outputs a very specific type. Okay, that's great. That's a good way of thinking. There's a problem with that though. I see some people shaking their head. So, huh? Sorry? Okay, so the gentleman in the front, the light in the scene will be different if you use a video webcam. Okay, so let's take a look. People use synthetic rain because we cannot collect rain at the exact same time. And this is a very nice paper in TPAMI. First author is Yang. One of the other authors is a colleague, Ravi Tan, who works a lot, who's worked for many, many years on deraining. And I've highlighted one aspect there. There's an underline. However, to obtain real rain images and their exact pairs of clean background images is intractable. Let me zoom that up again, okay? However, to obtain real images and their exact pairs is intractable because even for a static background, lighting will change, all right? So, all right, we read this, we were kind of stuck with our project. So we did the dumbest thing possible. We said, let's give it a try and see what happens. Let's do the naive approach and give it a try and see what happens. And in particular, what we can do is webcams are all around the world. The diversity of rain is there. And if you think about it, I should be able to scrape it for scenes where the rain is intermittent. So for example, the rain stops 15 minutes later. Maybe the next day would be too much, but 15 minutes later it would stop. Now I can't look at dynamic objects like cars and so on. So I need to really start training on natural landscapes, natural scenes where there are no animals, basically, right? And so if it works, if we're successful, it's going to be amazing, right? Because now we can mine videos from everywhere to get that diverse rain. This is Wyoming on the top, and then we have Japan, we have Florida, we have Norway, and we have Washington just on the slide with very little effort. In the pandemic, you know, I can just tell you that collecting rainy weather in Los Angeles was very difficult. So this is quite useful. Okay, so you know, there's some logic that you can start to use to be principled about how you do the data collection. You could have a criteria to select scenes based on, for example, if it meets the criteria that there's like no dynamic objects, it's got nighttime, the noise is within an acceptable level, there are water droplets that are not occluding the camera, right? Because we're not doing occlusion removal. Then we have temporal control, motion retrieval, and then finally we have some optical flow methods to try to see if it's windy and correct the images, right, to a degree. It's not going to be perfect, but it's a different data set. We call this GT rain. It's a very different way of creating yet another simulator, is what we thought. Now, typically when you create a new data set, sometimes it also makes sense to create a new model to just eke out a little bit extra performance if you can get it. And so we do have a contrastive learning model here, which essentially is designed to optimize how we derain. I won't go into too much detail on the contrastive learning approach. I'm going to go into some detail on the results, however. So here are the results with this. Okay. So it looks pretty good, but there's definitely some. It's not perfect. It's not like complete perfection. There's some very, very slight frequency variations in the image in terms of spatial frequency because of the motion of the leaves, right? But definitely you're able to remove the haze and also the haze that's caused by rain. And of course, the raindrops are being removed. And so here's the comparison again to MPRNet is probably the best one that we compared to. So I'll put that the best one there. And you can see that the comparison is showing, I think, hopefully some compelling results. Here's another scene. So notice that we can derain dynamic scenes once we've trained on static scenes, right? Because this is image-based deraining anyway, so it's frame by frame. And so here are some quantitative results, all right? What does quantitative results mean in this framework? Quantitative results means it's quantitative with respect to this data set, okay? So now we're evaluating different algorithm architectures. And so you can see that all the algorithms pretty much perform the similar. Like any computer vision researcher worth their salt, we will claim that our algorithm is better, but we're like better by, I don't know, like a dB, which is pretty significant, but still, the real value is coming from the data set being a quantum shift in the thinking of how people have collected previous data sets. Okay, when I say retrained, what that means is, if you look, NPRNet, it's NPRNet when it's trained on the synthetic data that the authors have developed. If you train, you can take the existing models and they're portable, right? They're compatible with any data set. So we can actually train them on this GT-RAN data set and get a little bit higher quality. All right, so now there's a workshop 2 doors down on vision in all weather, but you can also think about doing the same paradigm for any type of weather condition, particularly things like snow, which have maybe extremely high variability. So even more compared to rain, arguably. So here you have example pairs. This is from the data set itself of snow, and you see a little bit more diversity in the contrast differences because of the way snow behaves, right? The shape from shading aspects, like the whiteout effect, are going to be, a little bit tricky. And of course, you're removing the snow flakes. Okay, so here's some results on de-snowing, and as you would imagine, it's relative with the deraining. And if you look at it, you can see that it's not like perfect. There's still some, residual artifacts. It's not, completely perfect, but it's quite good. I think compares to synthetic data. Here's another example. So HDCWNet is a very good network and a very good simulator. But if you look at it, it's leaving a lot of raindrops if you just download images of snow from the web. Okay. And so here's some de-snowing results. Again, the quantitative numbers are not super relevant here for introducing a new data set, because of course we're going to do better on our own data set, right? So it's not super meaningful. But we'll also talk about a little bit of the philosophy in a few minutes about the quantitative versus qualitative in a problem that doesn't have ground truth. Okay, so there is a trade-off. It's not like one of these is better than the other. Okay, it's like which flavor of ice cream do you prefer? Some people like strawberry, and strawberry ice cream, I have to say, I can't really get my head quite around that. So if you look at the synthetic data, this example is not meant to showcase a result where the synthetic data is bad, but basically synthetic data gives you the advantage of the same space and the same time. So you get the same space, same time. If you use GT-RAN, which is the proposed method, you're at the same space, but you're at a slightly different time. So you're going to have artifacts in the training that may be temporal. Now you can filter those out by, again, curating your data set and removing the animals and stuff like that. But you are going to have those kind of artifacts. So that raises the question of which one is better to train ML models. What do you think? Okay, yeah, both is a good idea, definitely. So I think before we go to both, the question we have to ask is, what does better mean? Okay, what is better? This is where a professor takes their lecture and extends it, very long when they start questioning these things. But what is better, right? What is better in a problem that doesn't have ground truth? Because neither model is supervised to learn the gold standard, which is that parallel universe example I mentioned earlier, which does not exist, right? So the question also really is, what do you want? If you look at the ignore the raindrops for a moment, one of if you can call it a feature, you can call it a bug. One of the features or bugs of the GT-RAN, which is on the right-hand side, is although it's removing rain, it's enhancing the contrast here because it's removing the veiling effects of rain as well. Now, you may not want to do that. You may actually want the image to be hazy, and you just want the raindrops themselves to be removed. It depends on what you want, right? Because we're not right now talking about an AI application in autonomy. We're just trying to, do deraining for the purpose of aesthetics almost, right? That's almost how this field is working. So which is better is a subjective question. Okay. So if you look at it, here's kind of the spectrum of different methods that exist. There's really four bullet points here. On the top right, you have the ideal. It doesn't exist. You don't need to worry about it, right? You're never going to get that. On the top left, you have synthetic data, which is happening at the same space and time and has the synthesized rain. But if you look at the models, they don't really clean up the rain in real data. So if you have real data, then you're still going to have a lot of rain that persists. If you look at GT rain, it cleans it up pretty well. There is an interesting method in the middle that I'd like to highlight. Very nice directional that's actually, that I think really inspired us to do GT rain as well, which is called SPA data or SPA net. They made a very interesting observation. This is where self-supervision was kind of used, where they took video streams and they applied a video derainer, because you can look at the temporal motion of rain and say it has temporal motion, and you can apply that to remove the raindrops in video, and then use that to supervise image-based rain removal. The problem is that it doesn't generalize. The video-based derainers themselves are not really ground truth. If they were ground truth, then video-based deraining would be a solved problem, which it is not, right? So that gets us to the question of self-supervision and not. Okay. All right, so now let's go back to the core question of the talk. Is ground truth possible for image-based deraining and deweathering? The answer is really ground truth is what we want it to be, all right? And we can definitely use both. We can use all three. We can use a bunch of methods, okay? But I'd like to change the subject a little bit to sometimes the goal of what we do. This is where I'm going to commit career suicide in part, but also give you a very frank opinion of where I think things have become a little challenging to publish in Vision. So I'll be very candid with you. Our paper has been rejected over and over again because the area chair says this is pushing the community in the wrong direction. It's too simple. Use self-supervision, use synthetic data. And we have other papers. We have a paper at CVPR on synthetic data. But sometimes the really simple stuff is hard to get the community to buy in, right? And everybody has their own rejected papers. But I think what really sticks with me is I read this article about the muon. The muon was discovered, right? They got the mass of the muon in the Fermi lab with a $500 million government project. And it's very interesting how they did that, all right? So they have a bunch of engineers and scientists sitting there measuring the charges, okay? And there's going to be some number that's the right number for the mass of a muon, the charge that corresponds to the mass of the muon. Now, they're trying to experimentally verify a theoretical prediction, so they know what the mass should be. So what they did in the Fermi lab was the instruments, like imagine you have a voltage readout or some sort of display that's reading out a voltage. They actually used a cipher so that the experimenters did not know what the number was. So let's say it's 3 volts. Maybe that number should be, I don't know, modulo pi or something, right? Or whatever, modulo some cipher that they don't know. And so they're reading numbers that they don't know, and so they're recording without bias what those numbers are. Then there's not one, but 2 people who have a physical printout of the remainder of the modulo. Okay, one is in Seattle, and I think the other one was in maybe DC. Okay, so opposite sides of the country, and at the same time, the people who have the cipher who are not involved in the experiment, they're actually professors who are not affiliated with the experiment. They open up the cipher, they give it to the team in a ceremony at 9 a.m. and they apply the cipher to the data, and all of a sudden they see what the mass of the muon is for the first time. Okay? That is kind of the standard that other communities use. And with the deraining stuff, I feel like everyone is guilty. Like I feel uncomfortable with writing papers in some way because I have to put the best results in the paper all the time. So when we went through this exercise, we thought like if we just downloaded images, they'd all work. And this is a solved problem. We didn't know that deraining actually is an extremely open problem, right? And so are we also guilty of that? And the answer is absolutely yes. In the beginning of the talk, to get you interested, I showed you the results that worked. So now we're going to do that sealed envelope test again. Now we're going to just go to Google Images, and we're just going to type in heavy rain image and just pick a bunch of these, okay, and see how they work. This is just picked recently, maybe yesterday night, just at random, seeing which ones work. Now these are your 3 images selected almost at random. The question is, how would this work? So here's our results. And you can see that on these images, I don't know exactly why, but on these images, our results work pretty well compared to NPR.net. Okay. On this image, it's kind of a wash. And in fact, one could argue NPR.net is better in some places and ours is better in other places. Okay. All right, so we're getting close, I think, to deraining. I think definitely now some combination. There's a place for both types of methods, the synthetic data and the real data as well. I think are both together pushing the community where it needs to go. And so we hope this talk opens up, pathways that you consider if you work on this, such as blending real with short time offsets and synthetic data. We can also use the ground truth data set, GT rain. We call it GT rain because there's no real ground truth. GT rain, we can use that to make simulators better to guide their design. So for example, here, like, I don't know why the 2 images on the 2 columns on the left work better for real data. And then the column on the right is mostly a wash between real and synthetic. Maybe the streaks are just more like, I don't know, like this seems pretty streaky, pretty linear. But maybe these streaks are just better tuned to the simulators. I don't know, right? So this image was collected yesterday, so we can definitely do some analysis on, how those raindrops are behaving, why the simulators are breaking on those particular raindrops. And I think in some ways, this is where I will continue the pulpit, since this is a workshop. I guess it's supposed to be a little bit more on the candid side. I think that we should actually start moving back towards the academic contributions of vision, where we were not afraid to present papers that had really terrible results. Because it's okay, I think, for papers not to have terrific results. So I also, we're kind of conflicted at UCLA about what to do, right? Because if we present our paper the next conference that hopefully they'll reconsider this line, right, of work, but we present it candidly without like just cherry picking our best results, then the ideas won't get through, right? So it's definitely hard. So I think some fields of computer vision have done a great job, like Kitty, for example, where you have an external audit that runs your model. It's more similar to that sealed envelope test. And I think ideas like that might be good for the deweathering problem. I'd like to highlight this paper on the bottom. How many people have seen this paper? A lot of people, right? This paper is a 1966 paper from, it's a memo at MIT for the Summer Vision project. If you, it was like first required reading our first year in graduate school. And I think the lesson that it really imparted is that this project was actually a success because it failed. It was a summer vision project, and Seymour Papert and Marvin Minsky, who were pioneers in AI, they said, okay, you know what, like we have these perceptrons, we have these neural networks, so we're gonna connect a camera to a computer and have it tell what it sees, okay? So it should be fairly simple given the other things that we've been doing, like spam filters and stuff like that. And so they tried that and they scoped the project, I think for one poor undergraduate for one summer, was tasked with basically solving computer vision, right? Connect the camera to a computer, tell me what it sees. And so I think in some ways this memo and this project was really influential because of how it probed the difficulty of the field, how it probed the open problems of the field. So I think hopefully that's something we can look forward to, and definitely with blending smoothly the previous work on one stream, which is synthetic data self-supervision, and then blending that with the plain old Jane kind of approach of, all right, let's really go and just try something that seems stupid, right? Let's just try and just collect data that's time offset and see what we get. So with that, I'll kind of end here. And once again, thank the full team that worked on this. We have a multi-institute team that worked on this project. So thank you.
For the real data, could you please flash that? And I'd like to understand
Which slide?
well, the ranking. Like from what I see here, this is not on the high end, but it's very simply not
Yeah. So I think Yunha is here. So Yunha, do you know what resolution we used for the images here in the webcam videos? Yeah. Yeah. No, but 1080 is pretty high, right? 1080 is pretty high. Relatively high, right? On the last one, last test. Yeah, these images were downloaded yesterday. Maybe it's in the. Do you know what the file size of this is? The image size? Okay, let me search Google. Yeah, that could be something interesting. Like what I'm actually trying to see is if we have those three images, right? I wonder if the image that failed had a substantially different resolution, maybe, right? Because there's no resolution curation that's being done when you just select random images. So I don't know what the resolution of those three images is. Yeah, I mean, I think there is going to be some, I mean, to us, I think the bigger domain gap is the motion of the leaves and so on. So you end up actually, if you look at our results, the resolution is not great. If you look at the insets on what we zoomed in, you can see that there's a lot of blur actually on that, right?
Thank you for your really interesting presentation. I was wondering how much, do you know how much, let's say, removing snow and removing rain are competing goals? And could you imagine having a single model taking care of both tasks, maybe add D-days into the mix as well?
Yeah, that's a good question. I don't think that question has quite an answer yet. I think in general, in the short term, I would have different models for this. In the long term, people feel like the search will win out if you have enough data. So in the longer term, maybe there could be a unified model, but I think for the moment, I think it's better to have separate models for the next few cycles of conferences, in my opinion.
Yeah. especially if you want to demonstrate state-of-the-art result on a specific
Yeah.
or
Exactly. You would need a model tune for that. So right now, I think the community has put nice guardrails on different problems. Like there's deraining problem, there's de-snowing problem, and I think following that might be useful. Yeah.
Yeah, so this is more like a general question regarding the data set as an intention, as you sort of pointed to. So machine learning, right? When you have the data set, that's sort of how you specify how you want your model to behave, right? As you sort of pointed out with the derating, like which result is correct, kind of is up to what you want from it, right? So if you have an opinion how in general we actually ensure that the data sets that's used, right, actually matches what we kind of want the algorithms to do in the end.
Yeah, exactly. So first, the answer is yes. It must match what we want the algorithms to do. And I think that question, I think one of the mistakes that we made is we just assume that these results are good. I think we need to do user studies with the broader set of the population. We need to go again and figure out what is the, so we need to pop up, I think, one level and think, what is the point of deraining? What is the target audience for deraining? Is it for computational photography? Is it for downstream object detection tasks? What is the target audience for that? And then based on that, maybe a user study of, okay, which one do you prefer as the ground truth? Could be kind of one way to go for it. Yeah.
Just more questions. So I figure it would be very hard to control the 15 minutes gap from the reading and the after reading all the webcam. I just wonder if itself are going to keep some of the most unclear real images, real images still in the data sets.
Yeah, so we didn't look at unpaired images, but they would be very useful, I think. I think we could keep those in some of the data sets. So I think we're figuring out how we're going to release this to the community. And so definitely if folks want to start using or leveraging these, the unpaired examples, there could be very exciting things to do with them. Yeah.
how is, when you check how consistent your results are, let's say take two pictures of the same rainy scene, how much, and also data depends on the training data, consistency and result of two rainy images of the same scene.
Yeah, it's definitely much more consistent when you have two rainy images of the same scene. So it's definitely something that's playing there with the lighting and the physics of the raindrop, and maybe even the camera settings that were used there. But I think definitely more extensive analysis can be done as an example case, like maybe trying different, like we didn't do any hardware setup here, we're just using webcams. Maybe one example actually tying in with your point is to use different capture setups, different types of cameras capturing the same scene, and also assessing if the camera parameters have an issue on this problem. One of which was pointed out as resolution, but also includes compression and other types of ISP related camera nuances.
No more questions. Let's send Professor Kali again.
Thanks so much. Thank you. Thank you very much. So that they were
Young, I will give a short introduction and then we can get started. I guess. So Professor Minxuan Yang is a professor in WE and computer science in UC Mercy, and he received his PhD degree. Sorry. Oh, you are in the presenter mode.
Oh. Okay, so what do I? So do I need to change anything? I mean, I use a presentation. I don't need to see that, but
I think it's reach. Oh, you see the top left. You can present.
Oh, okay.
There's a button.
Okay. Yes, tell me. Okay, good. Thank you.
Yeah. Professor Minxuan Yang is a professor in electrical engineering and computer science at UC Mercy, and he received the PhD degree in computer science from UIUC in 2000. And his research interests including computer vision, pattern recognition, and artificial intelligence, and robotics and machine learning. And Professor Yang was a program co-chair of ICCV 2019 and was the AC for CPR and DCCV for many years. And he received the Best Paper Award on honorable mention in CPR 2018. And Professor Yang also received the Google Faculty Award in 2009 and the Distinguished Early Career Research Award from the UC University Senate in 2011. And Professor Yang is also a recipient of the NSF Career Award in 2012. Thank you very much.
Thank you. Hi, thank you. Okay, so can you hear me? All right. Yeah, I guess so. Okay, so I got in around midnight, so bear with me. And I wake up like 6:30. So okay. And so today I'm going to talk about recent result on image enhancement. Especially I'm going to talk about image enhancement and video enhancement. And so I will start with MPRNet, and then I'll talk about Restomer. And I will also talk about BIPNet. Both Restomer and BIPNet will be presented in the oral session on Wednesday. So you can ask them for details. I only know the main concept. Okay, so for details, you can check out the code and then you can grill the students. Okay, and then if I have time, I will talk a little bit on frame interpolation and our recent work on super slow-mo, then QVI and VIFTs, which is we're presented on Friday, I suppose. Okay. All right. So first, the first one is the MPRNet, and you will see this the progression how we did that. And this is the main work is done by Awakas and Adia. Okay. So the problem is very simple. I think I don't need to repeat that. Okay. Image restoration. You know, so mainly in this talk, I will talk about deraining, deblurring, and denoising, and super resolution. Okay. All right. So we all know that CNN are pretty good, and then they are pretty good at. So in the past, we've been working on statistical prior. I mean, before deep learning era, so we learned all kind of prior from data, and then use that for. And we also hand code a lot of prior. For that, but ever since AlexNet, we've been using CNN for many things, and the performance gain is mainly based on the model design, as you know. Okay, but one of the things is that the existing methods are mainly based on single stage approach.
Could you screen sharing your presentation?
Oh,
online?
sorry.
Sorry.
Yeah. Yeah. Sorry about that. Okay. I forgot. There's a Zoom one. So
screen sharing.
Okay. Okay. Yep. Sorry. Okay.
Thank you very much.
Sure. Where is mine? No, this is the other one. I have a longer talk, but that's a different story. Okay. Wait, this is video, right? Wait, sorry. My stuff. I don't need this. First. Where did it go? No, this is another one. But where did my slide go?
Open reset. Yeah, this one, and right click. You could open recent.
Oh yeah, I can hold on. Open recent. Where's the UG?
UG2. Yeah.
Okay, okay. Sorry about that. Okay, sorry about that. Okay. Okay, yeah, as I mentioned, so most methods are based on single stage approach. But we find that for multi-stage approach, you can break the problem into simpler tasks. And then we can also use we can use ground truth at different stage for that. And we can also integrate information from different stage together so that we can have better restoration results. And there are a few models that are based on multi-stage approach. But I'll talk about some pros and cons in a bit. Okay, so existing multi-stage approaches are either based on encoder-decoder approach or single-scale approach. So the problem with this is that for encoder-decoder, it is able to encode the context very well, and so but it doesn't have a fine spatial details. On the other hand, for single-scale pipeline methods, they are able to capture spatial details, but they don't encode the spatial context well. So in this work, we talk about multi-stage approach. So basically, we make a few modifications. So first, so if you look at the multi-stage approach, mainly they put the loss function at the end. So basically, you pass the data from and even go through several stages, and in the end, then you have a loss function there, and then you backprop everything. And the other thing is that most multi-stage approaches do not use cross-stage feature, and so we find that you can integrate features from different scale and then at a different stage, and you can have better results. So in this work, we use a multi-stage progressive restoration. So what it is that we have three stages here. So in the early stage, we use encoder-decoder to capture spatial context. And in the later stage, we use a full scale for restoration. In addition, we also add in supervised attention module. Between any two stages, we add in this supervised attention module so that we can better provide local context. And for this SAM, we make two contributions. So first, we take instead of using the ground truth in the end to supervise the process, we take ground truth at any stage and then use that to supervise. Use that for supervision, and we also use that to learn attention map. And this attention map can be used to recalibrate the feature map that we have at any stage, so that we can use them at any stage. And in addition, we also add in cross-stage feature fusions. So basically, from features from one stage will be concatenated with other features and fit into the other stage. So this is what we do, and then we use that for feature from any stage of the encoder-decoder model. Okay, so this is in a greater detail. So in stage 1, we break image into 4 non-overlapping patches. And in second stage, we're breaking 2 vertical patches, non-overlapping. And the idea is the same, except that here I just talk about details about the patches. Okay, so this is how we do that. And so there are several good things about this progressive approach, which I'll get to in a bit. And we evaluate the method on deraining, deburring, and denoising. So we follow the standard setup for that, and we compare with SOTA method on that. And for this MPR net, we have about 20% improvement, about at least 2 dB improvement. And yeah, stop me anytime if you have a question. Okay, and here are some visual results. And we also work on deburring. And then likewise, we also compare SOTA method, including some of our prior method, and they perform pretty well. And the code is available. You can download them for tests. We evaluate on synthetic data and real data, and overall it performs pretty well. Okay, and so here is a in terms of PSNR and model parameter, and we train different model for that, and overall the PSNR is pretty high, and you can choose a small, medium, or large model for that. And here are some deburring results. Maybe this is from Sangyong, okay. Okay. And we also work on denoising. Again, we follow a standard setup, and we do not use any additional training data for this work. So basically just use the typical setup, and then we do not use any additional data for training. And here are some big, okay, so bring to the projector, you cannot see that, but if you look at the paper, I always joke about it. I mean, the projector doesn't help us, okay? So if you look up our paper, you can see more, you can see the clear differences. Okay, so for this work, this is very straightforward. So basically we use multi-stage progressive approach. And why do we use progressive approach? Well, this is like any time algorithm. You know, you can, if you don't have a lot of compute, then you can get the result at early stage, and you know, you don't need to wait until the end. And so, and then we don't need to train a model in different ways. You can take the result from the early stage and use them for result. And so here, yeah, I just want to show you. Yeah, so here what I'm saying is here. So basically at any stage, we have some restore result, and depends on the compute you have and depends on memory requirement you have, then you can take a result at different stage. Or if you have more compute and more memory, then you can use a full stage for that. And this is one good thing about progressive approaches. Yeah, and so here are some comparison with the runtime and parameters, and at the first stage, second stage, and third stage. And for more detailed operation study, please check our paper. Okay, so yeah, the code is here, and I'll search my name, and you'll be able to find it. Okay, and so the second work I'm going to talk about is resolver, and this one is based on transformer. And so the following several words, you will see that we use transformer and for that. Okay, so yeah, we know image prior, and then as I mentioned in the past, we could learn statistical prior from data for that, but nowadays we mainly use GNN or CNN or resolver for that. And so yeah, for CNN, there are several problems for that, and basically it has you have limited receptive fields, and it doesn't adapt to contents. And I'll show you some example in a bit, okay? Okay, so yeah, I'm sure most of you know this. For CNN, the vanilla convolution operator, it has a limited receptive field. But for image restoration, it's important to consider non-local or far range patches. For example, for denoising, in this case, you may want to consider all the other patches, similar patches for restoration. And the other one is it doesn't adapt to image contents. Once you train that, the filter is the same across the field, across the entire image. So, and self-attention, as you know, in transformer has been useful for many things. And we also find that it's very useful for low-level vision tasks. And so in transformer, they are meant to, in transformer block, there are two main things. One is multi-hack self-attention, the other one is the feed-forward network. So in this work, we modify these two, we improvements on these two things for restoration. Okay, so this is a typical one. So this is conventional multi-hack self-attention. This is pretty good. The problem is that, you know, for an image of W times H, width and height, then the complexity is quadratic. So for small patches, you can do that. For large patches, you won't be able to do that. And of course, there are some recent approaches such as string to help resolve this issue, which I'll get to in a bit. But mainly the problem is that, you know, is for image is quadratic. Okay, so the problem, so yeah, so as I mentioned, so there are also other approaches to address this issue. You can limit, you can compute self-attention within a small patch, or you break the image into small patches, either way, okay, and you can do that. The problem is that it kind of defeat the purpose, because what you want to do is you want to compute self-attention across the entire image. But if you do that, you know, it's kind of defeat the whole purpose. Okay, and so yeah, so in this work, what we do is that we transpose. So this is the trick we do. Okay, so here the typical one is the computation complexity is quadratic with respect to image size. So here, what we do is that we compute self-attention on the channel instead of on the spatial domain. So this is what we call transpose. So what we do is that this is the same. We still have one by one of convolution filter, so that you can aggregate pixel-wise cross-channel context. Again, here we operate on the channel instead of spatial domain. And then we introduce depth-wise convolution operator to capture local context. Again, along the channel dimension instead of spatial dimension. This allows us to compute self-attention with complexity of C by C. So basically transpose, you know, it's like this one is HW by HW, but here this one is C by C. So the complexity is limited, it's significantly reduced. This is what we call transpose attention. And so, as I mentioned, so there are two things. One is this multi-head self-attention. The other one is feed-forward network. So this is a conventional feed-forward network. What we do is that we add in, so instead of using the original, first we introduce 3x3 depth-wise convolution operator in that, again, along the triangle dimension. The other thing we do is that we add in one getting network, so that we not only and one goes through a GRU activation, nonlinear activation, the other one is just, you have a typical expansion and reductions. So we add in, and this getting network help us to reduce noisy features. Again, so we have a brochure study to show you everything, all the design, say why we use this and how the improvement for each module. And I won't be able to tell you all the detail here, but just check out that we have all the brochure study on that. So this is the overall architecture. So here we have input, and then this is like MPR net, we have multi-scale. So we original image HW times C channel, and then we reduce that by 1/2, 1/4, and 1/8. And then we start from this, and then we at each level, we have several transformer blocks. And we increase the number of our transformer blocks from top to bottom, and we also increase the number of channels here. And then, so for each transformer block, we have as I mentioned, we have this transpose attention, and then we also have this getting network. And for each one of them, once we compute features, then we upsample them. Here we use pixel shuffling and travel, very simple one. And then we concatenate and then pass on to the next stage, and so on forth until the end. Okay, and so we evaluate this network on derailing, deblurring, and denoising. Okay, so here are some results. So for Rhizomer, it performs pretty well. We compare with our NPRNet and also some other SOTA method. And this one has a significant improvement, at least 1.5 dB improvement. And here are some visual results. And yeah, some visual. Oh, I'm probably go by too fast. I mean, I just use 15 minutes. Okay. Okay. Anyhow, so Rhizomer. Yeah, so stop me and if you find I went by too fast. Okay. So for denoising, we also compare with the SOTA method, and again, it has a consistent improvements. Okay, and for the focus, so yeah, so then there are Sangyong is here, so all right, and then so some other debugging results. Again, I mean, just check out the code, the paper, and the demo are available online. You can find them. Just search one of our names, and then you can find that. Okay, and so I've been talking about image enhancement. So oftentimes we have more than one image. So what do we do? So I will first talk about burst images. So nowadays on your iPhone and all that, you have burst images. So in this, we want to see how we can use multiple image for restoration. Okay, so yeah, so I'm sure I don't need to talk to you about this one. Okay, wait. Okay, so for burst image, basically we have multiple image. Okay, so that, for example, for SR, and in fact, this is the one of the earliest super resolution method was based on multiple image, and then more or less based on this. So now in burst image, you have multiple image, but then they are not well aligned. So basically, the first thing is that we have to align them, and then how do you integrate information from different scale and then put them together? Okay, so for existing method, then they either explicitly compute optical flow or offset so that you can align them. And this one has auto play. So then, but the other thing is that they aggregate feature at the very end. So we found that it doesn't work well. So obviously in our method we use early fusion, and so this one for the first of all the error may be propagated through the process, and there is no access to multi-frame information in upsampling, and there is no communication from different frames. So these are the things we want to change. And for adaptive feature extraction method, they use implicit alignment. They estimate kernels, and then they have adaptive feature extraction and use that. But the problem is that it's bulky, so the model size is large, and again there is no communication between frames, and there is no access in multi-frame information for upsampling. So in this work, what we do is that we extract features, and then we have early fusions, and so in that we have implicit alignment, and we use model frame at the very beginning and use them as a pseudo burst, and then we allow them to communicate. We basically all the frame would be we concatenate with other frame so that we can use them for alignment and upsampling. So here are alignment stages. So for the first one, we have this H boosting feature alignment. And so that from that, we have the roughly aligned features, and then we bring them into bundles. We have this, we call pseudo burst feature fusion. So we have a set of frames, F. Okay, so we have a set of F frames in the burst, and then we concatenate all the information, and then we use all of them for upsampling. Okay. So here are some more details. So the first stage is we have this edge boosting feature alignment. So what we do is that we take one base frame, usually the first one in the burst, and then we use modular deformable convolution filter to compute the offset. And then we align this feature. We align all the other frames according to this first base frame. And in that, we also add in one feature processing module, which I'll explain in a bit. Okay, so in this alignment module, we add in this FPM module. What we do is we use local feature. We use global context for that. And so this one, yeah, it takes a while to explain that, but the main thing is that we denoise the input frame and to facilitate alignment. And we have a residue in residue learning module here. And in that, we exploit global context attention to align all these frames. And then once we align this frame, then we have this, we put the MO element together, we put into a bundle. So we have this tensor, and with that, again, we have a F frame in this burst. And then we concatenate them into this tensors before we feed them into the this UNet module for processing. Okay, so then after that we want to upsample that. So then here we in this work we use 4 frames in each burst, and then we upsample them at different scales. So for each one of them, we have this upsampler here. But basically what we do is that we take 4 frames and then we compute attention maps for each one of them and multiply with each image before we put them together. So this is what we do in this one. And so, yeah, so then for experiment, sorry about that. I mean, the student, I didn't know there is a timer for this one. Okay, so we evaluate this model on super resolution and also on other tasks. And this is an end-to-end trainable, and for each task we train one model for that. And likewise for the MPR and for the resolver, for each task we have to train one. We didn't train everything in one model, which we will do in the future. And we evaluate on the super resolution. And so, yeah, so there are some details and okay, but overall it performs pretty well. I mean, so I'll also as Sang-Yong on that. So we also compare with MPR on that and other sort of methods on that. And overall it performs really well. And we also evaluate on low light image enhancement. And here are some details. Okay, so here are some results on the low light image enhancement. And we also evaluate on image denoising. Okay, so yeah, again, the code, this will be presented on Wednesday morning too, and then the code and the paper are available online, so please check them out. Okay, so I will use a few minutes to talk about our recent result on frame interpolation. So this one I'll play some video, so it's easier. So this is the work we did we published in CPR 18, and this was this was a work in collaboration with NVIDIA people. And so the main thing is that we compute optical flow in both direction, bi-direction, and it also allows for interpolation with, and we can interpolate any number of frames in between. So this one, we basically use the PwCnet for that, and we compute optical flow from both directions. And this allows multi-frame interpolation too. And although the official code was not released, but someone re-implement that and put it on GitHub, and the re-implement one was pretty good. It was pretty close to the NVIDIA one. Yeah, this one was shown in the NVIDIA website. Okay, and so after that, so okay, so the other thing we find out is that for most frame interpolation measure, they do not consider depth information. So in this stand work in the following year, what we did was we analyzed the foreground background and we apply super resolution differently. This is particularly useful for the boundary. When you have depth boundary, when you have depth discontinuity, where with this method you will be able to interpolate frames better. Again, it basically utilizes depth information, and thereby it helps frame interpolation. Okay, and then so in the following year we did another thing. So for typical optic flow is linear operator. So in this work we use quadratic function for that. So in this variable frame interpolation, so what we did was we instead of using linear optical flow, we use quadratic function for that. And this turned out that when you have a draggy videos, which I'll show you in a minute, then you will be able to estimate motion better. Of course, the price you pay is a higher computation load. I should be able to put here. Okay, so yeah. Is it working? Okay, so here. Oh well. Okay, so yeah, so here when you have a dragging motion, then for quadratic function, you can estimate optical flow better, and thereby you can compare with lens SOTA measure, it performs much better this way. Okay, so finally, I will just talk about our recent result. This one will be presented on Friday. So this one is also, again, you will see that over the years, we use different tools. In this work, we use string transformer for that. And so here, the comparison with the SOTA measure in terms of PSNR and the model parameters. So in this work, what we did was basically we extend that for spatial temporal string. And then we separate a spatial domain from temporal domain. And then the other one is that we use multi-scale kernel prediction for when you synthesize the images. So I'll skip this one. So then basically so the main thing here is that, okay, so this is a typical string operation. And if you use it for Valina for spatial temporal work. So what we did was in the spatial domain, we use the same one as strings operator. But then in the temporal domain, we concatenate along the temporal domain and use that for interpolation. So that's the main thing. So basically we separate the spatial and temporal domain, and thereby it allows us to reduce the memory cost and also reduce the compute cost. And we also use a GLU activation like the other one. We also use getting network for that. There are similar tools that we use throughout all these methods. Okay, And so I'll skip this. Okay, this is just coming here. Okay, so here are some results. So this one, we have two models. One is called the base model, the other one is small model. And the small model is we use have and the base model. And we also compare with the other also QVI, which we published in Europe in 2019, and we compare with Dan and Super Slow-Mo, and this one performs reasonably well. So this is Intel PSNR and SSIM, and then this is for a runtime. So basically, as I mentioned, so as we separate spatial domain from the temporal domain, that allows us to have a very efficient model. And with the base model, it's about 0.14 a second per frame on one of GPU. I don't remember the detail. Okay, but if you use small model, it's much faster. So you can decide which one to use. And the code should be available online by now. And here are some results. Okay. Yeah, again, for this draggy video, fast motion video, then these methods are particularly useful. We'll show you side by side. QVI is a quadratic one. So you see some artifact along the dinosaur. I think that's all. Okay, a few more frames. Okay, so to conclude, so yeah, so we use similar tools in all these methods. Basically, we use multi-scale hierarchical models, and we explore interscale interframe features, and usually we have progressive formulation, and as you know, it's all about context and spatial fine detail, and then it depends on how you exploit that. And we also play with channel instead of spatial dimension, and that helps a lot, especially in computation. And that's all I have. It's a short questions. Yeah.
So I have a question regarding the frame interpolation work. You mentioned you use text maps, but the text are not usually available on
Yeah, so there are several ways, right? I mean, so we didn't even use transformer for that. So you still can estimate. The key is that you don't need very detailed or great depth information. All you need is to figure out the boundary, and that will help a lot. You don't need all the details. It's not about estimating depths. Okay, so it's just what we really want to do is figure out where the boundaries are, the motion boundary, and that is important. And if you want to find the motion boundary using depths, then there are some methods that are available. Okay, I mean nowadays there are also depth transformer based depth estimation, right? But again, we didn't even go there because it was 3 years ago anyway. So yeah, you don't need a great. You don't need detail for that. You just need to find out boundary for that, and that will be useful.
I have a question regarding the information picture in the first image restoration. So I think you mentioned that work you're using an early fusion. So what is the particular advantage of early fusion?
Okay. Right. So this is all. I mean, the test is always in the pudding, right? So this is what we test, and then we evaluate, and we find out. I mean, so and this. So is it the final? I mean, is it the only way to do that? Not necessary. But in our model, we test that. Okay, when you fuse all the feature in the beginning or in the end, well, I'm sure the student must have tried it to fuse a feature in later stage, but they find out, okay, if you fix all the first image at early stage, that helps the result better. So that's all I can tell you. I mean, yeah. So for different model for late fusion, you may have good result, but in our case, this is what we find out. Sure. Yeah.
So since you use many self-attention layers in different level tasks, I just wonder if you have studied different number of attention layers in different tasks, because I suppose different tasks may require different levels of global information. Maybe some of them require more, some of them may still survive under confusion layers. I just wonder if you do observe that different tasks require different number of attention layers to the whole.
I think you're right, but I don't think they did any in-depth study on that. I mean, but if you use different attention map for different things, you probably most likely you can have some performance gain, but we didn't try that.
No question. That's a young focus.
Thank you.
Can you hear us? Do you want to share your screen? Yep. We couldn't hear you yet. Hi, Professor Donald Harvey, can you hear me?
Yes, I can hear you.
Okay, that's great, that's great. I think I can give a short introduction and we can get started. Hi everyone, we are happy to continue with Professor Donald Guerri. Professor Guerri is an assistant professor and director of the Image and Video Computing Group in the CS department at the University of Colorado Boulder. And her current research interests span computer vision, machine learning, human-computer interaction, accessibility, and biomedical imaging image analysis. And Professor Guerri's research has been supported by the NSF, Microsoft, Adobe, and Amazon. And she received her PhD from Boston University and was a postdoc in UT Austin, and then became an assistant professor in the School of Information at UT Austin. And thank you very much, Professor Guerri. We can get started.
Thank you so much for the invitation to speak to everybody. And thanks to everyone for showing up for the talk. Quality issues and images taken by blind people, as well as to talk about the implications of those quality issues for AI that describes the images. So why do I want to share about this? The motivation is that as today, there are real users, being people who are blind, who want on-demand visual assistance. On the slide, I just show 4 examples for 30. What flavor is this? What type of pills are these? Please describe what you can see. Are the kinds of information that might be trivial to people with sight, but for people who are blind. And so already real users are relying on kind of on-demand visual assistance. Take a picture, optionally ask a question about that picture, have that sent off to remote humans who in turn will provide an answer if a question was asked. And so I just show on the slide a few of the different applications that have emerged over time to provide this kind of support. This includes VizWiz, Be My Eyes, Ira, and Be Specular. And just to give you context of how many people are using this kind of service today, as of 2021, there were thousands of users of Ira, thousands of users of Be Specular, and 250,000 users of Be My Eyes. And that's just a drop in the bucket of the potential for the number of users. There's an estimated 39 million people worldwide who are blind. So there's really the potential to have far reach with these kinds of applications. What's the motivation for using AI? We know that there's a lot of limitations for relying on humans. Like humans are constantly slow and the privacy issues that humans in the loop. And so a lot of the goal of this work is to teach computers to automatically describe images taken by blind people. I believe, and hopefully I'll convince you by the end of this talk, that many people would find this important. I believe that success with images taken by people who are blind, they translate to helping with analyzing images from other kinds of photographers that have similar abilities. So thinking about robots that similarly have just two cameras where all the intelligence comes from what us as developers embed in them, little children who take photos, as well as wearable devices. I also educate yourselves. One of the things that happens with sight loss is that is on onset as we age. And so you might be developing for future you or your siblings or your friends as you develop this kind of work, if you so desire to jump on trying to improve algorithms for people who are blind. And then of course, there's situational sight loss where we can benefit from having a little bit of assistance. And so with that, what I'm going to go over for the rest of this talk are three parts. First, I just want to introduce what are the AI tasks for describing images by blind people and really talking about what are the quality issues that we know are common for images taken by blind people. And then I'm going to end with a discussion about the AI models and techniques for overcoming quality issues. So with that, jumping in. So the tasks for describing images are twofold. One is captioning. So for this image, something like a bunch of small light brown mushrooms in a green field for answering visual questions, was poisonous. So just the background for how AI challenges work, you have sort of large data set where you have images, and we want to take our large data set and split it into a training set and a test set with the target responses for the test set hidden so that teams can submit algorithms, predictions on the test set to evaluation servers to see which algorithms do the best. And so with that, our team embarked on building a challenge for a real-world application. We leverage data from over 11,000 people who submitted over 70,000 requests to what's called the VizWiz mobile phone application. And this was between 2011 and 2015 when these requests were submitted. We were able to use about 62% of that data because the purpose is to improve upon the technology for describing their images. This is real world applications. So we had to anonymize the data. So we transcribed all the questions to remove people's voices. We resaved images to remove metadata, such as where they're located. We went through all the images repeatedly to verify that there's no personally identifiable information. We came up with a category of about 23 different privacy categories to remove, and that includes things like people's faces, their prescription pill information, as well as information in their mail, such as social security numbers, bills, and much more. And then finally, we went to the crowd and we asked them to produce for us high quality captions, as well as answers to the questions that were asked. And the result is two different data sets, one for visual question answering, which contains 10 answers per image question pair, as well as over 39,000 images with 5 captions per image. So at the time that we released these data sets, these were the first publicly available data sets where individuals requested image captions and answers to support their real daily needs. So just of note, this is a different scenario for data set creation than mainstream data sets. I know this workshop is about understanding real world challenges. One of the real world challenges just from the data set creation is that you can't do what mainstream data sets do, which is to go either and collect images from the or synthetically creating images. And then we also can't make up questions by asking crowd workers to just make them up or use computers to automatically synthesize those questions. So before jumping into the quality issues, I just want to give you a sense of what is the information that blind people are seeking. And so here I show on the slide what were the most popular questions that were asked when questions were asked. We see that the most common question is, what is this? And here I just show a few examples of the images for which this question was asked. So you see things like a remote control. It appears there's medicine on the bottom. We can see there's some pictures of scenes, food such as pizza rolls, and a can of food, seemingly beans. Other common questions included, what is in this can? What does this say? And what color is this? And so for examples for each of these, we see what is in this, what is in this box is the question. And you can see we have boxes mostly of food. So we have things like fudge brownies, macaroni, and then we also have things like Tide bleach for cleaning. For the question, what does this say? That can span anything from reading mail to reading about food and drinks to reading menus as well as computer screens. Insofar as what color is this, I show examples on the slide, and mostly that question has been asked about people's clothes, ostensibly to help them decide what to wear for that day. If you're interested in exploring real people's data a bit more, we do have a live website where you can go and you can review all the images. And then for the different images, you can click on them to get a sense of what does the metadata look like, including the visual questions, the answer data as well. So this is all a backdrop for us to think about how do we make automated algorithms that solve a real world application. And so we did what is standard in the community. We set up public leaderboards to track algorithmic progress. And so teams can see where they fall within the international rankings. We also established an annual CVTR workshop to celebrate progress. We actually have our workshop going at CVTR. And so that's it for what are the tasks that are driven by a real world application. So now jumping into what are the quality issues that we observe from this real world use case. Hopefully it's evident that the challenge for people who are blind and taking images is that they cannot verify the quality of images they take. So it should be clear that there's going to be some differences in the pictures that we're going to see from this population from experienced sighted photographers. And we wanted to quantify what are the differences. So we did a few when we allowed people to provide a caption. We notified them that they could specify that the quality issues in the images are too severe to recognize the visual content. And so when someone was making a caption to an image, they could just say copy to description, and that was the pre-crammed language we had. The other thing that we did is we asked the people when they were reviewing images to let us know what are the quality issues that are observed in the images. We provided it as options: blur, so is the image blurry? Bright, so is the image too bright? Dark, is the image too dark? Obstruction, is the scene obscured by the photographer's finger over the lens or any other unintended object? Framing, Are parts of necessary items missing from the image? And rotation, does the image need to be rotated for proper viewing? We also allowed for users to offer other kinds of issues that they saw beyond what we had identified a priori. And then they could also specify when there's just no issues, meaning that there are no quality issues observed in the image, looks good. What we observed across the over 39,000 images where we collected all this metadata is that over half of the images suffered from one or more quality issues. The slide just shows examples of each of the quality issues that we were looking for. So we could see a blurry image, a too bright image, a too dark image, one where the framing is not of the content of interest. So it's showing more of the hand and not enough of the bottle. We see an obscured case, and then we also see where the image needs to be rotated. When we quantified how often each of these kinds of quality issues occurred, what we observed is that the most common flaws are going to be image blur, occurring for 41% of the images, as well as inadequate framing, which occurs for 55.6% of images. You can see that there are other categories that are actually quite rare. So bright images occurs for 5.3% of images, too dark of images occurs for 5.6%, and obscuring occurs for 3.6%. Insofar as being able to even simply recognize what is in the images, we found that for 14.8% of the 39,181 images, the quality issues were so severe that the content could not be recognized. So with that, now I want to jump into what are the models and techniques we can use to overcome these kinds of quality issues. What I argue is that there are a spectrum of solutions, and our team has embarked on addressing the spectrum where it includes preventive, so guiding photographers to take better images, to reactive, to AI for describing images with quality issues, and then in between to each of these. In the case of preventive, the goal is to help a user understand what are the quality issues when the photographer is taking the picture. And so as a foundation for this work, we wanted to know, can existing techniques that exist for help a user know whether the content in the image is recognizable or not? What we found is that existing techniques do a terrible job of differentiating whether the content in an image is recognizable or not. Okay, so we looked at 6 different methods, and what you can see is there's a high overlap on the distribution, which means basically we can't separate recognizable from unrecognizable with these techniques. We actually want to see those 2 distributions totally disjoint. So that prompts the need for new algorithms that can work well with images from people who are blind. So we actually embarked on that. We found that the algorithm and so we tried some more traditional techniques based on SIFT and HUG features, where we throw a linear SVM after those features. We also tried a 2-layer neural network. What we found is across the board, when we look at 3 different evaluation metrics, we can get pretty good results from such basic architectures. And so this suggests that it should be very easy when a photographer is taking a picture to just notify them, hey, you've got some issue with the picture, try again. We also wanted to do better than just notifying a user of whether the image is recognizable or not. What kind of quality issue occurs? So we, again, have categories of blurry, too bright, too dark, and so on. So we again tried some simple algorithmic frameworks. In this case, we tried a 3-layer neural network using exception features. And then at the final layer, we have 8 sigmoid functions, so that for each of the quality flaws, as well as the no quality flaws choice, we could just flag, hey, this quality issue occurred or not. We again found that across 3 different types of evaluation metrics, we can get a very good job of notifying photographers what are the quality flaws that occur in their images. One thing I like to note is that the performance is worse for flaws, but overall, we do find a good ability to notify photographers about quality flaws. All the data that was used to build the 2 sets of algorithms I described are publicly available. Better algorithms that could then be used to assist photographers to take good pictures from the get-go. Just with that said, I do think there's still an open question of how do we effectively guide a photographer using this information of the quality flaws. It sits a bit on the human-computer interaction side and that community, but basically we need to know how to interface with end users to help them know when they find out the image is unrecognizable or the quality issue, how to improve that image taking skill. And so I'll plant that seed for anyone that's listening and interested in this direction of work. Of course, if there's no issues, then move forward with captioning and preventing low quality images is one extreme. The other extreme is reactive. So let's accept that these images are going to be having quality flaws. And let's design AI that robustly can describe images with quality issues. For the data set challenges we put out there, that is what all the teams have had to contend with. We have had over 60 teams who have participated in our captioning and VQA challenges, where part of what they need to do is make sure their algorithms robustly handle these kinds of quality issues that naturally emerge for the photographers. This is a summary of what are the basic architectures people are building off of. To date, the predominant architectures for captioning have included an encoder, so describing the image using some sort of feature representation. Then attention is used to focus in the image on regions that are more salient into a representation that can be decoded into a sentence. Insofar as VQA, or visual question answering, the architecture looks pretty similar. Again, we are taking an image and we are encoding it into some sort of feature representation. Often attention is used to identify on the image what are the regions that are really important. And then that is paired with an encoding of the question to figure out from the question, hey, this is the set of regions I should look at, such as what's in the background. Hopefully the combination of the background with encodings of different parts of the image would help someone to know to attend to the background regions and what a background means. And then that information gets decoded out into a prediction, where the prediction is from a predefined list of answers, often 3,000 answers. That means, of course, that methods can't handle providing an answer if it goes beyond that scope. Over the years, what we've seen from these 60 plus teams is that the key innovations that are leading to better outcomes on lower quality images include data augmentation, such as rotating images, and then improved pre-training. So the pre-training has been done not only on larger data sets, but on data sets where the images are coming from mobile phone cameras. And so things like LexSmart were trained on massive amounts of cell phone images, which mimics what we see from our photographers of cell phone images. And so we have seen tremendous improvement over the years where models are now outperforming human performance. With that said, we have a question of, well, how are they doing with respect to different image quality levels? And so to assess that, what we've done over the years is we've monitored how they're doing based on how many people from the 5 crowd workers that provided captions used the pre-canned text of quality issues are too severe to recognize visual content. So we said if no one selects this, then it's an easy image. But if 1 to 2 people select that pre-canned text, then it's a medium quality image. And here are just some examples on the slide on the left where you can see the medium quality images. And then we said for high quality images, it's where 3 to 4 people selected that pre-canned text. And you can see on the right examples of very low quality images. Over the years, what we've seen is that the captioning models have struggled on the medium and the hard examples. So the cases where those quality flaws are deemed to be pretty high. And that's true across all the different teams. So here we just show results from 4 teams from last year. And across the board, they do much better for clean images where all 5 people said, hey, this can be captioned. And the performance gets worse and worse for the lower quality images. So I do believe even though we've hit human performance, we still have a niche where we have to do better for where quality flaws are arising. Interestingly, we see a different trend for visual question answering. So for low quality images, these are very low quality. This would be unrecognizable, but the trend, what we're seeing is that models consistently performed better on images with quality issues. The reason for that is because the answers were often unanswerable. And so that's the reason that we're seeing this difference, is that because we allow in VQA for people to say the answer is unanswerable. So with that, again, I think that there's still open space for research here. And I just want to touch on what I think are the open opportunities. And my team has touched a little bit in this as well. I think we still have a lot of work to do on how to train models that handle rare quality issues in the data. I mentioned earlier that we see that some quality flaws happen a lot, such as blur and framing, whereas others don't happen a lot, such as obscured images, oversaturation, and undersaturation between the too bright and the too dark images. So I do think that this issue of not having large amounts of training data presents a problem for our community. And compounding that is that we often will get combinations of these kinds of quality issues in practice. So we'll often see that we'll have both blur and bright, or blur and dark, or blur and obfuscation, or blur and framing, or blur and rotation, and bright and obstructions, and bright and framing, and so on. Those combinations amplify the problem because we even have fewer examples representing all those quality flaws. We know real world data is hard to come by. And so how do we make progress when we don't have a lot of examples in our real world data sets? And so my team has made some research in this direction, but we struggled to find an answer. And so I would pose this for the community, thinking about how do you generalize from a few examples that you can do well when you see these kinds of novel yet rare quality issues in other spaces. All right, so now diving into the final AI component, which is editing images. We have started a little bit of work on thinking about how do you just edit those images when you get low quality data before you pass it off to an algorithm or a viewer. And so part of this means how do you automatically locate the patches where you have issues, such as here, how would you automatically locate the obstruction? And then how do you in-paint some sort of edit to this region? Or how do you automatically locate when there's some sort of rotation and fix the image, and so on. So I think that that's one really interesting direction. And our team has made some progress on a related problem to this, where we actually try to increase our data set size by saying, let's use images where there was private content. So things like credit cards, we removed out the credit card numbers and we in-painted with different in-painting techniques. So again, we're editing the images. In this case, it was to increase the data set size because in a real world application, you just don't have a lot of data. But you can imagine extending this for just editing images for any purpose, whether creating data sets or helping people just take better photographs. And so finding the patches where there's some sort of an issue and then developing and painting algorithms to improve upon the original content so there aren't corruptions. If you want to work on this kind of technique, we do have a visual privacy data set out there that you can use for this purpose. So with that, I would like to wrap up. There are many people who I'd like to acknowledge. We've had many mentees over the years. I have some colleagues who have been fantastic in supporting this work. Then there's those who have provided support with the VizWiz application, the crowdsourcing, the evaluation server. And then we've had thousands of crowd workers who've contributed tens of thousands of hours. And finally, we have received funding from NSF, Microsoft, Adobe, and Amazon for this work. So I want to leave you with some thoughts about potential next steps. We do have a website that you can visit at bizwiz.org. And just a call to action. You can learn more about the technological needs of blind people and what happens in this kind of real world application by browsing the data set at this website. You can also join our many VizWiz challenges for designing algorithms for blind people's data. Inherent in that is you have to deal with the quality issues that emerge in real world applications. And as I outlined in this talk, there are a wide range of them, and they can occur in combinations, which makes the problem very challenging, but very fun. I would encourage you, if you're from industry or you're about to go to industry, to think about how do you deploy these inclusive algorithms for the benefit of society, not just for blind people, but arguably for robots and any other photographers that similarly struggle to take high quality images. And finally, we have an annual workshop, so you're always welcome to come and join our community and hear what we have to share at our workshops and contribute what you have learned. And so with that, I know we have a little bit of time left. I very much welcome any questions from the audience. Thank you so much for your attention and attending this talk.
Thank you, Professor Gregory. This is a great talk. I appreciate that. Any questions from the audience? I personally do have a small question. You can hear me, right? So my question is that
yes, I can hear you.
Since most of the data I think is requested from the online users or blind users, I wonder if there are any long tail or data imbalance problem in your data sets, and especially I think not all the blind people do have access to your to the request. So I wonder if any possible long tail problems will affect the downstream use cases.
Yes, long tail, I think, is the heart of the issue for this community. So the answer is yes, and we have quite a bit of analysis in our captioning data set paper, as well as our visual question answering data set that kind of pinpoint what are the specifics insofar as the categories of the long tails that exist. And so that's just with respect to in the vision language problem and the recognition problem of what is the content that is observed within the data. I would like to expand on that and say we also, I think, have a long tail of the kinds of quality issues that occur. And I know that that matters to this community, and think about what are the rare kinds of photography issues that you may not see from images that you capture online. Long tail and rare categories also persist. So I think I mentioned that this data set was created between 2011 and 2015. If you think about what is it that people want to learn about, what they wanted to learn about in 2011 to 2015 will evolve. And that's just the nature of society. The kinds of technology that existed then, well, we've shifted the kinds of technology we have today. And so as a result, people have new novel categories that need to be recognized. And the reality is we don't have access to that real world data using the VisWiz mobile application anymore. So we can't really upgrade for those new categories that are showing up. And so we still have a long tail problem if we think about how do we incorporate the newer categories for which they weren't present from 2011 to 2015. Maybe we can collect 10, 20 examples by paying people to take pictures for us, but it's hard to access big data. And so that's another aspect beyond just what we observe in our data set of where the long tail problem will continue for us into the future.
Right, I agree. I think it's a long time span that from 2011 to 2015, I think all the devices have been changed and even the quality of the data could be a problem. But I admit that this is a serious challenge. I appreciate that you are targeting on this.
Yeah.
Okay, if no more questions from the audience, let's thank Professor Donald Guerri's great talk. I do appreciate your time and thanks for joining us.
Thank you so much for the invite. Enjoy the rest of the workshop.
Thank you. Thank you. Have a nice day. Okay, we will have a 1 hour lunch break and all the talks in the afternoon will be online and we shall rejoin in an hour. 得这样。哦。
Many individual point sources of radiation.
你那儿有声音是吧？就是它的音频的，就是视频声音从你那边能传来，所以你待会儿就你那边全都 disable 了。OK， 行，好。
Oh, yeah.
As a Keiko is experience.
Hi, I'm here.
How are you, Keiko?
I'm doing good.
So Dan won't be here today, and he's in transit, so he won't be even able to join us for the Q&A.
Okay.
Which I think is okay.
Mhm.
You can answer questions, right?
Yeah, we can handle that.
One control overview, one slide. It's very.
And then Russ is joining us also.
Russ will join live for Q&A.
Okay. I don't see him on the list yet, so.
Or we can just play, I will show the whole screen actually. Okay, so let's get started. Thank you for coming to the afternoon section here. Stanley Chen from Purdue University. We're gonna play two videos with you for the two talks. One is by Daniel Lamaster from Air Force. The other one will be from Russell Hardy from U of Dayton. So Dan is not able to join us today for the Q&A. So he sent us a video. We're going to play it. If you have any questions, I'll try my best to answer, but I probably cannot answer too many. And then we're going to do another talk by Russell Hardy. And then Russ says he will be able to join us for Q&A. Okay, so without further ado, let me start by introducing the first speaker. And Dan is with Air Force Research Lab. He's a fellow over there. He has been doing a lot of work on imaging through turbulence. He's sort of overseeing quite a few programs in the Air Force Research Lab. The talk that he has today is a review of turbulence and refractivity effects on imaging systems. So this, if you know, this year in UG2 challenge, we have a track on imaging through turbulence. And so it's really my pleasure to have Dan here, although virtually on this video, to tell us a little bit about the problem of turbulence. Okay, so I guess we can get started.
Thank you for your attention and to the organizing committee for this invitation to speak. I'm Dan Lamaster, and it is my absolute pleasure to talk to you today about turbulence and refractivity. First, here is a conceptual view of imaging through turbulence. Starting on the left, imagine that we're imaging some object of interest and that this object is composed of many individual point sources of radiation. These point sources radiate incoherently, which is to say that the light waves leaving any point on the object are not correlated in time or space with waves from any other point. This is a good representation of natural light, for instance, reflected sunlight, which is in contrast to a coherent source like a laser that we would need to treat somewhat differently. In the absence of turbulence, these waves would propagate to the right with some portion being captured and focused onto our camera's detector array. For an ideal optical system, blur due to diffraction of these wavefronts is the only limit in our ability to resolve each point reproduced in the resulting image. However, When a volume of turbulence is present between the object and the imaging system, these wavefronts become increasingly distorted as they propagate. You can imagine the crest of each wave deforming, with some regions falling ahead or behind. These effects are cumulatively referred to as phase errors, and these phase errors result in a distorted image of our point, so that diffraction is no longer the limiting factor in terms of resolution. The physical mechanism behind turbulence-induced blur and distortion is random time and space refraction variations, which is distinct from diffraction at the aperture, which is fixed across time and space. In the previous slide, I depicted turbulence as being distributed uniformly along the path between the object and the imaging system. Before we go on, let's imagine a different case where turbulence is concentrated near the aperture, in the middle of the path, or at the end. In the video on the left, where turbulence is close to the aperture, blur and global motion dominate. Everything looks like it's moving together. This is because the wavefronts from the distant point sources are all more or less experiencing the same phase distortions. In the middle of the video, the strength of the turbulence is the same, but now shifted to some middle point in the path. You might see that now the warping is evident in addition to blur. The points no longer move together. This is because waves emanating from different points in the object are now partially interacting with the volume of turbulence in different ways. And finally, on the right, turbulence is concentrated close to the object. Blur is hardly noticed at all, and there is just warping. Now each point on the object interacts with a local patch of turbulence. A local patch of turbulent air, resulting in a tilt of the wavefront, but not much else. The key takeaway from this slide is that the effect of turbulence on an image depends on how the turbulent air is distributed along the imaging path. We will return to this idea many times as we discuss path weighting functions. As an example, to drive the point home, imagine that a camera is on the Earth's surface and a camera in orbit. Imagine that a camera on the Earth's surface and a camera in orbit are imaging each other simultaneously. These images are made through the same volume of turbulent air, but the image taken on the ground will be much blurrier than the image taken from space. This is why you don't hear about Planet Labs or Maxar worrying about correcting imagery for turbulence. When I talk about a volume of turbulence, I am specifically talking about variations in the refractive index of air. Remember that refractive index is a quantity that expresses the apparent speed of light as it propagates in a medium. It is helpful for me to think of this relationship between speed and phase when considering turbulence distortion of wavefronts. There is a small random component of the air's refractive index, N1, that is responsible for turbulence. The characteristic time scale of turbulence variations are on the order of a few milliseconds, along with spatial scales from millimeters to tens of meters, all overlapping. This structure is caused primarily by temperature variations, though wavelength and to a lesser extent, other factors like pressure contribute as well. This N1 term rides on the much larger N0 term, and I will refer to gradients in this term as refractivity, which is also driven by temperature, but also moisture over time scales that are much longer than in the turbulence case. Also, you will see toward the end of this presentation that the effect of refractivity is the same over large spatial scales. Once again, much of the image will move together, but this is unrelated to the global motion case for turbulence near the aperture. Refractivity effects accumulate over the entire path. Due to the random nature of turbulence, it is most useful to talk about concepts in terms of the statistics of refractive index rather than the index itself. The refractive index structure parameter, often referred to as CN squared, is probably the most useful statistic to know. CN squared tells you about the strength of spatial variations in the refractive index in terms of a structure function. If your experience is similar to mine, then structure functions are less familiar than the related concept of a correlation function. For our present purposes, it is enough to remember that when a structure function is increasing with separation distance r, then the corresponding correlation over that distance is decreasing. I think that the structure function is preferred over correlation in turbulence matters simply because the structure functions are readily identifiable components in the dominant derivations of concepts like long exposure MTF, which is something that we will discuss later on. So higher CN squared means that refractive index is decorrelating more rapidly in space. For shorthand, when you see CN squared, think strength of turbulence. CN squared also varies in time and space. On the left, you can see measurements of CN squared as a function of altitude for a late summer day near Wright-Patterson Air Force Base. In general, you see CN squared decreasing as a function of altitude, but here we have an interesting bump at a few hundred meters. This bump is, sorry, the phone keeps ringing. This bump is due to an inversion layer, essentially a region of warmed air that is sandwiched between cooler air above and below. The height of the inversion layer varies and is, in fact, somewhat low in this case, with 1 or 2 kilometers being typical. The smaller bump at around 10 kilometers is due to a wind shear layer that ranges from 8 to 14 kilometers in height. The red curve, the HV57 profile, is a general purpose nighttime turbulence profile used as a handy reference. But it's important to realize that these profiles will vary significantly depending on when and where you make the measurement. On the right, you can see a plot of CN squared near ground level as a function of time for a midwinter day in 2019. Minimums around sunrise and sunset are expected, though in this example, the minimums occur a couple hours before sunrise, maybe due to clouds, but the evening minima looks right, occurring right around sunset. You probably already expect that higher CN squared means more blur and warping. Here is an example that shows a time sequence of images collected under identical conditions except for changes in CN squared. In this case, it's fine to imagine the turbulence being once again uniform along the path. On the left and rightmost cases, you see the most motion, most blur, and most warping. In the middle, where turbulence is less, warping, blur, and motion decrease. Of course, CN squared alone doesn't fully describe the blurring and warping effect of turbulence. Now I want to introduce a new concept, the coherence diameter, also called R0 or the Fried parameter, that is useful for characterizing imaging blur and takes into account both CN squared and path weighting, which is something I promised to talk about early on. Before we get to some math, here are some zoomed in images of the moon's surface taken under 2 different conditions. On the left, R0 is very large, and on the right, R0 is more typical, near sea level at visible wavelengths. The Fried parameter has units of length and is typically expressed in centimeters. R0 is defined as the diameter of a circle where the root mean square departure from a perfect spherical wavefront is equal to 1 radian. But the key takeaway is that just like aperture size, a larger coherence length means better spatial resolution, at least until the aperture itself becomes the limiting factor. Here's how R0 is calculated, and I would like to point out a few things. First, notice the wavelength dependence. R0 increases with wavelength. If this were the only consideration, it would appear that we could mitigate turbulence effects by building cameras that are sensitive at longer wavelengths. Unfortunately, for a given aperture, diffraction works against us, with resolution decreasing with increasing wavelength. The second thing we see is this Z over L term, where Z is position along the path and L being the total path length. It appears in an integral with CN squared, and as promised, now we have an analytical expression that includes path weighting. Clearly, turbulence near the aperture, where Z is equal to L, will have a bigger effect on R0 than turbulence near the target, where Z is equal to 0. We saw this on slide 3. Lots of blur when turbulence is concentrated near the aperture, and no blur when turbulence is concentrated near the object. Now we can turn to the plot on the right. For completeness, I'll say that the vertical scale resolution is defined to be the volume underneath the optical transfer function, and that it is normalized to the case of an infinite aperture. The horizontal axis, d over R0, is the ratio of the aperture diameter to the coherence diameter. Next, you see two highlighted curves, one for long exposures and one for short exposures. The distinction here has to do with the exposure time of the image. So in other words, it is long or short compared to the time scale over which turbulence is changing. And we'll talk about that more later as well. Looking at the left side of the chart, for small apertures, it is clear that turbulence will not have a noticeable effect for long or short exposures. This explains why turbulence is not a perceptible problem in our everyday experience with vision, cell phone cameras, and so on. For the long exposure case, when d over r naught becomes large, the coherence diameter sets the upper limit on achievable resolution. Now look at the blue short exposure curve. It tells you that you can expect to achieve better resolution with an average short exposure image than you will with the long exposure case. And that is true at least beneath d over r naught less than 30 or so, which is the portion of the chart that is of practical interest. This is our first clue to an important insight. For larger apertures, from an image restoration perspective, it is almost always better to work with a series of short exposure images than to work with long exposure images with the same equivalent total exposure time. At a glance, it might seem strange that resolution is less than 1 beneath d over r0 equals 1. But this just means that the aperture is limiting resolution rather than turbulence. Also, you may wonder why resolution is less than 1 for a certain, is more than 1 for a certain part of the short exposure curve. This is due to Fried's choice of normalization to an infinite aperture, but does not mean that you are somehow imaging beyond the diffraction limit for any practical aperture. So here is a sequence of short exposure images at the top with the corresponding long exposure image at the bottom. Note that for this simulation, I use a case where all turbulence is concentrated near the aperture. This is not realistic for the scenario implied by the tank image, but it gives us one point spread function for each short exposure image, which will help convey my next point. First, the long exposure image is well approximated by summing the short exposure images. As expected, you will see that on average, you can make out more details in the short exposure case than in the long exposure case. Now notice how the short exposure point spread function moves around. In this example, adding the images is equivalent to convolving the true object image with the sum of the point spread functions. This leads us to an important insight. Most of the blur in long exposure imaging comes from the motion of the point spread function that occurs over the interval while light is collected. This turbulence near the aperture case, which is also referred to as the isoplanatic case, provides us with a straightforward demonstration of this concept. But the insight is true in general, no matter how turbulence is distributed along the path. You can always use it. So now you know that you want to work with short exposure images. How short is a short exposure? I cannot make a prediction in general, but I can offer some insight for the special case of adaptive optics. AO, or adaptive optics, is a hardware-based approach for optically correcting turbulence before detection that is very well suited for certain cases like astronomical imaging from the Earth's surface. In this case, you can think of the Greenwood frequency as the number of optical wavefront corrections that need to occur per second in order to maintain a sharp image. The inverse of the Greenwood frequency gives us some sense of the coherence time of turbulence. That is to say, how much time must elapse before significant changes in the spatial distribution of turbulence will occur. The Greenwood frequency depends on wind speed and CN squared, which makes sense because more spatial structure and turbulence should cause faster changes in the character of the point spread function. If our exposure time is equal to the coherence time or less, then we can say that we have collected a short exposure image. An image that is exposed for many coherence times is a long exposure image, and I don't have a name for anything in between. So what happens in between? You can expect to trade some resolution, perhaps for an increased signal to noise ratio. Now let's focus specifically on anisoplanatism. This is the case where blur and motion are space varying and it is what you should expect to occur in most normal imaging conditions. You see the LED array at the center of this image. Notice how each LED is blurred in a different way. This is precisely what we were talking about. You can also see anisoplanatism on display in the tri-bar resolution target as well. Adjacent bars are sometimes resolved and sometimes not. The warping of the bars is a result of anisoplanatism as well. This is a hard restoration problem to solve, especially when there's also real motion in the scene, in addition to the apparent motion of turbulence. Now, on the far left, the bright object you see there is the transmitting end of a turbulence measurement device known as a scintillometer. I'll point this out now since I'll be talking about it later. We can borrow another idea from adaptive optics, the isoplanatic angle, to get some physical insight into the causes of anisoplanatism. The isoplanatic angle is the angle over which two field points experience the same phase distortion. Note that this parameter is weighted toward the object end of the optical path. This is the opposite of what we saw for the coherence diameter. This figure on the right from Russ Hardy does a great job in illustrating why this must be. Concentrate your attention on the green and blue boxes. Do you see how they overlap more near the camera, but don't overlap at all in the object plane? In other words, the image of both points on the object are affected by the same phase distortions near the aperture, but by totally separate distortions near the object. The isoplanatic angle is chiefly concerned with the differences in distortions, which are greatest close to the object and hence receive the greatest weight. Now, it would be nice if this adaptive optics concept translated directly to our general imaging concept, to our general imaging through turbulence problem, but this is not the case. The isoplanatic angle is not also the angle over which blur and warping in the image remain the same. Fortunately, for image restoration purposes, this angle is actually somewhat larger as a practical matter, though I don't have an analytical expression for this that I can offer. Now let's focus specifically on the image motion part of the problem. You won't be surprised to learn that this is readily described by another structure function, but this time in terms of apparent angular motion in the image. I've given the structure function here in terms of a time average rather than an expected value because, unlike CN squared and refractive index variations, residual motion can be measured directly from a sequence of images, and a time average is a practical way to do this. Though I know that you know that this is not really the same as calculating an expected value. I'll call your attention to two components of motion, global motion in blue and residual space varying motion in yellow. On the next slide, we'll look at how path weighting effects affect each. First, global motion. This is the delta squared expression on the left of the slide. You'll see that it has the same path weighting as coherence diameter, which is to say that global motion is weighted most heavily to turbulence near the camera aperture. On the right, I provide an expression for the residual space varying component of motion, decomposed into two orthogonal orientations. These expressions are a mess compared to everything that we have seen so far, but don't worry about the details. The most important thing to know is that for differential motion in the scene, the path weighting changes with separation distance, and this is something that we haven't seen before. On an earlier slide, maybe you were wondering how CN squared altitude profiles are measured. One way is to launch balloons that sample temperature and then translate these temperatures into differential refractive index and then calculate CN squared. Another way is to exploit the path weighting differences that you see on this slide to infer CN squared as a function of distance along the path by tracking a multitude of points in an image. And in fact, the CN squared altitude profile that I showed you on slide 6 with the inversion layer bump was generated by exploiting differential motion for points tracked on the moon.
Quiet time So he recorded the video. He doesn't play it.
Speed up a little bit.
There's no sound. I think we might actually check. I didn't check. I think there is sound. When I watched the video, I think there was sound. And yeah, there's no sound coming out.
Oh, I think he mentioned that he had a 1 minute gap without any sound. That mentioned like it's 30 minutes or 20 minutes.
Yeah,
right. There is a 1 minute without any sound.
And then
But we are still. Yeah, music is just
past that.
yeah, we passed it already, but there's still no sound.
There's still no sound. Oh, really?
Oh, it's 26 now.
I actually, okay, when I was
I think before is okay.
Yeah.
Mm.
Can we go back?
Yeah, we can go back.
And see if the sound is video copying.
Is that you see on this slide to infer CN squared as a function of distance along the path by tracking a multitude of points in an image. And in fact, the CN squared altitude profile that I showed you on slide 6 with the inversion layer bump was generated by exploiting differential motion for points tracked on the moon.
After 1 minute, I think I can hear the sound after 1 minute.
Yeah, I remember I heard the sound.
Yeah.
Here are some nice examples of path weights for global and differential motion over a 1 kilometer path. As a reminder, the camera is at the 1 kilometer point in this figure. The red curve, which corresponds to delta squared on the previous slide, is weighted most heavily near the camera. This is what we expect for global motion. For differential motion, the green curve represents larger separations between points, and the blue curve represents smaller separations. Together, they show that the differential tilts will remain small when turbulence is concentrated near the aperture until separation between points of interest become relatively large. In contrast, if turbulence is concentrated near the target object, so at 0 kilometers in our figure, then this path weighting shows that differential tilt will be more evident for more closely spaced points. These outcomes were exactly what we saw in the resolution target simulation videos back on slide 3. Before moving on to refractivity, I'll close the turbulence discussion with scintillation. The phenomena of scintillation is probably how we all first encountered turbulence. That is to say, as children looking up at the night sky and twinkling stars. This brings us to a key point. The scintillation effect is most commonly observed as the temporal or spatial variation in the received intensity of point sources. The image on the left is a fine example. Each LED in this array has been adjusted for equal brightness at the source but propagation through turbulence results in a range of observed intensities. This ranges from bright to barely perceptible. For extended objects, scintillation can be ignored, but let me mention these two things. First, the path weighting for scintillation peaks in the middle, which is different than the other quantities that we have considered, like coherence diameter, which is shown in blue. Second, for a range of conditions, a two-part device called a scintillometer is a very popular way to estimate CN squared along a path. I pointed out one end of a scintillometer in a picture back on slide 12. A scintillometer works on this principle, but not exactly using the equations that you see here, which are for the case where both the transmitter and the receiver are theoretical points. After all this talk of path weights, I hope you'll leave my presentation as a savvy consumer of CN squared data. Imagine that someone offers you their CN squared measurement. What does this measurement mean? If it's from a scintillometer, this measurement is mainly telling you something about turbulence conditions around the middle of your path. If, on the other hand, someone were to estimate coherence diameter or global motion from an image, and then from this infer CN squared, then the estimate would mainly tell you something about the turbulence near the aperture. You can work through the ramifications for differential tilt measurements and so on as well. And now refractivity. Remember, refractivity and turbulence are different things. Refractivity effects are born from large-scale gradients in the refractive index of air, where turbulence is caused by rapid random fluctuations in this refractive index. These index gradients are driven by air density gradients and cause rays of light to curve away from the direction of decreasing air density, which is the same as saying that these rays curve away from the direction of decreasing refractive index. Mirages are an example of refractivity in action, and in this sailboat example, you can see how a temperature inversion forms a mirror-like inverted image in the sky of objects on the ground. This is known as a superior mirage. An inferior mirage occurs when temperature decreases with height, resulting in increasing refractive index. This is what you have seen during summer as shimmering pools of sky out on the road. The image on the right is a result of multiple layers of warm and cold air that result in the appearance of both types of mirage. We don't often notice it, but refractive bending occurs all around us every day, even without inversion layers. In the example you see here, images are taken at 10-minute intervals from a location just down the street from my office over to a hospital on the opposite side of the Miami Valley. This is a total distance of about 13 kilometers. As you can see here, the apparent altitude of the hospital shifts dramatically, particularly during the transition from night to day. The equation here gives you some sense of what's happening. Changes in temperature lead to changes in the index gradient, kappa, which leads to an offset or deflection of the image that grows with the square of the distance to the observer. Thinking about this, maybe you have guessed that in some cases, refractivity would allow you to see below the geometric horizon. In fact, this is a common occurrence at sunrise and sunset. I haven't measured the effect myself, but I have read that the sun is visible 2 minutes earlier than geometry alone would predict at the equator, and this is due to refractivity. Just for fun, here is an image that might plausibly be the longest range photographic documentation of an object below the horizon by exploiting refractivity of air. The mountaintop is over 500 kilometers away. You should read the article if you get the chance. It's open access. The author discusses many interesting details that we haven't discussed here. And finally, let's imagine a case where a telescope on the ground is observing an object as it moves through an inverse temperature layer. Look at what happens as I click through the different object altitudes. The image itself is demagnified in one direction as I move into the higher temperature region, and then it expands as I move out again. The outcome of this simulation was not at all obvious to me, but is completely consistent with the nature of refractivity. Maybe someday I can use the turbulence profiling technique that you saw in slide 6 to hunt for low, thin inverse temperature layers, and then fly a drone carrying a resolution target to obtain experimental evidence for this refractive phenomenon. Until then, you can read this paper too. It's a lot of fun. Thank you again for your attention, and to the organizing committee for the invitation to speak. I'm sorry that my travel plans have not allowed me to participate in person, and with some luck, I will join you next year. In case I am not available to answer questions, feel free to contact me at this email address, daniel.lemaster@us.af.mil. So thank you again. Enjoy the rest of your day and the rest of the conference. Goodbye.
The answer. If not, I think Hegel is here. You can help.
Yeah, I'm still here.
The technical question, maybe we can.
Hello, this is Russell Hart presenting some of our recent.
So the second talk is by Professor Russell Hardy from the University of Dayton. In case you guys don't know, your Dayton is right next door to Air Force Research Lab. So close collaborators. We also the co-author of this work is Michael Lucci. He's also one of our collaborators on this imaging through turbulence project. So Russell Hardy has been working a lot on this atmospheric turbulence actually way before us starting to work on this problem, and he has a lot of great experience on this topic. So he's going to talk about atmospheric optical turbulence modeling, simulation, and mitigation. So it's really the whole package of this pipeline. And so Russell promised us to join us today to take Q&A. So maybe we can play the video first, and then we can have Q&A.
Hello, this is Russell Hardy from the University of Dayton. I'm pleased to be joining you for CVPR 2022. I'd like to thank Dr. Stanley Chan and the other conference organizers for inviting me to give the presentation and for accommodating the video format. On behalf of my colleague, Mike Rucci, and my other co-authors, I'll be presenting some of our recent work in the area of atmospheric optical turbulence with regard to modeling, simulation, and mitigation. I'll begin with a brief introduction of atmospheric turbulence, and then I'll talk about some important turbulence statistics, optical transfer functions, turbulence simulation, and finally, turbulence mitigation algorithms. Atmospheric turbulence can be a significant source of degradation for long-range imaging through the atmosphere. The index refraction of air is very close to 1, but it does vary with pressure, temperature, and other factors. So index variation along the optical path causes refraction that disturbs the wavefront of the light coming from the object plane. And the result is imagery that's blurred and warped. And because the atmosphere is dynamic, the degradation's time vary. The picture shown here shows a point source and shows these blue pockets indicating a slightly different index of refraction. And you can see that the wavefront becomes progressively distorted as it propagates from the object plane to the pupil plane. The video here shows an example of the spatially and temporally varying nature of the atmospheric turbulence. Now, restoring imagery that's been degraded by turbulence is a very interesting and challenging problem, in my opinion. From a signal processing perspective, it's very interesting. And this is because the degradation is both spatially and temporally varying. But the good news is there's a rich framework of statistical models that can be drawn upon to aid in the development of image restoration algorithms. I'd like to talk now a little bit about the differences between astronomical and terrestrial imaging scenarios. In astronomy, the telescopes tend to have a very narrow field of view. And in this case, the degradation from the atmosphere may be uniform across the image. This is what we call isoplanatic imaging conditions. Here, only one point spread function is needed to model the degradation across the whole image. Also, in astronomy, artificial guide stars can be generated with a laser source from the observatory and positioned near any object of interest. This allows us to obtain a measurement of the local atmospheric point spread function, and adaptive optics can then be used to compensate for the point spread function degradation. In contrast, terrestrial imaging tends to involve a much wider field of view. This means that the atmospheric degradation will tend to vary across the acquired imagery. And this is referred to as anisoplanatic turbulence. Because we have an extended scene and anisoplanatic conditions, conventional adaptive optics is not well suited to terrestrial imaging. The typical approach to turbulence mitigation used here is to acquire a sequence of short exposure images and then use post-processing turbulence mitigation used here is to acquire a sequence of short exposure images and then use post-processing.
Maybe some network issue, I think. It's off rendering anymore.
To acquire a sequence of short.
Let me refresh my page.
Varies according to this refractive index structure for the remainder of this presentation. Let's turn our attention now to some important turbulence statistics based on the Kolmogorov model. Kolmogorov turbulence assumes that the index of refraction varies according to this refractive index structure function. The refractive index structure function involves here the index of refraction of the air at position x, that's a 3D coordinate, compared to the index of refraction at some offset coordinate, n of x plus r. Note that the brackets here refer to an ensemble average. So the model says that this refractive index structure function is equal to the magnitude of the displacement, magnitude of r, to the power of 2/3 times the constant referred to as the refractive index structure parameter. Now, when the turbulence varies along the optical path, we, instead of using a single Cn squared, we talk about a Cn squared profile where Cn squared varies along the optical path. One of the most widely used turbulence statistics is the atmospheric coherence diameter, or Fried parameter R0. It's defined as the diameter of a circular area on the pupil plane where the RMS wavefront aberration from turbulence is 1 radian. One typically compares the Fried parameter to the aperture diameter d. And if R0 is less than d, then the imaging system is more limited by turbulence than it is by diffraction, and vice versa. For spherical wave propagation, the Fried parameter is given by this expression here at the bottom, which is calculated in terms of the Cn squared profile. Now, the Fried parameter plays a big role in tilt statistics and the optical transfer function that we'll introduce shortly. To capture how spatially varying the turbulence is, one may use the isoplanatic angle statistic, computed as shown here. Roughly speaking, 2 point sources within one isoplanatic angle of each other will have very similar point spread functions. To illustrate this, consider the video shown in the lower right. Every second of video is an angular change of one isoplanatic angle for a constant atmosphere. So we can see that as the angle changes, we get a different point spread function. And with a change of about one isoplanatic angle or 1 second, there isn't much change in the point spread function. But in the span of several isoplanatic angles, we see a great deal of evolution and change in the point spread function. The warping due to turbulence can also be described in terms of tilt statistics. For a point source originating from an angle of theta, let the Zernike tilt be defined as z tilde of theta. This represents the angular tilt caused by turbulence for that source. The two-axis z tilde variance may be expressed in terms of the free parameter, the aperture diameter, and the wavelength lambda. Now on the bottom, I have some pictures. On the left, there's a scatter plot showing some tilts as measured on the focal plane of the camera for different realizations of the atmosphere. You can see they have an approximately Gaussian distribution and a zero mean, and this is relevant later. Now on the right, I'm showing the wavefront as measured in the pupil plane and a best fit plane, and that best fit plane defines the Zernike tilts, which affects the position of the point spread function on the focal plane. So with each wavefront, the corresponding point spread function is shown on the right. And you can see the centroid indicated with the red dot and the z tilt shift from the plane indicated with the blue circle. Going beyond tilt variance, my colleague, Dr. Santashri Bose-Pillay, derived z-tilt correlation statistics for spherical wave propagation. These expressions give the correlation in radians squared for tilt components that are parallel to the source separation and perpendicular to source separation. I'll say more about that in the next slide. Basically, sources that are very near each other will tend to tilt in near unison and have a very high correlation. As the source separation increases, the tilts become less correlated. But interestingly, the correlation for the components of the tilt that happen to be parallel to the source separation are different from those that are perpendicular to the source separation. Consider an optical system with the parameters shown in the table here. And by the way, all of the simulations and the rest of this presentation will use these same parameters unless otherwise specified. Now, the tilt correlations that we showed previously are plotted here in this figure, both the perpendicular and the parallel component. To understand why these are different, consider the diagram on the upper right. This shows 2 point sources producing spherical waves. And notice that when you consider the overlap area, there's more overlap in the vertical direction, the blue arrow direction, than there is in the horizontal. And the horizontal direction is parallel to the source separation. So we have more overlap in this perpendicular direction and less overlap in the parallel direction. And that gives rise to the two different correlation functions. The other thing to note about these curves is they drop as we'd expect with greater source separation. There's less correlation. But notice that even out here to 700 pixels, these have been converted to pixels. The distance has been converted to pixels. Even out to 700 pixels, there's still a fair amount of correlation. So this has consequences for the impact of turbulence on images. There tends to be a very large scale global shift that we see in the imagery in addition to local warping. Now the parallel and perpendicular tilt correlations can be converted to more traditional wide sense stationary 2D spatial correlations using vector projection. This clever transformation was done by Schwartzman and his co-authors as part of the development of a warping simulator in the paper cited at the bottom here. And we utilized the same trick, but using Dr. Bose-Pillay's statistics, and the results are shown here. So what you can see is a 2D autocorrelation for the horizontal tilts, and here we see the autocorrelation for the vertical tilts. And notice that there is some cross correlation between the two. And also notice that the X and Y correlations are not circularly symmetric. However, the total correlation that we get if we add the two is in fact circularly symmetric. And we're going to use these statistics here to aid in our optical transfer function models. And we've also used this to aid in a free parameter estimation algorithm. Our idea is that we could define something like a patch tilt variance by imagining applying a moving average filter to the tilt fields. And the moving average filter could have the shape of any patch of interest. The result is that we get a modified tilt field. The correlation functions for this modified tilt field can be found using the well-known properties of random processes through linear shift invariant filters. We can evaluate the modified correlation function at 0 to get the patch tilt variance. This can be useful for understanding how groups of pixels, patches, or even large, a full-size image, how those images move and warp in turbulence. We can also understand how block matching image registration impacts the warping from turbulence. And we do that in a similar fashion, but here we use a residual filter impulse response that is a high-pass filter. And that high-pass filter is a Dirac delta minus a patch-shaped moving average filter, and the patch shape is the block shape used in the block matching algorithm. So the resulting tilt fields would be the residual tilt after registration. And the correlation for that residual tilt field can be found in the same fashion as before, and we can evaluate that at 0 and get a residual tilt variance. And this is a post-registration residual tilt variance. So let's consider a registration process employing 101 by 101 block size. And that registration should reduce the tilts and produce residual correlations that are much lower than we started with. So this plot here on the left shows 3 things. One, it shows the input one-axis tilt variance with no registration. And then the red curve shows the patch tilt variance for an ever-increasing patch size. So when we increase the patch size, we're averaging more pixels and we're getting a lower average tilt from that averaging. The residual tilt variance would then increase with patch size because a larger patch, block matching with a larger patch will do less to track and correct for local warping. So as the block size increases, we see the residual tilt variance increase, and that's the blue curve here. So to characterize the effectiveness of image registration, we use what we call the tilt correction factor, alpha. It's defined as 1 minus the residual tilt variance over the input tilt variance. So alpha can go from 0 to 1. When alpha is 1, that means we're doing perfect tilt correction, and we've removed all residual tilt variance. We have no residual tilt variance. When alpha is 0, we've done no tilt correction, and we have the original tilt variance remaining. And we can track the tilt correction factor as a function of the block size used during registration. A smaller block is going to track local warping and do a better job with tilt correction. In the limit, if our block size is down to 1 pixel, in principle, we would get a perfect tilt correction factor of 1. In practice, it's impossible to do that because you can't do block matching with a single pixel. In the previous slide, notice that there was an error term, and this particular plot assumes an error of 0 for illustrative purposes. But as we increase the block size, we will get lower error in the block matching, but we will also get less tilt correction because of that averaging effect. But we do see that the larger block sizes, we get less tilt correction, and even a very large block of 1001 pixels by 1001 pixels still creates a significant tilt correction factor of about 0.5 here. Let's now consider optical transfer function models. To do so, we need to define a little bit of terminology. First, a short exposure image is one that's acquired with a short integration time, short enough that there's no motion blur due to atmospheric changes. Such an image will contain spatially varying warp and blur in the antisplenetic case. A long exposure image is one that's simply acquired with a long integration time. This image will be much more heavily blurred because it does include atmospheric motion, but it will tend to have the correct scene geometry because the tilt mean is 0. And finally, the average short exposure image would be one that is an average of short exposure images that have been fully tilt corrected. And the average short exposure image is really the best of both worlds. It has no atmospheric motion blur, but also has the correct scene geometry. This, however, would require perfect image dewarping to achieve. The OTF model we use applies to potentially imperfectly registered short exposure frames that have been averaged. And our model includes 3 components. Our overall model here, H alpha of rho, is made of a diffraction component, short exposure, average short exposure blurring, and then finally a residual motion blur from imperfect registration. These are circularly symmetric functions and rho here represents a radial frequency. The diffraction component is given by the well-known diffraction OTF specified here. The average short exposure OTF is given by Fried's analysis, given here. And then finally, we use the Gaussian model for the residual motion blur that is a function of our tilt correction factor alpha. Our OTF model is set up so when alpha equals 0, that's no tilt correction, the overall OTF matches that of the long exposure OTF from Fried's analysis with diffraction. And when alpha equals 1, our overall OTF matches Fried's average short exposure OTF with diffraction. This slide shows the OTF model as alpha changes from 0 to 1. When alpha is 0, we see that the red curve, which is the overall OTF, matches the green curve, which is the long exposure. And as we increase alpha and improve our registration, the OTF approaches that of the short exposure OTF, which is the curve that's blue. The light blue curve, by the way, is the Gaussian residual motion blur. So you can see how important it is to have the best possible registration and have alpha as close to 1 as possible to get the most favorable optical transfer function. I'm going to change gears just a little bit and talk about turbulence simulation tools that we've used. Now, turbulence simulators typically take a declared truth image and degrade it according to the relevant camera and atmospheric parameters. The simulators can help us understand atmospheric turbulence and its impact on imaging systems for any scenario of interest. Accurate simulation is also critical for developing turbulence mitigation algorithms. Since we have a degraded image and corresponding truth, we can use quantitative image metrics to evaluate turbulence mitigation. We can also use these image pairs for training machine learning algorithms. There are many turbulence simulation methods presented in the literature. I'm just going to briefly touch on 2 methods that are used for the results presented here. In particular, we use a numerical wave propagation method and a fast warping simulation method, as cited here. The numerical wave propagation method is based on propagating numerical point sources through a series of phase screens to the camera's pupil plane and ultimately forming a point spread function for that particular point source. In the anisoplanatic scenario, we have to do this for every point in the object plane because potentially every point in the object plane will give rise to a different point spread function. So the video here shows an example of how, as we change the point source location in the object plane, we get a different point spread function. For each point in the object plane, we perform a propagation algorithm that's known as a split step propagation. And again, we numerically propagate a numerical point source through phase screens that emulate the degradation of the wavefront from turbulence. The details are presented in the cited paper here. But the bottom line is that we end up with a point spread function for every point in the image, and we apply these point spread functions in a spatially varying convolution operation to provide the image degradation. The other type of simulator we use is a fast warping simulator based on the work of Schwartzman et al. We basically use white noise fields and we filter those to provide tilt fields that have the correct correlation statistics from our earlier analysis. What we do is a little bit different than what's reported in Schwartzman paper in that we use statistics from Dr. Santashri Bose-Pillay. We also apply an isoplanatic blurring using the average short exposure point spread function. So this gives us an isoplanatic blur with an anisoplanatic warp. So it's not an ideal simulator, it's an approximate simulator, but it can be very fast, and under certain circumstances, we think it can be very useful. This slide shows the output of the 2 simulators. The numerical wave propagation output is shown on the left, and the fast warping simulator with its isoplanatic blurring is shown on the right. And I believe you can tell that the warping is quite similar between the 2 as we might expect. On the other hand, the blurring is a little different. On the left, we can see the anisoplanatic blurring. We see patches that are a little sharper than others come in and out of focus, whereas in the fast warping simulator, we have uniform blurring. However, the fast warping simulator is about 300 times faster. The other thing to keep in mind is that if we average these frames temporally, they will both end up looking about the same. And that's because when we average the output of the anisoplanatic simulation, those point spread functions will average to something that looks like the average short exposure point spread function. Thus, after a temporal fusion, both simulators produce a very similar result, and the fast warping simulator is much faster. I'll now address the final topic in this presentation, turbulence mitigation. I've been a big proponent of a relatively simple and intuitive method that we refer to as the block matching and Wiener filtering turbulence mitigation algorithm. The block diagram here shows the main steps. It begins with the acquisition of short exposure images. The first thing we do is we form an initial prototype image by averaging those frames. We typically do use a global registration prior to averaging to account for platform, camera motion, and a little bit of that global turbulence shift. This prototype image then is used to feed as be a reference for a block matching algorithm where the short exposure frames are matched to the prototype. We choose a block size here to try to balance the error with the block matching with the desire to get the largest tilt correction factor possible. Once those frames are then registered, they're averaged to produce the image shown here as f of xy. That image should be as close to the average short exposure image as we can get. That's the goal. We then apply a Wiener filter to perform image restoration to provide the final result. And the Wiener filter uses our parametric OTF model that we discussed earlier that takes into account diffraction and uses information like the aperture, focal length, and wavelength, and also uses information about the turbulence, the Fried parameter, and our tilt correction factor. The most recent paper cited here at the bottom, number 2 here, focuses on how we can estimate the Fried parameter and how we can calculate that tilt correction factor to give us all the parameters that we need to populate our parametric model. This video shows how the block matching algorithm provides de-warping that's helpful in reducing motion blur when these frames are temporally averaged. On the left, we have the raw frames. These are independent atmospheric realizations. That's why they're jumping around so much. And on the right is the result of the block matching algorithm. So when these frames are averaged, the image on the left is going to have the long exposure blur, and the image on the right is going to be much closer to the average short exposure blur. But you see the registration is not perfect, and that's again why we have that alpha parameter. This slide shows all the relevant images for the block matching and Wiener filtering method. The upper left here, we have a single raw short exposure frame. Here we have the long exposure image. Down at the bottom left, we have the result of block matching plus averaging. And then finally in the lower right, we have the final output with the Wiener filter applied. Now notice here that the block matching image is much less blurred than the long exposure image, thanks to the block matching alignment. And that gives the Wiener filter a much better starting point. The Wiener filter result here should be compared to the truth image on the right. You can see that visually it looks like it's doing a pretty good job. This is using 200 frames, and the peak signal to noise ratio is shown here. With one frame, we can't do a very good job, as you might imagine. We can't get the geometry right, and it's just not enough frames to get the blur looking isoplanatic. After about 30 frames, we're doing a much better job with the peak signal noise ratio. And this is in part because we're getting the geometry right with the averaging of extra frames. And the anisoplanatic blur is averaging out to look more isoplanatic, allowing the Wiener filter to do a better job. And from that point on, we just see a little bit of an incremental improvement with better geometry and more and a blur that's more in line with our parametric model. While simulated images are great for quantitative analysis, it's important to see how the algorithm performs on real data. Here we have some real visible imagery acquired with the camera parameters shown in the table. This is an approximately 1.8 kilometer distance and a telescope focal length of 3.7 meters. A single raw frame is shown here on the left. A long exposure image is shown here on the right, achieved by frame averaging, and the final block matching Wiener filter result is shown on the right. The Fried parameter here was estimated using the algorithm in the paper cited. And you can see that the Wiener filter result is much sharper than the individual frames or the frame average. And you can start to make out some details. The scene here is a checkerboard pattern. There's a junction box here behind that board, and then there is a trailer in the background. The letters here are actually MZA. You can, if you look carefully, you can just make those out in the Wiener filter result. Recently, my student Matthew Hoffmeyer explored a variation of the block matching and Wiener filtering method. And here we replaced the Wiener filter with a regression convolutional neural network. We call this the block matching, the BMCNN algorithm. We trained the network using the fast warping simulator for convenience and speed. However, we tested the algorithm using the numerical wave propagation simulator. Because the input to the regression network is in fact an average of frames, a temporal average coming out of the fusion block, we really don't see a problem using the fast simulator with its isoplanatic blur compared with the full numerical wave simulator. Here's a summary of the results. We observed only a small boost in performance in low noise using the convolutional neural network. However, in high noise, it was a very interesting result. So the truth image is shown here on the left. A single short exposure frame is shown on the right. And here you can see it's very noisy. This particular scenario has a noise standard deviation of 30 with respect to an 8-bit dynamic range. The block matching and Wiener filtering result is shown in the lower left, and the new result with the convolutional neural network is shown on the right. Notice how the CNN produces a spatially varying adaptive restoration. The flat areas of the side of the train look nice and smooth without sacrificing a lot of the detail on the edges. The PSNR analysis also shows there's a nice boost in performance using the block matching CNN method. The red curve here is the convolutional neural network, and that's compared with the Wiener filter in blue. There's just one more algorithm I'd like to talk about before concluding. We refer to this algorithm as the fusion of interpolated frames super resolution, or FIF-SR. And here we seek to perform image super resolution and turbulence mitigation jointly. The main difference here is that we perform sub-pixel image registration to create a sequence of aligned and upsampled images coming out of the registration step. Also, when we take those frames, we don't just average them, we do a weighted sum fusion where the weights are based on how far an interpolated pixel is from a native observed pixel. And this grid is representing that process. So imagine that the high resolution grid are the red squares, and the blue circles here represent the observed pixels. So we have to interpolate the values of the red squares based on the blue circles. Now in this particular case here, this red square is very close to a blue circle, meaning we have a real data point, a real pixel value measured very close to that spatial location. So we would want to give that interpolated value a high weight in the fusion process. On the other hand, this particular red square is far from any of the original measurements from the original low resolution data. And therefore, we probably want to give that a low weight. And because we're going to have different motion in each frame, the hope is that every red pixel somewhere in some frame will be close to a blue circle, and will it be able to form a high resolution image with relatively low interpolation error. So that produces a fused image at this point in the block diagram. And as before, we apply a Wiener filter. The model, the OTF model now is a little bit more complicated because we take into account the detector shape, which is now larger than a pixel in our interpolated image. We take into account the interpolation kernel that's used, And we take into account how we did that distance-based weighting. So all of that factors into our model-based OTF. We also use, you know, the Freed parameter and the tilt correction parameter as before, and we add these new factors. And that gives us our overall model here, H of alpha beta. And then we perform the Wiener restoration as before. So you might be wondering if super resolution and turbulence mitigation are really ever needed simultaneously. Because turbulence, as we know, acts as a low pass filter, much like an anti-aliasing filter. Well, we studied a variety of scenarios and determined that in light to moderate turbulence with a relatively short focal length lens, the answer is definitely yes. And this slide shows some modeled OTFs for a short focal length camera on the left and a longer focal length camera on the right. The vertical dashed line shows the folding frequency above which any energy would get aliased. And we see that here on the left with the short focal length, for all these different R0 values, there is a significant amount of potential energy above the folding frequency, even in the relatively high turbulence scenario. When we have a longer focal length, here we have a 1 meter focal length, we see a little bit less energy above the folding frequency. And when we have high turbulence, like the black curve or the cyan curve or even the magenta curve, we have very little energy above the folding frequency. But in the lighter turbulence here in the green and yellow, with a relatively large Freed parameter, we still do see a significant amount of energy over the folding frequency, even with that longer focal length. So it's interesting to note that there's definitely a potential benefit from doing joint super resolution, which can combat the undersampling problem, and turbulence mitigation. So here, let's take a look at some simulation results for the FIF-SR method. We use the numerical simulator to create Nyquist sampled images, and then we simulate detector integration and downsample those images by a factor of 3 to create an environment where we have both undersampling and turbulence. And we consider 2 acquisition scenarios. One where the camera's on a fixed platform, and we call this jitter off. The other scenario is where we have random translational platform motion, and we call that jitter on. The best results are obtained using a little bit of jitter to provide sampling diversity for the super resolution algorithm. The results for jitter on are these solid lines here on top. This is peak signal to noise ratio as a function of our turbulence strength. And again, the best results are here with jitter on. And down here is a reference. This is the just simple single biframe, bicubic interpolation on a single frame. And obviously our FIF-SR algorithm is much better than that in all of these scenarios. But what's really interesting to me is that the jitter off scenario shows something very interesting. These dashed lines are the jitter off scenario. And here we actually get an improvement in performance as we increase turbulence a little bit. And what's happening is that the turbulence is providing a little bit of tilt. And that tilt is providing sampling diversity, which allows the super resolution algorithm to do its job and produce a reduction in aliasing. Of course, once the turbulence gets strong enough, the effect of that starts to, again, produce a reduced result. But it is really interesting to see that that turbulence is actually helping. And this idea was postulated by Yaroslavsky and Fishbane in a paper that's interestingly titled Super Resolution and Turbulent Videos Making Profit from Damage. And in fact, this is exactly what we're talking about. There's the profit from damage right there. The images tell the same story. Here we have a single frame with no turbulence and no jitter. Now the FIF-SR algorithm can't do much with that. The result here is a little bit sharper, but the aliasing that we see here on the roof is not improved. The aliasing in the picket fence is not improved because, again, there's no shift, there's no sampling diversity. Now on the bottom left here, we have an image that has some turbulence in addition, but has no jitter. But there is a little bit of shift due to turbulence. The turbulence is relatively light, so you don't see much extra blurring. What's a little bit hard to tell is that there's a little bit of tilt in the images. Now the FIF-SR algorithm is able to take advantage of the tilts from turbulence. And now we see a much reduced aliasing artifacts on the roof of the house here and a much better representation of the picket fence. And this is all due to motion from turbulence, which I think is particularly interesting. I'm going to conclude the presentation by showing just two more real image data sets. The first is this truck sequence. And here the camera is nearly Nyquist sampled. However, for these results, we still do an upsampling by a factor of 2, and we utilize subpixel registration. So the input sequence is shown on the top. A single, and that's been interpolated by a factor of 2, by the way. A single frame, also interpolated by 2 using bicubic interpolation, is shown in the middle. And then finally, the FIF-SR result is shown on the bottom. Notice there's a significant improvement in the bar target. These are 3 bar targets, horizontal and vertical, and you can make out all the horizontal bars and most of the vertical bars in the FIF-SR processing. And that's very difficult to do in either the video or a single frame. Here we used a relatively large block size in order to try to get as much registration accuracy as possible, since we were trying to get subpixel registration. So we didn't have a very high tilt reduction factor, but we needed that larger blocks to get a good accuracy. And the result shown here is using 500 frames with an upsampling factor of 2. And that brings us to the last set of results here. This particular data set is from a camera that has a much more significant amount of undersampling. The Q parameter is 0.4. A Q of 2 would be Nyquist sampled. Anything below that would be undersampled. So here we do have some aliasing artifacts, and we also do have a significant amount of turbulence as well. So it's a really neat example of a scenario where we definitely see both turbulence and aliasing. The image on the left here is an interpolated frame. Here, upsampling factor of 3 is being used. So this is interpolated using bicubic interpolation. And the image on the right is the FIF-SR output. And you can see, for example, these power lines are heavily aliased. And here we see they're straightened out very nicely, and the aliasing artifacts appear to be reduced. Some turbulent warping is detectable a little bit if you follow this rail line here, this handrail. This is a roller coaster, by the way. That really should be quite a smooth curve. You can see that we do achieve that over here on the right. So we're getting both aliasing reduction and we're getting some dewarping, and clearly we're getting a lot of sharpening using the FIF-SR algorithm. And the images on the bottom are basically just a slightly different field of view that really shows these overhead power lines and how much improvement we see in terms of aliasing reduction for those power lines. So this is an interesting result that shows that there are scenarios where both turbulence and aliasing can happen simultaneously, and a joint restoration algorithm can work and be beneficial. Well, that concludes my presentation. Thank you very much, everyone, for listening. Thanks again to Stanley Chan and the conference organizers for inviting me. Thanks to all my collaborators and co-authors on the various papers cited in this presentation. It's been a great pleasure working with all of them. Take care, everyone. Goodbye.
All right, so let's see if Russell, are you here?
Okay. Yes, hi, I'm here. Can you hear me okay?
Yes, I can hear you very well. Thank you for joining us remotely. Yeah, so thank you for the talk. This is extremely informative. I think I learned quite a bit here. So we have a couple minutes for questions. Wonder if people in the room have any questions for Professor Hardy. Yeah, can you speak up?
last couple mentioned that it's beneficial from the super resolution task to the turbulence concept model, and we should do the joint validation for separate.
I'm sorry, I am having difficulty hearing that. Could someone repeat that?
Yeah, can you hear me now?
Yes.
My naive question is that since solving the super resolution task will benefit the turbulence task, shall we solve this task together, or is it same that if we sequentially solve one and another?
Okay, so your question is, should one tackle the two problems jointly or one after the other?
Yeah, exactly. Thanks.
Right. Well, I think that in general, I'm sure this is you would agree with this that whenever possible, joint restoration is preferable, but sometimes it's more practical and simpler to solve the problems separately. What's interesting about the two problems, solving them jointly, actually it's not such a difficult thing to do, because for turbulence mitigation, we really want to average as many frames as possible. But we want to average them after alignment. And with super resolution, we also need to do alignment, and the averaging is actually quite helpful, because even if your registration is imperfect, averaging many frames can save you from from error. So it's much more robust. So yeah, doing the two jointly, I think, works quite well here, since they do both methods require registration, and both methods benefit from a great deal of averaging.
Can I ask a follow-up question, Russell? For turbulence, if I do not have blur, meaning that the isoplaneticism is not as strong, then I can see the super resolution will seem to work. Just think about all these Google Pixel phones. They are doing a burst photography. They align the pixels, then you can do subpixel. When you have anisoplanetic turbulence, those blurs are everywhere. And typically we are doing lucky imaging. We pick up the sharp frames. Out of 100 frames, I only have one frame that is really sharp. So in your experience, would this lucky imaging be better, or shall we go with a pure super resolution, that kind of approach, or are they complementary by any chance?
Well, that is a really interesting question. There's some work that we're doing now a little bit on lucky imaging. And so you're asking a really great question. I'm not sure if I have a thorough answer, but lucky imaging is not always as helpful as you might think. and that is because with lucky imaging, you're using fewer frames. So that means you're potentially throwing out information that could otherwise be used to improve your signal-to-noise ratio. And an improved signal-to-noise ratio allows you to be more aggressive with your restoration. So what I have found is that in a lot of circumstances, you're better off just using the extra frames and not necessarily going for lucky frames. However, with that said, there are certain scenarios that I've observed where there is still a benefit to doing lucky processing. But lucky processing and super resolution are definitely different things. You can still be lucky, and you can still be lucky and aliased, and you can still be lucky and not aliased. So I do think they're kind of separate, separate issues. And generally speaking, the more frames that you can fuse, the better the signal-to-noise ratio you can get, the more aggressive you can be with your restoration, and that tends to help super resolution as well.
I see. That's a very good comment. Good question. Okay, can you come over?
Hello, Dr. Roddy. Thanks for the talk.
Thank you.
A question regarding the super resolutions. So from your slides, I think there's only a certain region that the super resolution is benefiting from the turbulence. Is that right? So
Oh,
is
yeah,
this
so
regime?
in the simulated data, right? So in the simulated, the real data, there was the camera was moving. So in the real example, in the final sequence of the roller coaster, the camera was panning and there was jitter. In the simulated data, there was no camera motion. So the only way to really get sampling diversity is to introduce motion. And if the camera's not moving, we're relying on the turbulence to produce motion.
Okay, yeah. So is this kind of this regime like depend on the algorithms, or is like a theoretical bounds there? So basically, if I have a better algorithms, do you expect that the turbulence can help the super resolution in a much larger like a turbulence strength?
I'll bet that one could calculate sort of the point at which the motion from turbulence is not helpful enough to overcome the blurring from turbulence. We didn't really pursue that sort of boundary in the study that we did, but that's what's happening is that as the turbulence increases, you're getting more blurring that has to be overcome for the super resolution to look good. So the sweet spot is when you have a pretty good tilt variance without too much of the short exposure blurring. So the tilt is helping you, but the blurring is hurting you. And you saw in the plot that when the turbulence CN squared gets large enough, you're back down to where you were before you turned on the turbulence, and then it goes down from there. So yeah, we didn't calculate like a theoretical boundary there, but I'll bet it could be done. So I don't think it's algorithm dependent.
Right.
Thank you, Dr. Hardy.
Oh, sure.
More questions? Any more questions from the audience?
Yeah, I have one. This is Keigo, Keigo Hirakawa. I work with Russ. But yeah, very nice presentation. I really appreciate that. And just follow-up question on the follow-up question that Stanley asked. So with the super resolution, it's very fascinating that it's truly that these problems seem very connected. So is there anything to be learned from the super resolution exercise that you've done for non-super resolution case? In other words, for example, is there something that we can exploit in your super resolution study for cases that you don't really care about upsampling, but maybe that there's some stuff that you can exploit to improve their result?
Oh yeah, that's a great question. If you notice with the truck data, the camera, when you calculate the undersampling factor there, it's basically Nyquist sampled. But we actually did get a slight boost in performance because we are doing subpixel interpolation and subpixel registration. And so the better as the theme, the main message of the presentation was that better registration leads to a better final result. So subpixel registration can help you even if there's no aliasing by just virtue of getting a little bit more accurate registration. So that's one aspect where the super resolution processing was helpful, even though we didn't have aliasing.
Okay, thank you. Yeah, that makes sense.
Okay, great. Thank you, Russell, for joining us remotely. Thank you so much. Hope we will be able to bring you to on site in person next year. So I really look forward to that.
Okay, great. Thanks. I hope you guys are enjoying the local seafood down there.
Sure. Thank you. So I'll just give time back to Wu Yang for the next item.
And thank you, Russ, for this great talk. Okay, our next speaker is Dr. Xiaohua Zhai from Google Brain. And Xiaohua, are you able to hear us?
Yes, it's good.
Okay, that's good. Yeah, I can see you. Thanks for joining us. And do you want to share your screen? Great, I can see your screen. Yeah, okay. I will give a short introduction and I think we can get started. Hi everyone, I'm very happy to have Dr. Xiaohua Zhai as our next speaker. Dr. Jai is currently a staff researcher at Google Brain, Zurich. Before that, he received his PhD in computer science from Peking University in 2014. And he is also one of the inventor of the vision transformer last year. And he's recently working on deep learning and computer vision, and particularly interested in representation learning, transfer learning, and self-supervised learning, and generative models and cross-model perceptions. Thank you very much, Dr. Jai.
Yeah, thanks for the introduction and especially invitation to the UG2 workshop. I'm really excited to talking about our recent research. So the title of my talk is large-scale general visual representation learning. So to start with, let me first introduce our goal of what do we want to achieve. So we plan to use any upstream data and then use the upstream data to train a pre-trained model. With upstream data and pre-trained model, we plan to use an adaptation algorithm to deploy this model to very diverse downstream data sets. And the diverse downstream data sets can be sampled from the real world, like it can consist of real natural images classification, like a dog, cat, or this can consist of very specialized images, like the remote sensing images, as well as medical images. And finally, we also want this model to act well in the reinforcement learning environments. Like we can make use of the representation and use it to solve some reward prediction problems, like having these targets either positive or negative in a reinforcement learning environment. Then we can use this representation to predict whether this is positive or negative, and what's the distance to the next reward. So that's our target, having this general representation learning using this single representation and adapt to everything. So this plot shows the comparison of a typical human behavior with respect of how much images do they need to achieve a reasonable performance. For example, as a typical human, we just need a few images for each class to recognize them. But with a machine learning model, especially if we're training from scratch, this is the blue curve, we may need up to 1 million images to achieve good performance. And our goal is to achieving this red curve with pre-training and with knowledge transfer. We can cut the cost of the training set size, especially for the downstream task. We can just pre-training on extremely large data set, and we can transfer this model to diverse tasks just with, for example, a few examples per class for the downstream adaptation. Okay, so this is the agenda or the outline of my talk today. So how do we get there, keeping this goal in mind? So there are 4 methods. I will quickly remind of the 2 efforts we have done. First is large-scale pre-training with convolutional neural networks, as well as using less inductive bias by getting rid of the local parameter of this local sliding convolutional window with a vision transformer, which is using the global attention to the full images on every layer. And I will spend the majority of my time introducing 2 very recent efforts, scaling vision transformers, as well as locked image text tuning. Okay, let's get started with the first point, large-scale supervised pre-training. So in this effort, we tried to scaling up the standard ResNet architecture to large data sets. On the right top corner, you see this plot when training on 1.3 million images, which is standard ImageNet. And by scaling up some models from the very small point with a standard ResNet 50 to the biggest model, which is ResNet 152 layers, which is deeper, both deeper and also wider, which is 4x wider. And we use different size of bubbles in this plot to donate different model size. And you can see when we're scaling up the model size on ImageNet, we observe consistent improvements on ImageNet. And then when we go in with more images, like on the middle column, it's using 14 million images on the ImageNet 21K data set, which is a full set of ImageNet data set. And this one, we observe consistent improvements. But when we continue scaling up the data set as well as the models, you can see this red curve is actually dropping by scaling up from 14 million images to 300 million images. We observe worse quality. So if we cut there by using a small model, sorry, then we may conclude with wrong messages like yeah, you should not scaling up your data as more data hurts your performance. But when we keep scaling up some models, like from RESA 50 to RESA 1 by 1, we observe a big jump on the rightmost. And then when we go into the pink point and to the biggest model, 152 by 4, we actually observe very big boost on the big data sets. So that means if you have sufficient amount of training examples, then you normally need a super large model to fit those data. Otherwise, it may hurt the performance. And one thing very interesting we observed in this effort is that with 152 by 4 model, which has close to 1 billion parameters, it's actually performing pretty good on downstream tasks when it has only, for example, as low as one examples per class. For example, on CIFAR 100, this one shot means there are only 100 examples in total, and going to 5 shot is 500 examples in total. The model is getting up pretty fast. That means we have much fewer examples for the adaptation task comparing to the original model parameters, like 1 billion parameters. And that's quite interesting. The model does not all fit into the downstream data sets. So we checked the training curve, especially for this 5-shot, 10-shot adaptation. The loss or the adaptation loss goes down pretty fast. That means the gradients also gets much smaller if the loss goes to 0. That means the model does not get long enough to overfit into those small downstream examples. And the story could be different if you're training from scratch, because the parameters are initialized randomly. And if you just use those few examples per class, then you cannot train this model well, because it will just overfitting significantly. But here, with pre-training and then adaptation, the loss goes down quickly to the goal, the target you want to achieve. So going along this direction, we were thinking of, can we use less inductive bias? For example, with convolutional neural networks, it's still using the sliding 3x3 windows or 7x7 windows on the input image. It's based on the assumption that of the locality of human vision system, that all of the pixels, the surrounding pixels, are more or less relevant with each other. So with those sliding window and then strides on different layers, it can actually cut the cost or cut the computational cost. So we were thinking, can we getting rid of this inductive bias and instead using the global attention on every layer, like on the lower layers, the model should still have large perceptive field instead of a small local window. And the model actually have this global attention from the first layer till the last layer. And we want to ask the model to learn this inductive bias by itself. So yeah, that's one context. And on the other side, so convolutional network has been widely used in the literature for the past many years. And we just tried using transformer encoder to modeling a vision task. So it's going as simple as just cutting the image inputs into non-overlapping patches. And then we use a simple linear projection layer to map those non-overlapping patches into token embeddings. For each patch is corresponding to a token in the language domain. And then we append the positional embedding on top. And that's it. We feed this into the vanilla unchanged, unmodified transformer encoder, and then try to do classification problem with this architecture. So still on the same plot on the right and the top corner, you can see the bubble points from the bit, which I just discussed, as this square and this gray area. And the models with vision transformer marked as bubbles here. So let's just look at the leftmost column again on ImageNet. You can see that the VIT models is performing actually below big transfer, the ResNet models. And that's likely because of not sufficient training data. The model gets a bit underfitting. And the same question, if we cut here, then we may come up with conclusion that VIT is not comparable to convolutional networks. And then going from left to right with using more data from 1.3 million images to 14 million images, you can see the VIT models is catching up. And going to the rightmost with 300 million images, the VIT model, especially the biggest one, is performing better than the ResNet architecture. So that's quite interesting that with less inductive bias, you actually need more data to fit those positional embeddings. For example, for this positional embedding, it just attends to everything. And the model is able to figure out, yes, the surrounding patches are the most important, but the patches far away from current one is less important. Yeah, so along this direction, let's continue scaling up vision transformers. And I will present the key results of our scaling laws study. So what we did is a systematic study of understanding scaling laws with scaling up data and scaling up models. So from data perspective, we use a data set called JFD 3 billion, consists of 3 billion images. And we try to split these datasets into multiple subsets, including 30 million images, 300 million images, 1 billion images, and 3 billion images to understand the impact of the dataset. And the second point is we create a lot of different width variants with different number of parameters, and it's denoted as a letter slash with patch size. So this small s, for example, small s representing a model with 5 million parameters, and the big G, the capital G, representing a model with close to 2 billion parameters. And the number after slash means the patch size. So that means given an input image, for example, with 224 by 224 resolution, if we want to cut patches into 28 by 28 by 28, then you would get 224 divided by 28 times 224 divided by 28 patches. So the larger patch size, the less number of tokens, and the faster model training. Of course, it's getting fewer G-flops. Okay, so after having all of the model variants and all of the dataset sizes, we try to make a cross product of the model size times the dataset size and times the training schedule. So you can see from this plot, there are multiple small curves. So each curve representing a combination of a dataset size and the model size. And those different dots on a single curve means how long we train this model. So we are using a reverse square root schedule, which you can keep training forever. And then we can do cool down at different locations, cool down the learning rate to 0. And that means we just do a single training job, training, let's say, for infinite steps or for million steps. And then we do cool down at 10K steps, cool down at 50K steps, cool down at 500K steps, so that we can get multiple points using different computational cost with the same model on the same data set. So from this plot, we can actually draw this curve on the to fit all of the points falling into the frontier of the best compute and downstream performance trade-off. And we can use a scaling laws equation to fit this curve. And here you can see that according to this curve, we estimate the ImageNet downstream fine-tuning accuracy is actually would converge around 91% accuracy or 9% error rate, which is also almost matching the current state-of-the-art number on ImageNet. And our observations is that so one needs to scaling up compute model and data together to improve the representation quality. So for example, on the rightmost point, it's the biggest model training on biggest data set and for the longest duration. And then you can see those orange dots. So they are also using very large models like this L16, if we compare the color. And then if we train L16 for super long, the dot size represents the dataset size. And this one is actually using 30 million training examples. That means if we train a big model on a small dataset for extremely long, the model can actually overfitting and force off this frontier. You can see the dots at the beginning, it's actually force on this frontier. And if we keep investing more compute, it falls off. And the second observation is that the representation quality can be bottlenecked by the model size. And in this small plot, we show all of the experiments with different model size. And you can see that by increasing the model size, actually we get significant boost. And even though with the biggest small G model and the big G model, we also observe boost the error drop. And third point is that large models actually can benefit from additional data. And in this plot, you see on the left most, it's using 30 million data set size, and going to the rightmost, it's using 3 billion data set size, and on the column left, it's using 1 billion data set size. So you can see that large models can benefit from using more data. Even the data set is already 1 billion. By scaling from 1 billion to 3 billion, you can also see additional boost. And the fourth point is a bit interesting. It's also a bit aligned with the point I just described with this downstream adaptation data efficiency. So you can see here, by pre-training on the data set for how many images seen, so you can calculate this image seen by the number of steps times the batch size. So that's how we calculate the image seen. So the more image seen, the longer this model has been trained. So we compare 3 models, the smallest, the tiny model, and the base model and large model. You can see that to achieve the same error rate, large models needs much, much fewer images seen to achieve the same level of error rate. So that means if you don't have enough data, so using big models is likely also a good option. So the last point is we tried the same scaling laws on the smaller ImageNet 21K dataset, consists of 14 million images. And we can see that the same scaling laws hold and with almost identical conclusions. And this model is doing good on ImageNet classification. And when we releasing the paper, it was on top of the leaderboard. And now the best method is getting close to 91% accuracy. And in this plot, we also show this few shot linear regression results. X-axis shows examples per class on ImageNet, and the Y-axis shows the top one accuracy. You can see that with the proposed VIT-G model, we can get one shot gets close to 70%, and the 10 shot gets close to 85% top one accuracy. So this is even fewer images than 1% of the full ImageNet training set. And those are more adaptation results. We got 90.45 back then, and now the best is close to 91. And we tried the same model on different ImageNet out of distribution variants, and also observed either close to SOTA or SOTA results. And finally, on the VTAC Lite benchmark, consisting of 19 different tasks, the model also achieving the best performance. So next, I will introduce a recipe of how we train the large-scale VIT models. So the first one is about the memory efficient optimizer. So this is most important because we did not use model parallelization. We fit the model into a single TPU chip. So that means we have to fit the model in memory. If we use the original VIT paper used Adam optimizer. So if we use Adam and for a model with m parameters, Adam actually needs 3x m memory for the first momentum and second momentum. So we try to store the first momentum in half precision, and then we can save the memory cost, but it still use 2.5x m memory cost. And we try to also do the same to second momentum, but it gets much worse performance. So we try to explore different ways memory efficient optimizer. So we tried Ada factor, which needs the M memory plus a constant cost. But this doesn't work out of the box in our experiments. So we reintroducing the first momentum in half precision and with a few other small tricks. Altogether, this costs about 1.5x memory and almost matching Adam perfectly. So this plot shows the 3 different setups. You see the 3 colors. The orange means original bit using Adam optimizer. And the green one is the 2.5x m cost with half precision first momentum. And the blue one is the one with Ada factor with the half precision first momentum. And you can see that with orange color, the model gets out of memory pretty soon. So we use the dots, the color dots on this plot to show the models we can fit in memory. And the white color means the model cannot fit in memory. So you can see that going from the original to half precision Adam, we can scaling up the model quite a lot. So for example, we can go to this bit small g, while in the original VIT paper, we can only come up to VIT big H. And with this Ada factor, we can even scaling up the model to VIT big G with close to 2 billion parameters. And this slide shows a second improvement we introduced to train the model. So we tried different weight decay for the big weight backbone. So for the backbone, we have to set the weight decay for the body, and we also need to set the weight decay for the head. So normally we use a single weight decay value for the full network, but here we tried using different weight decay for the body and for the head, and it's quite interesting that with a different combination, for example, with super high, extremely high head weight decay, like 10.0 on this plot, and with reasonable body weight decay, the model actually performing pretty good downstream. And that, but however, if we look at upstream performance, the story changes. So the best performance achieved on the left bottom point of this plot. That means we have to use a uniform or use a single weight decay for both body and head. But if we look at the downstream ImageNet transfer performance, a higher head weight decay gets better models. So our explanation is that with higher head weight decay, we try to push back the capacity to the model, to the body, and we can get a great body that can be transferred afterwards. But if we set the same weight decay, like smaller weight decay for the head, the model is powerful to solve current tasks, but actually the body is not as powerful as the one with higher weight decay. And this is a schedule we used in our paper in order to get so many checkpoints with different training costs. We did not train the same model many times, but instead we just use a single reverse square root weight decay. You can see this green curve. It's starting from the beginning point and then goes infinity. And we can insert any cooldown at any position of this curve. And this model is performing more or less the same as cosine or as linear. So this is good if you don't know how long do you want to train your model or how much compute do you have. So we rather keep this model running forever. And as long as we are short on resource, we can just do this cooldown. But with linear or with cosine learning rate schedule, that means you know your schedule at the beginning. But after this training, you cannot easily continue this job unless you're starting from scratch because your learning rate has already been cooled down to 0. And in this plot, you can see that with the pink curves, it's like we have the oracle. We know how long we can train, so we can use linear learning rate or we can use cosine. And with this green curve, it's like infinite training, but with different cooldowns. You can see it's below the curves, which you know how long you want to train, but not much. So that's the reason we finally choose this to save the resource. Yeah, that's it. To getting the scaling laws as well as training the big models. And in the next part of my presentation, I will introduce how we are making use of this model to solve as diverse downstream tasks as possible. So it's called the LIT, zero-shot transfer with locked image text tuning. So locked image means we will not modify the image backbone. Like the biggest VTG, we will not change it. And we just train another text model to use this model to do zero-shot transfer to any downstream tasks. So a bit background. So this animation shows how one use a pre-trained image model for different downstream tasks. Like here, if it comes to task 1, even with 5 images per class, we have to fine-tune a full backbone on this task in order to perform recognition on those customized classes from task 1. And if we have 3 or 5 different tasks, we have to adopt this fine-tuning 5 times, and each one with a considerable amount of engineering cost. And the second background is contrastive learning. So this method is a bit different from pre-training than fine-tuning. It takes image and text pairs as input. Let's say this dog and airplane and coffee images, as well as pairwise the text, like I love my morning coffee. And then with all of those pairwise data, like in this example, there are 3 pairs. They input images into an image encoder and input the text into a text encoder. And they apply contrastive learning on those pairwise data. So this means on this diagonal of this matrix, similarity matrix, those are positive examples. And on all of the remaining entries in this matrix, they are negative examples. So if we think about this in the pre-training within a mini batch, that means the pair in this mini batch is considered as positive, but all of the remaining examples in this mini batch is considered as negative. And the loss is calculated from both directions, like from rows of this matrix. You can see it's from as image input to all of the 3 text candidates. So we calculate the contrastive loss from this direction. And also we calculate losses from the columns. So that means with a text input, we calculate all of the distances to the image embeddings and then calculate yet another contrastive loss. So finally, this contrastive learning is a mixture of 2 losses, image to text loss and text to image loss. Both are contrastive. And so what we propose is the best of both worlds. It's called locked image tuning. So we take the pre-trained image encoder. It can be with G here. We never adapt it afterwards. And given the same 3 pairs of image and text, so the image goes through the image encoder, and we should be able to get good representation just because the big bit G is pre-trained on GFT and it's getting good quality downstream. And what we do here is we train from scratch text encoder. The text encoder takes text as input, and it calculates the contrastive loss between the frozen image embeddings and the embeddings from this text encoder. And then we use gradients to update this text encoder. After lead tuning, the model can be applied to many different downstream tasks because it's contrastive. So it can just get embedding of a given image and get the embedding of a given text. For example, it can do zero-shot retrieval by comparing them in the embedding space. Or it can also do the zero-shot classification by comparing an inference image with the candidate classes, for example, 5 classes. And we get the embeddings from the text encoder for the 5 classes. And we rank all of the 5 classes. The top one becomes classification results. So to discuss a bit more, we introduce the symbols of how we denote lit models. So we use 2 letters to denote lit model. The first letter means how we set image model. And the second letter means how we set text model. So small u means we initialize from scratch, and then it's uninitialized, and we train both towers. And the big U means we initialize the model from a pre-trained model, and then we fine-tune this. So this is unlocked, and we fine-tune this tower. But this has been initialized, for example, from WithG, and this small U here means it's purely from scratch. And clip and align falls into the small U case. On the leftmost, we initialize image model from pre-trained model, but in the meantime, we lock and freeze the image tower. And all we did is train this text tower unlocked. So we denote this as LU. So in this plot, we show comparison of the from scratch methods, which is clip and align on the 2 datasets. On the left-hand side is on the public YFCC 100 million dataset. And the clip achieves slightly above 30% on ImageNet zero-shot classification with fine-tuned. So this fine-tuned means big U and small u. Big U means we initialize from a pre-trained model, but we fine-tune it. And lit means we initialize from pre-trained model, but we don't fine-tune it, we lock it. And you can see with fine-tuned and with lit-tuned, we get much better performance, especially with much fewer image text pairs seen. The model already outperforms from scratch clip. And on the right-hand side, we compare this on private data sets. And you can see that lit model almost half the gap between from scratch methods and the supervised methods. So this table compares lit with clip and align or more benchmarks. So this one shows ImageNet. So the most promising thing is on the public setup. The best methods out there is only 31 or at most 35 on the OpenClip GitHub repo. And with lit tuning, we can get close to 76% performance, close to the ResNet 50 supervised model. And with a private data set, we get almost close to 85%. And on many ImageNet auto distribution variants, the lit model also gets pretty good results, either SOTA or close to SOTA. And finally, on the VTAP natural splits, the model gets comparable to a supervised counterpart. So we look a bit deeper into this and try to understand why does this work. So we did ablation test of different setups. So on the right-hand side, it's on a very large scale data set of comparing LU, UU, and the small UU. You can see that with small UU from scratch, it's performing much worse than this big U, small U. And this locked image tower and unlocked text tower is the best across all the benchmarks. And on the left-hand side, it's a comparison on the YFCC 100 million data set. We have done many different setups, like from UU, which is more or less the same setup as clip. And we also get matching clip results or slightly better results. And by initialize the image tower with a pre-trained model like this big U, or we lock the image tower, we can see this big jump. And we also try to initialize the text tower with pre-trained BERT model for the text encoder, like it goes from small U to big U, but the difference is not huge in our experiments. And we also tried one very interesting experiment of this big L and a big L. So that means both towers are locked and pre-trained. Like we have a pre-trained VIT model and we have a pre-trained BERT model. Or we have the embeddings from both models trained from different worlds. And the thing we have tried using a linear mapping between the two models or using a MLP mapping between the two models. Yeah, we were getting exciting about this for the simplicity, but we never managed to make this work. You can see the curve is almost flat at the bottom. This plot shows a bit more comparison with the three different setups: the from scratch UU and the LU and this big U, small U in between. So you can see the training loss. The green curve is the best. Look, if we just look at the training loss, and the blue one, the LU, gets the worst training loss. So that means the LU model does not adapt well to the image text dataset. But if we look at the downstream transfer performance with this model as the training progress, for example, this one, it shows ImageNet linear 10-shot accuracy. The UU, of course, starting from 0 and slowly catching up. And the pre-trained model, either locked or unlocked, they both start from a good point. Like this is about 70%. And the locked is flat across the training. But this fine-tuning setup, the representation quality goes down first, and then slowly catching up in the end, but still getting worse representation quality than the locked setup. So we just, so our hypothesis is that the image text dataset is very noisy, and it's not as accurate or as clean as a pre-training image and labels dataset. So this contrastive tuning stage may destroy the image tower and thus gets worse representation quality and leads to worse performance. Here you can see the comparison of the images. For example, from on the left-hand side, it's a few examples from the CIFAR dataset. You can see it has labels and with well-correlated images. And on the right-hand side, it's image samples from the Align paper, which is collected from internet with the images as well as alt text available on the web page. So you can see that sometimes the image and text are relevant, like motorcycle from the wheel versus this image, but sometimes the image and text are completely unrelevant, like this one. Second one, some layer 4 version as of this date. So this is from Wikipedia. So you can find many examples like this from websites. So those are likely the examples which may destroy your representation. So we did a bit more ablation tests of this model. So the first question we try to answer is it due to labels in pre-training? So we take a few models without labels during pre-training. For example, this algorithm. It's a pre-trained on ImageNet 21K with labels, and Dino and the Moco V3, both are self-supervised learning methods on ImageNet without seeing any labels. And you can see that all of the three models perform similarly on the full ImageNet fine-tuning task. And then we try to adapt those models on the lit tuning setup, like we train a text tower pairing with Moco V3, and we train a text tower pairing with Dino. And in all of those setups, we can turn them into a zero-shot classifier. and all three models achieving more or less the same performance. So that means the labels in pre-training is not the key leading to good results. And we also tried to ablate, for example, for the algorithm model, we use ImageNet instead of ImageNet 21K, or we switch from ImageNet to Places dataset. And both needs to very off results, either very high or very low. And then second, we try to deduplicate the data set because for pre-training the model on image text pairs with close to 2 billion image text pairs. So this may include the duplicates in the pre-training set and the downstream data sets. So we try 3 setups. The first line is without dedupe. And the second line is dedupe the downstream test splits with a pre-training data set. And we remove the 76K examples from downstream examples from the upstream data set. And because the duplicate can be N-to-1 mapping, so we remove the 2.6 million examples from the upstream data sets. And the second setup is we try to dedupe against the downstream training and downstream test both splits, and to make sure this has a full coverage. So we want to go with high recall, low precision. We can remove as many as possible, even though there could be precision error, but we want to make sure the recall is high so that we don't leak the training images or the test images. And in this setup, we remove 3.6 million duplicates from the upstream data set, and those corresponding to 220K examples in the downstream data sets. And you can see that on ImageNet and on the cross-model retrieval, image to text, text to image, there's some quality drop, but it's not huge. And in our paper, we always use the most strict setup, the third row, dedupe against train and test to make sure we don't overestimate the numbers. And here we try to ablate the VIT architecture. And you can see that by switching from VIT to MLP mixer or to ResNets, we see the performance drop, even though those models performing more or less the same on ImageNet adaptation. And this plot shows the impact of different model capacity. So on the x-axis, you can see that when we're scaling up the image tower from the base to the giant, and on the y-axis, you can see when we're scaling up the text tower from base to huge. So you can see when scaling up the image tower, we observe huge boost at on the leftmost, and then going to rightmost, actually it's diminishing. The boost is not that high. The same story applies to text tower. Going from base to large is a big jump in this stacked bar, and going from large to huge, it's quite small everywhere. Okay, so finally, I want to introduce a few interesting properties of the model about multilingual. So since we lock the image tower, it's a pre-trained VIT-G, and the web and the internet image text pairs, they actually consist of many languages. So in this setup, the locked image tower, they see similar images, and those similar images actually was mapped to the same or very close position in this shared space, in this image text contrastive learning embedding space. And then for the text tower, it sees all of the languages, and it tries to align the languages to the frozen image embedding. And we can use this setup to use a text tower, text encoder, to anchoring concepts coming from different languages, but describing the same concept. It's just like a kids, they can learn multilingual by seeing the same image or by seeing the same animal. They can understand what does the different languages mean. So we tried our model for multilingual tasks. We translate ImageNet into many languages. And then in this setup, we try to pre-train models using this locked and unlocked setup of lit. And actually the model can do pretty good, especially when pre-training on this multilingual setup. On Chinese, on Japanese, the lit model is doing pretty good, and it can understand the prompt in those local languages. Okay, finally, I want to show some demos of the lit model. So this one shows richer information, like it has an image with the Honda Civic parking in front of 2 towers, and the model can actually understand this rich information like color and the buildings behind. And the bottom example is a blue car parking in front of green and pink walls. And second example is counting. Like here, an image of 7 cats, or an image of 9 cats, an image of 3 cats. So yeah, the model is not perfect to doing counting task. It's just for this example, or it ranks the 7 and 9 pretty high, but the model does not distinguish 7 and 9. And in the bottom, it can recognize a cow sleeping on the beach almost for free. So we also tried the same model on many existing vision models, and they are doing pretty good. So it's not as we thought, it's out of distribution image, because cow normally sleep on the grass, but not on the beach. Actually, this is not that hard if the model has been tuned in this way with a massive amount of image text pairs. And those are multilingual examples. And top one, it's Chinese New Year celebration, and it can rank in the Chinese candidate very top. And the bottom, it also ranks this Thai World Festival very high, as well as the local language. It's not top, but it's also among the top 3 candidates. And of course, there are failure cases. By the model is actually having trouble recognizing those emoji with whether they are yawn or cry, smile. Okay, finally, let's take a look at this example. So it's a Apple image with iPod tag on top. So we are editing the text candidates, and let's see how the model reacts. Yeah, the model is managed to recognize this is an Apple with an iPod sticker on top. So it's doing a pretty good job with all of those different edits on the prompts. Yeah, that's all of my talk. And those are a few links that could be relevant. So if you want to play with official VIT models or the VIT-G models, or the very recent LIT models, you could try to take a look at the Vision Transformer GitHub or the Big Vision GitHub. We plan to release VIT code, the LIT code, and as well as models to the Big Vision. And the models has already been live on Vision Transformer GitHub, as well as this live demo. Thanks a lot.
Thank you very much, Dr. Zhai. I think this is a very interesting talk. First, any questions from the audience? Actually, I do find the lead model and its contrastive training strategy very interesting. I do have some small questions. So first is that I remember you show an Appalachian study where you train the capital U with the lowercase u, and seems the accuracy first drops and then increase, right? To me, it sounds like a forgetting issue that perhaps the prepared knowledge in the image encoder can help in the in this 10 short task, but if you don't fix it, maybe during the fine tuning, it's for the pre-trained knowledge is kind of forget during this fine tuning, and then gradually grows. But if you totally fix it, this knowledge can be preserved. That's my first intuition, because when I was working on some lifelong learning problem, especially involving any domain shift, this training curve also happens before.
Yeah, it's quite interesting because in a recent paper, named the Basic, they tried to take a pre-trained model on JFT and then doing similar fine tuning. They did not lock the image tower. They fine tune both image tower and text tower, but they have to use a mixture of the image text dataset and a JFT dataset for the fine tuning stage to make sure this curve does not drop. Otherwise, I believe they observe similar behavior and the model does not perform well. So they have to adding back the data again to your new program so that you can you will not forget this information. I think it's quite interesting. There should be other methods of doing this, of solving this forgetting other than locking, because locking indeed the gradient does not propagate back through the image tower. So you also restrict the capacity of the learning process. So for example, if we can using residual adapters to keeping the pre-trained weights, but still making using of fine tuning, I believe we can get even better results.
Yeah, I totally agree. You have a question?
Could you repeat the question? I cannot hear it. Yeah, maybe closer to the microphone, or maybe Wu Yang, could you help repeat the question?
You want to try here?
Hello, can
Hello.
you hear me?
Yes, yes, I can hear now.
So I'm wondering if you try to fix several layers and fine-tune the other layers, like instead of fixing all the layers or fine-tune all the layers, did you try like this that partial fine-tuning thing?
Yeah, that's a very great question. We have not tried that. So all we tried is in this plot, you can see all of those different letter combination. Small u is from scratch, big U is fine-tuning everything, and L is locked. So we have not tried that, but we have been discussing about that setup for a while and have never got time to try that. So yeah, what we found could even further improve is we first lock the image tower like LU, and then afterwards we unlock the image tower. So we do this multiple stage thing, and then we unlock the full network. We unlock a few layers like the top layers after the first round of pre-training to make sure the initial stage, the image tower does not get destroyed. Yeah, that's a very good point, and we have not tried that, but we think this could be useful.
Yeah, thank you. So because we have previous experiments, like we found that lock several previous layers and unlock last few layers could help future transfer. Yeah, so I found that might be helpful for this task as well. Yeah, so that's basically my question. Yes, thank you.
Yeah, thanks for sharing this knowledge. So I think for few shot, it's a slightly different scenario, because for few shot, one faces this overfitting problem. If you don't lock a few layers, there are so many parameters, then you suddenly get overfitting and you cannot adapt well to few shot. And in the lit setup, it's slightly different problem. It's rather forgetting than less than overfitting problem. But I think for either case, this should be useful.
Oh, okay. We have one more question.
Hi. I wonder if you can hear me.
Yes. Yes.
Yeah. Hi. Thank you very much for your nice presentation. So I noted there are very interesting phenomenon for your demo part. So basically, you're feeding the model like for the image classification data. But it seems like for the iPod, like Apple, so that demo, you'll also be able to like recognize something like very similar to OCR, but you are not feeding any OCR data into it. So does the model actually have the capability of recognizing the text by only feeding the model with the image classification data?
Yes, that's a great question. We observed this emerging property with large-scale pre-training. So we tried quite a few examples as fun side project. We have not write it in our paper. So the model gets the capability of doing OCR. So if you think about the dataset, we pre-train the model. It's from websites, like a user have this image, and then user while developing the website, they write alt text field. So you can think of maybe 10% or 5% of the users, they input the text which they marked on the images. And so those actually become in the training data, and the model actually gets trained on those supervised and noisy examples in an end-to-end manner. So the model gets this capability. And this has also been reinforced by a recent publication from DeepMind called Flamingo. That's a generative model instead of discriminative ranking model. And that model also can recognize the text from the images. So I think the key ingredient is this noisy training data.
I see. Yeah, thank you very much for the answer.
Thank you.
Thank you.
Okay, I think due to limits, we need to shift to another speaker, but I think the lead work is really inspiring. Thank you very much, Xiaohua, again, for this great talk.
Thank you very much, and thanks everyone.
Thank you. And let me shoot. Hi, Dr. Liu, can you hear us?
Yeah, I can hear you.
And you want to share your screen?
Yeah, sure.
Thanks for joining us. And I will give a short introduction and we can get started.
No problem.
Hi, everyone. We are happy to have Professor Angie Liu here for our next speaker. And Professor Angie Liu is now an assistant professor in computer science department at the Johns Hopkins University. And before that, Dr. Liu was a postdoc in Caltech. And her research interest lies in machine learning algorithms for building more reliable, trustworthy, and human-compatible AI systems in the real world. Thank you very much, Dr. Liu.
Hi, it's a great honor to be here. So it's a pity that I cannot really be there in person. So I'm happy to answer any questions afterwards and also maybe communicate by email. I'll share my contact information afterwards. Today, I'm going to talk about uncertainty estimation and calibration under domain shift in vision. So vision has been a very important component to many applications that concerns significant societal impact and human safety. For example, self-driving car perception depends on image classification, segmentation, object detection, and so on. Control experts are also trying to use directly generate like control signals from vision signals. And finally, in healthcare, there's a lot of applications that's vision-based. For example, Google basically launched this like AI health tool for skin conditioning tracking. And also there are a lot of applications, X-ray images or radiology images for machine learning for healthcare. However, the conventional machine learning algorithms may not be directly used for those trustworthy and risk-sensitive kind of applications. The first failure mode may be our data may violate our assumptions. In conventional machine learning, you usually assume that training data is a very good representation of the testing. That's why we usually have training and then input a model and then test on the same distribution. While in the real world, it's like very common that you have very clean images in training, but then it's very blurry, it's very noisy in the actual test domain or actual application domain. It's also very easy to and cheap to collect data in black and white and 3D models and then have simulation in the synthetic domain. While in the real world, you have very colorful and noisy images. So people call it distribution shift, domain shift, dataset shift, etc. Another aspect of those applications is like they're possibly high risk and constraints associated with those applications. For example, a mistake in self-driving car perception may risk humans' lives. And also this machine learning for healthcare, we will assume that we want our model to have equal opportunity to produce equal opportunity for different groups of people. While in reality, you may have very few images from certain groups, and then how to generalize in a robust way, and then provide like fair kind of results to the different groups is a question. So I think one key aspect here is like, how do we extrapolate when there's domain shift? How do we extrapolate to the new domain? And then how do we actually quantify the uncertainty, produce a good model of confidence in the new domain? So let's say we have a very naive example to say it has a Mars rover and it sees some images on Earth. But then when it's actually deployed on Mars, you can see maybe something it has never seen before, like this kind of different color of different shapes coming rocks. And then the question is like, how do we generate confidence in the new domain? And I argue that if you have the right uncertainty and confidence and have right extrapolation in a new domain, we can do a lot of things. The first thing is like, if I fail, I probably can fail more gently. That means even though I cannot really recognize this weird rock, I will not recognize as something else with very high probability, with high confidence. The second thing is like, if we have the right amount of confidence, we may check the constraints and also the expected risks in a new domain. And so then we may satisfy those maybe constraints and also be accounting for those risks in a new domain. And finally, if we have the right confidence, we may collect new data, use those confidence values to collect more data for us to adapt and generalize in the new domain. So the high-level research questions I'm really interested in is how do we produce good model confidence under domain shift, under distribution shift, and how do we calibrate uncertainty to account for risks and constraints, and also how do we integrate methods into real-world applications. So in this talk, I'm going to mostly focus on the first question, which is the uncertainty estimation and calibration field. I'm going to talk about two works mainly. One is on the large-scale sim-drill domain adaptation, which we mostly account for epistemic uncertainty, while we want to account for the lack of target images. And then we also want to talk about a slightly less investigated domain, which is areotoric uncertainty in vision. And then we use this visual event understanding as the application to look at how these uncertain human judgments in labeling data, can we really account for that, and can we use this kind of data better? Let's first talk about the first part, which is a paper that's titled Distribution Robust Learning for Uncertainty Calibration under Domain Shift. So I have talked briefly about the meditation and using this example. It's easier and cheaper to get synthetic images than dealing with like noisy, colorful data in the real world. And then domain adaptation is relatively well studied in vision. So there's a recent framework for domain adaptation. It's called self-training. And the idea is like we first use like labeled source images to do some initial source training, and then apply this model to make predictions on target images. We look at uncertainty and confidence, and then we choose the ones the model is currently more confident about. We generate those pseudo labels. For example, in this case, horse, and it is more confident, and then we use the horse actually as actual labels, and then merge that into our source training data, and then we retrain the model. And in next iteration, similar things, we make predictions on target images. We look at confidence, which pick the one that's more confident, the model is more confident about, and then use that label as prediction as the true label, as if it's a true label. And then generate pseudo labels, and then merge that into another round of source training models, and then do this again. So we may have figured out, like, in this case, it's highly dependent on the confidence. However, when we look at confidence generation on the distribution shift, on data shift, there's this like very interesting work in NeurIPS 2019, looking at, can you really trust your model on uncertainty? Can we, how to evaluate like predict uncertainty under distribution shift? So they basically add different noise, different kind of blurry, and also like possible distortion of the images. And then they basically evaluate the accuracy and also the ECE score. ECE score is the expected calibration error. So with the shifts intensity like higher and higher, you can see the accuracy just get lower and lower, and more importantly, the ECE get higher and higher. So that means like you're less and less calibrated when you have a larger and larger shifts. So that means like you basically cannot really trust your models like uncertainty, especially when the shift is large. So then the question is like, can we obtain the right uncertainty on the shifts, and how do we do that? So let's start with a very simple example to motivate what we are going to propose. So let's say there's a very simple regression example. We have like 2 domains, source and target. We want to map our input signals to some alpha signals Y, and this is our source data. So then it's very tempting to just use, a simple linear regression model. Here we are using the also the dashed line to show the possible confidence interval. So depending on the source data, you may very easily get a model like this, right? And then it's just extrapolate very optimistically to a target domain. However, when you actually see the green triangles, which are the target domain data, and also you can see the possible ground truth curves of this model, and you can see that especially a very big difference between your projected uncertainty and also projected predictive labels, and also the ground truth labels in the target domain. So, and imagine how bad it can be if you're really in a safety critical or high risk kind of application domain. So maybe a better solution is like we be more conservative in the domains that's farther away from your training, and then have a larger confidence interval there. Let's see why it's better. So in this case, we have labeled source data. We have X and Y in the source domain. And then we also have some input source and target distribution. We have some information about the target distribution. And then this proposed solution basically says, I look at like this is the distance between target and the source, and then I project for a larger confidence interval. I'm more conservative when my source data is not supporting. It's like a lack of the take data support in the source domain. So I'm going to first review the proposed predictive form before we really justify why it's the right thing to do. So the idea here is actually very similar to a conventional logistic regression. Besides that, you have this density ratio that try to adjust your uncertainty in your prediction. So this density ratio basically is source over target. And then these are from this input source and the target domain distributions. And you have this uncertainty goes up with the density ratio goes down. So then the intuition is like, oh, we give uncertain prediction on data samples that's farther away from my training data. And how are we measure this kind of farther away, this kind of distance, quote unquote distance? We use this density ratio. So this source over target density ratio would just directly adjust your predictive uncertainty. And let's see how, why is the right thing to do? So we're going to now justify it. Before we go to the math, I'm also going to introduce a simple classification example with only 2 data points. Let's say you have only 2 data points in your training data, yellow banana and red apple. And then the goal is to the prediction model such that in this kind of target domain, you still get a good prediction. But in target domain, you only know the input, you do not know the labels. So then you know there's a shift between the source and target color distribution. And then you want to know, given this color, whether it's a nano, and given this color, whether it's an apple label. So a very conventional machine learning, popular machine learning mechanism is called empirical randomization. The idea is I look at my training data, I assume this training data basically approximate what is true data distribution I care about. Then I directly use this training data to optimize the empirical risk. So I have some F predictor that minimizing my empirical expected loss. And the idea is I assume data approximates the distribution I care about. So then if you apply ERM directly to this very simple example, you'll see that, oh, then it's very easy to see maybe it's very probably if the color is yellow, it's a banana, while the color is red, is an apple, right? So then when you have a yellow apple in the target domain, you basically will say it's a banana with a very high confidence. So an alternative of a framework for ML is called distribution robust risk minimization or diverse risk minimization. So they're different names. It's actually a very classic framework. The idea is still similar. We start with some training data. But then we ask the question whether it's actually approximating the data distribution we care about. Maybe not, because data is always imperfect. It can be always imperfect, right, in certain domain. So then at least we can extract certain like feature statistics from it. And I use that to constrain my adversarial player when it's trying to play a game with the predictor player. The idea is like the adversarial can perturb data distribution while satisfying constraints from some feature statistics. So the definition of robustness here is basically says the predictor achieve its best payoff or this equilibrium when playing this game with an adversarial who is compatible with training data. So the training data will constrain the adversary while the predictor play a game with it. And the predictor then achieve the robustness if it's achieve the best payoff or equilibrium. So it's basically robust to the worst case data generation distribution in the adversary distribution. So a closer look in math is something like this. So you have this minimax game. Your P hat is your predictor who tries to minimize the loss. Your Q is the adversarial player who tries to maximize the expected loss. And then one thing to note here is like, now I assume there's no distribution shift. The data we have basically is from the training distribution. And also the loss we care about is also defined on the training distribution. So the data that constrains the adversarial player and the data that basically you calculate your loss on is from the same distribution. The question is like, what if they're not the same distribution and we need to account for possible distribution shifts. So when there's distribution shift, we still have this minimax game. The only difference here is now like the data I have is from source training data. So the adversarial still subject to the constraints based on source data. But the loss function I care about is actually on the target domain. I directly want to minimize certain loss function in a target domain, even though we do not have any test label data. So a recipe for using this framework is like, we need to choose a loss function that you care about. We need to choose certain constraints for the adversarial player. What kind of feature function you want to use there? Maybe it can be like linear, can be higher domain, higher moments and the kernel functions, or even like deep neural networks. And then we can derive a learning algorithm on top of that. So there are certain nice properties for this kind of framework. One thing is like there are some analytical form for this predictor, so that when you choose certain feature functions, like in this case, I choose a phi function that I care about, and then I make sure this expectation under this Q, which is the adversarial distribution, is equivalent to the expectation under this training data distribution, which is P tilde y given X. Under this kind of constraints for the adversary, we may directly derive an analytical form for this solution. Then it's basically the parametric form I showed you before. So this exponential form with density ratio weighted is derived from this minimax framework. And that it has this property that it can adjust uncertainty according to the density ratio. Similarly, if we're doing regression, you can also have a very similar analytical form. I'm going to kind of skip this part since we're mostly talking about classification tasks in this talk. But just one thing is like you can directly derive a Gaussian distribution from this framework, which can be very useful in many robotics or control kind of applications when you're doing dynamics modeling. So the next property is very important here, which is the key thing we're talking about, which is uncertainty. So I show that this density ratio may have this effect, and let's see how it works. So in this classification problem, you have this two extreme case of only two data points. But then if you know like there's a shift between source and target domain, then you may, when you have a yellow apple in your target domain, even though you may still give a very like wrong label, which is a banana, the confidence is much lower because this density ratio is smaller. since is like source over target. And then in the regression example, similarly, we have shown this before. So even though the linear regression optimistically project and extrapolate to a target domain, this reverse regression kind of framework will become more and more uncertain when the target domain is farther and farther away from the source. So given a X data point, that's maybe is more probable in target domain and less probable in the source domain, you may get a small density ratio, and then it will basically induce a larger confidence bounds. So the takeaway for this method is like, we want to give uncertain predictions on data samples that's farther away from training data, unless being told now to give a more prior knowledge by the user. So when there's no prior knowledge, can be very uncertain when the data point is really far from this training data. Since we're talking about the vision tasks, there's a very big issue here is like, if you look at the predictive form, right? You see this exponential family, which is nice, but then you see this density ratio. People will ask, how do you really get at if X is the images, is high dimensional images, right? So in this case, if you are dealing with those kind of black and white versus like colorful images, how do you really get this value? So in high dimensions, density ratio estimation by itself is a very hard problem. So are we really solving an even harder problem by introducing this kind of component in this kind of predictive form? So the answer is like, well, there's a way to deal with it. So we propose this differentiable density transformation kind of framework. The idea is like we use a neural network to basically do the density transformation when it can be trained alongside with the classification network. So in the classification network, we basically follow the predictive form in the right top. So it takes like source labels and source images into input and then use this predictive form. While the discriminative network basically try to learn a classifier, a domain classifier or binary classifier, try to differentiate source images from target images. And then according to Bayes' rule, you can basically estimate your density ratios according to this kind of conditional probabilities you get from a binary classification network. And then this kind of signal is directly input into the target predictor. One thing to note here is also like we can, in the target predictor, when you look at this density ratio, you can also regard it as a trainable variable. So that means the density ratio itself can get learning signals from the loss function for training this target predictor. So that means when you train this discriminant network, it get both learning signals from the binary classification and also the target prediction tasks. So it has two learning signals. So then when these two networks like are learned like end to end, are trained in an end to end way. So then the idea is like remind training and then how self-training depends on the uncertainty and confidence. Uncertainty and confidence is very hard under domain shift. We introduce distributed robust learning. And here when we plug in DRL to self-training domain adaptation, we basically first use training data, source training data to train a model, and then we use DRL model to predict like pseudo labels, and then we merge that into the previous training data and then form a new source distribution, and then retrain the DRL model again, and then repeat that in the next iteration. So we basically regard every round of self-training as a domain shift problem, and then we train and update a DRL model on top of that. So let's see how it works in practice. In this case, we use data from Visual DA of 2017, and then compare to two most relevant baselines, CBSC and CRST. And we call method distributed robust self-training, and which is the red line. So we first look at accuracy. So even though we care about uncertainty estimation a lot, we like envision accuracy is still very important. So we look at accuracy. And you can see that this red curve is like above the baselines. So this is the close to the state of art, like self-training domain adaptation result in Visual DA. And then if you take a closer look at this plot, you can see that Actually, it's very close to the baseline after maybe 10 epochs. So we also want to zoom in to the harder examples to see how our method works in the relatively like harder examples. I can see in this case that density ratio is small when it's very hard. Remember, density ratio is like source over target. So it's small, that means this data is very not probable under the source domain distribution. That means it's like far away from the source, right? So the small is like harder examples or farther away examples from training data. And you can see the gap of accuracy is even larger in the like harder examples in the right hand side, in the left hand side, sorry. So the smaller density ratio is the harder example is, or the farther away is, and the method is even have a larger like gap there. And this is also similar to look at how the accuracy like margin went from hard to easy. So the performance gap is larger on the hard examples. And finally, we want to really care about the uncertainty and want to know whether we have like better uncertainty estimation result and more calibrated result. In this case, we look at the test barrier score. Barrier score is a very important like metric for evaluating the level of calibration. And the lower the barrier score is, the more calibrated the uncertainty is. And we can see that with more along all the like epochs, DRST get a lower like barrier score like earlier in the training process. We also want to know like whether density ratio really makes sense in this case. Remember that even though we derive this parametric form from DRL, which is the minimax framework we talk about, but then the density ratio now is not directly learned using a conventional density ratio estimation, but it's using a neural network, which is a binary classification, and then also it's trained end-to-end with a image classification method. So we want to know whether the density ratio here is still meaningful and what is capturing the relation between source and target domain. So in this case, we show two examples of the data like railway image. The source domain data is in the right top corner, which is like a rectangle. So that the right hand image is like closer to the typical source domain kind of chain or railway. So it also has a larger density ratio here. Well, the left-hand side is a noisy and less typical railway because it covers also a lot of human in the platform, right? So so we have a like smaller density ratio, so which makes sense because it's farther away from what is how the railway or the train is represented in the source domain. And finally, we also want to look at some interpretability results. This is using the Graham, and then we can see that with this image with both like bus and the truck in it, DRST captures the right label and also has a better coverage of the region for the truck. So the takeaway for this part of the work is that we look at like self-training and how it's affected by the model confidence, and we realize that model confidence are important for it. We introduce distributed robust learning and use that to generate this better uncertainty and a more calibrated uncertainty for the sample selection. And we achieve the sort of self-training accuracy in domain adaptation, and also we look at whether the density ratio is actually showing the relation between target domain and the source domain. So for target images as far, it's actually giving like a smaller density ratio values. So in the previous part of the talk, we mainly talk about epistemic uncertainty, which means that one original definition of epistemic uncertainty is like by collecting more data, the uncertainty can be reduced. So in this case, we will account for the lack of like target images. And if you can imagine, if you really have target images labeled data, you probably can reduce that uncertainty. So you can roughly say that's the epistemic uncertainty we're accounting for in the previous work. But then actually there's all kinds of sources of uncertainty, and there's one important source, is the intrinsic randomness. It's usually called aleatoric uncertainty. So this is relatively less like investigated in the vision domain. And then we also want to take a look at to see whether we can really evaluate and also account for this kind of uncertainty. So this work is on ambiguous images with human judgments for robust visual event classification. It's a collaboration with Professor Benver Min in the Hopkins University. So in this case, we want to look at this ambiguity of data in computer vision. So it actually largely exists. This human judgment, bias, and noise largely exist in vision data. And there are certain domains suffers more than others. For example, in this case, we look at situation recognition and event classification. So basically, it depends on the human's bias and background. They may label things differently when they look at the image and try to recognize what's the situation and event. And also another important application domain that suffer from this kind of intrinsic randomness is the medical diagnosis. So if you have images and you give that to the physicians or clinics, and then you want them to label the image, actually you can get very large variation in the possible like annotations. So in this case, example, we focus on the event classification. So these are examples showing you like wedding, birthday, and medical kind of events. And then we basically feed these images to human annotators to ask for their like human uncertain judgments. But then we also realize like we want to ask this question, like how can we account for this human judgment uncertainty? But we realize we do not really have very good data for it. You know, in image, like in conventional image classification kind of tasks, there's a lot of data. But then in this field, we want to study human uncertainty, or the ambiguity of data when it comes to human labeling bias and labeling uncertainty. We just do not realize we have a very good data set. So we first basically collect data set to study it. So in this case, we actually extract images from YouTube videos, and then we ask like human labelers to from 0% to 100%. Ask them to label their uncertain values, like confidence values, in terms like whether this is a birthday party image or not. And we basically have like 20, I think, event types in this kind of data set, and eventually get, I think, more than 10K, more than 10K like images, like pairs of like images and the event type pairs. And then we want to take a look at what are the sources of annotator disagreement? What are the sources of this kind of intrinsic noise and bias in the data? So we realize actually look at data and realize that there are multiple sources, and there are even more than that. So first one is like visual attention. So in this right image of the birthday image, it is actually a birthday party in the movie. But then people usually focus on the middle part of the image. They focus on which is a human conversation, but maybe ignore the birthday related signals in image. And then in this kind of cases, you get a large variation in the labels. And then background knowledge is also another big issue. So what big feature, right? Because people have different like background knowledges. So this image is from the wedding image is from Princess Aiko's like wedding in Japan. And if you really know the background knowledge, you can easily have very high confidence like labels. But if you do not have that knowledge, then you may have a very low confidence there. And also there is also cultural kind of bias in this case. And then certain uncertainty quantification strategies for humans. So different people have different like risk tolerance level or uncertainty tolerance level. So you may have a range that's all like a range of uncertainty or confidence level that's all like reasonable for different people. And then also another case is like people are just maybe careless, and then there's also definitely a big contributing factor, and then also a combination of all 4 possible like sources. And there are other things as well. We didn't really list here, but there are also other things. So So basically, we want to use this data to see like how previous pre-trained model, for example, performs in this kind of human uncertain judgments data, and also how do we really use this data? Can we use this kind of human uncertain judgment to do like cool things, right? So first, we want to see like how the pre-trained model, pre-trained method works. So I want to remind you that a perfectly calibrated method's accuracy will basically fall into the appropriate bins. So basically, we like chop the data into different bins according to the human uncertainty level or confidence level. And then if a method is calibrated to this kind of human uncertainty level, you basically will have the similar accuracy in that bin. For example, for the bin that's 40 to 60 confident in human judgments, then a calibrated model should be around 40 to 60 like accurate, percent accurate in that bin. That's one version of confidence calibration in the literature. So then we basically look at like the accuracy in each bin, right? And the top one accuracy basically is very bad in terms like calibration, while top 5 is much more calibrated in that way. And then you can see that especially in the more certain bins, like 80 to 100%, these 3 pre-trained models in grounded situation recognition basically are relatively more calibrated, but then in the less certain ones, bins, things are really bad there. And then we also want to know, like, can we really train, try different training like paradigms to basically better use this kind of human uncertain labels. So in this case, we try to train the model using only high certain labels, like the clean and standard data, versus we use like data augmentation, and also we use the data with human uncertain labels. And then we use these 3 type of data to train a model, and want to see how it works in different bins, and also how it compares to like evaluating on the standard data. And we can kind of conclude that training on this distributional, training on this like more uncertain distribution of signals, which is our DAI data, is more calibrated in the relatively certain bins. If you look at above 40, this 3 columns, and you can see that our model is basically relatively more calibrated than the training just using standard or using augmentation data. And then also something interesting is like, maybe it's also expected, like model trained using standard data have high accuracy in standard data, but very bad in the ambiguity data. While a model trained using the ambiguous data has better accuracy in the when we evaluate on the ambiguity data. And finally, we want to look at uncertainty estimation method to see whether those methods which claim to account for uncertainty quantification and calibration, whether they can really calibrate the model to the uncertain human judgments. So in this table, basically show compare training on standard data and training on the ambiguity data, and then we also compare like different kind of like model uncertainty estimation methods, including label smoothing, focal loss, relaxed softmax. Those are the more recent method that claims to account for and smooth and soften the predictions. And then we can see that model trained using the standard data fails to really achieve good accuracy on ambiguous data. And also the focal loss, which is the one that achieves relatively better like MSE for human uncertain judgment here, it's able to calibrate models trained on SD data to the uncertain human judgments. And then I also want to say this work is also relatively preliminary, and then there's still a lot of things unknown. And then so here's some basically like takeaway. One is like we can study a rhetoric uncertainty in vision by building data set with intrinsic noise. And in this case, we look at the human judgments, human uncertain judgments. And then it's possible to perform uncertainty calibration for the human uncertainty labels. We can see that the focal loss method is basically relatively effective in the calibration. But then there's a lot of caveats here, and also the future question we really want to ask is, can we use this data to train or calibrate models, we usually use this human uncertain labels so that it can contribute to a more calibrated model. Before we close, I also want to talk about basically mention another work on uncertainty labeling in my lab. So we're looking at like predictive inference under covariance shift with guarantees. So there are different kinds of guarantees for uncertainty estimation. And one important one is the coverage guarantee. That means you want your two label values to be covered in the predictive confidence interval with high probability. And then those coverage guarantees basically will be broken on the data distribution shift. In the right-hand side, you can see the figure. Under covariance shift, basically the coverage much lower than the ID case, the blue one. So and in this work, we basically look at, can we still really get coverage guarantees under like covariance shift, and we get a positive result there. So this paper will also be out soon. If you're interested, look out for the link as well. So the main takeaway for this talk is like in the first part, we look at how to deal with distribution shift in the principal way. We use this min-max gain to give a more uncertain prediction to the target data that's farther away, and we make sure the model extrapolate accordingly to those density ratios. And we show that's very essential for uncertainty modeling. And we use a domain adaptation application to show the benefit of a more conservative uncertainty. And also in the second part, we look at a rhetoric uncertainty, which is a different type of uncertainty, but it's also very interesting and important in trustworthy AI applications. And then we show that building data set for studying this different kind of source of uncertainty still has a long way to go, but we are starting to work on it, and we see some promising results as well. So with that, I want to basically thank you for your attention, and this is my email, and yeah, I'd like to take any questions. Thanks.
All right. Thank you very much, Dr. Liu. This is a great talk, and I wonder if any questions from the audience first. I do have a small question. When you talk about where you train a discriminative model to estimate the density, I have a curious question. For example, like on the Visa 17 data set, usually we want to transfer from the synthetic data to the real data. Sometimes we actually, of course, for the experiments, we do use the real images for the evaluation for the final accuracy, but in the real case, sometimes we don't have those real images for to train a discriminant network. So I was wondering, in the real cases where you only have the synthetic images, how would you do this density estimation?
That's a very good question. So yes, currently we do assume we have some data from the target domain, so we kind of can train the discriminator between source and target. But then in many cases, you may not even do not actually even know what's your target domain. So it's more like a discussion between domain adaptation versus domain generalization. While in domain generalization, you do not know the target, but then you maybe assume that target is certain combination of multiple source or has some relationship with source, but you do not have data from it. You basically directly try to learn some invariant representation that's generalizable to certain target domain. And I would say that's a very relevant follow-up work that we're basically working on. So we're trying to build in certain invariance to the representation learning, and then so that we still have assumption that target is not too difficult, too far away, right? Still there's some relation between source and target, but then in that case, we do not really need like exact target domain. We can directly use the invariant learning framework to learn something that's shared, that's generalizable to target. So that's something I would say domain adaptation versus domain generalization. They're very related, and then generalizing to that domain is very straightforward follow-up work that we're still working on. Yeah.
Sure, I totally agree. Yeah. Okay. If no more questions from the audience, I think we'd like to thank Dr. Liu for a great talk, and we really enjoyed it. Thank you very much.
Thank you so much. Yeah, yeah. Let me know if you have further questions, and then yeah, happy to also communicate by email if that's the case.
Yeah,
Thanks.
definitely. We should follow up. Thank you very much.
Thank you. Bye.
Bye. Have a good day. Bye. All right, so I think this is our closing time, and thank you very much for joining us. And I think we are very likely to continue our workshop in the next year. So keep tuning to both our workshop and challenges. And thanks for coming.